Preface. Dear reader, this book is the culmination of nearly 4 years of research conducted in collaboration with a team of around 20 high-level international specialists and scientists. Its objective is unique: to shed light for you on the question of the existence or non-existence of a Creator God, one of the most important questions of our lives, which is being posed today in completely new terms. Our hope is that by the end of this reading, you will have in hand all the elements necessary to decide what seems most reasonable for you to believe. We have conducted this work as a rigorous investigation. We have always used rationality as our only compass and have sought to avoid two major pitfalls of our time. On one side, that of creationism, which rejects modern discoveries and adheres to fanciful beliefs. On the other, that of an extreme materialism which refuses to consider the implications arising from the latest scientific advances. Until recently, believing in God seemed incompatible with science. Now, unexpectedly, science appears to have become God's ally. Materialism, which has always been a belief just like any other, is seriously shaken as a result. This book is a 180-degree panorama of current knowledge regarding the existence or non-existence of a Creator God. It is not limited to science, but also explores what philosophy, morality, history, and even some of humanity's great enigmas have to say on the matter, because the question is far too important to be confined solely to the realm of science. To our knowledge, no other book like the one you are holding in your hands exists. We have aimed to make it easy and enjoyable to read for all, while ensuring accuracy. The chapters are independent, so readers can approach them in any order of their choice. We have done our best. We leave the rest to your free judgment. Michel-Yves Bolloré and Olivier Bonassis. Introduction. 1. The Dawn of a Revolution. Never before have so many spectacular scientific discoveries emerged in such a short period of time. These discoveries have overturned our view of the cosmos and forcefully put the question of the existence of a Creator God back on the table. Physics, much like an overflowing river, has surged beyond its banks into the realm of metaphysics. This powerful intersection reveals the necessity for an intelligent Creator. For nearly a century, groundbreaking theories have sparked robust intellectual debate. Above all, this is the narrative we aim to explore in this book. We are living through an amazing moment in the history of knowledge. Advances in mathematics and physics have turned questions once thought to be forever beyond the reach of human knowledge, questions about the nature of time and eternity, its beginning, its end, and the improbable unfolding of the fine-tuning of the universe and of the appearance of life, into objects of scientific study. These scientific advances, which began in the early 20th century, brought about a complete reversal of the thinking of previous centuries when science was considered incompatible with any discussion of the existence of God. Revolutionary discoveries and their impact. The thermal death of the universe. A result of the theory of thermodynamics, first developed in 1824 and confirmed in 1998 through observation of the accelerating expansion of the universe, thermal death, also known as heat death, implies that the universe had a beginning. But every beginning presupposes a creator. The theory of relativity, developed by Einstein between 1905 and 1917, and since confirmed many times over, this theory affirms that time, space, matter, and energy are interrelated and that no single one of them can exist without the other. This finding implies that if a cause exists at the origin of our universe, it is necessarily atemporal, non-spatial, and immaterial. The Big Bang. Theorized in the 1920s by Friedmann and Lemaitre and confirmed in 1964, the Big Bang's account of the beginning of the universe is so specific and spectacular that the theory sparked an explosive controversy in the world of ideas, so much so that in some countries, scientists risked their lives to study and defend it. we dedicate an entire chapter to exploring the overlooked or concealed persecution and execution of scientists. Tragically, these persecutions highlight the profound significance of the discoveries made by the scientists involved. The fine-tuning of the universe. Generally accepted since the 1970s, the question of the fine-tuning of the universe poses such a problem for materialist cosmologists that to evade it they are forced to invent purely speculative, unverifiable models of the universe, such as multiple, successive, or parallel universes. Biology. Toward the end of the 20th century, advances in biology showed that the universe needed even more fine-tuning to create the conditions for inert matter to come to life. In fact, what we once thought of as a short step between the most complex inert matter and the simplest living matter now seems more like a leap across an immense chasm, a leap that certainly could not have been made, according to the laws of chance, alone. And while we still do not know how that gap was bridged or, a fortiori, how to replicate such an event, we do know enough to appreciate its infinite improbability. In earlier centuries, however, a series of scientific discoveries seemed to go against faith. Since the late 16th century, a series of scientific discoveries appeared to challenge the foundations of belief in God, unsettling the pillars of faith. Here's a brief historical overview. The discovery that the Earth revolves around the Sun rather than the opposite, Copernicus, 1543, Galileo, 1610. The mathematical description of a simple clockwork universe, Newton, 1687. The Earth's extreme old age, much older than just a few thousand years, Buffon, 1787, Lyell, 1830, Kelvin, 1862. The concept of a universe entirely governed by physical laws eliminates the need for angels to maneuver the planets, Laplace, 1805. The view that life emerged and developed over millions or even billions of years, Lamarck, 1809, and others. The idea that this evolution was based on natural selection, not divine intervention, Darwin, 1859. The rise of Marxist dialectical materialism with its seductive promise of a world of equality and justice, beginning in 1870. The ideas of Freud, around 1890, who postulated that man is not even the master of his own thoughts and for whom this new science offered man a life free from prejudices. Somewhat smugly, the Viennese psychoanalyst Sigmund Freud spoke of the three humiliations that modern man had suffered thanks to Copernicus, Darwin, and himself. The wounds to our pride were indeed accumulating. Humankind had lost its place at the geographic center of the universe. It had lost its sense of superiority in discovering that, according to the proponents of evolution, it had descended from apes, and finally, it had even lost autonomy and responsibility for its deepest thoughts through the theory of the subconscious. Thus, over the course of 3 centuries, from Galileo to Freud via Darwin and Marx, much of the knowledge that once seemed part of the bedrock of Western thought was shaken, causing confusion among religious believers. In the end, there was actually no reason to be disturbed by these new discoveries, as those which eventually proved to be true did not, in fact, contradict the faith in any way. Many believers, however, lacked the perspective and knowledge needed to see this, and as a result, these scientific advances were greeted with disbelief and even hostility. After all, it takes a great deal of effort to abandon old certainties and redraw one's mental geography. Materialists, on the other hand, embraced these discoveries with enthusiasm and used them to justify their theses. Their cause was greatly aided by the technological advances of the time, which simultaneously eradicated famine and epidemics in the West, cured most diseases, extended lifespans, reduced infant mortality, and provided an unprecedented abundance of material goods. Science forced religion to retreat, while material abundance made turning to a god to solve humanity's problems seem unnecessary. It was in this favorable climate that materialism came to reign supreme in the intellectual world of the first half of the 20th century. Under these circumstances, many believers in the West found it even easier to abandon their faith, as it now seemed superficial and implausible. Those who remained often developed an inferiority complex in the face of the ascendant rationalism. Avoiding scientific and philosophical debate, they retreated into their own private sphere, where they were expected to stay, lest they face mockery, disdain, or hostility from the intellectually dominant materialist class. The second half of the 20th century saw the twilight of this seemingly irresistible materialist trend. Until the middle of the 20th century, human reason remained boxed in by three analytical viewpoints that cut it off from any spiritual aspiration: Marxism, Freudianism, and scientism. However, cracks soon started to appear in the structure, foreshadowing what would ultimately lead to a complete collapse. During the first half of the 20th century, belief in a simple, mechanical, and deterministic world was shattered by a more precise confirmation of the principles of quantum mechanics and its postulates of indeterminacy. In 1990, the failure and collapse of the Soviet Union and the parallel abandonment of Marxist economic doctrine by the Communist bloc in Asia proved to the world the falsity of Marxist dialectical materialism. Eventually, this collapse would expose the economic, political, and human horrors to which it had given birth, such as the gulags, where death tolls ranged in the millions. This disillusionment coincided more or less with a re-evaluation of the theories of Freud. For example, French author Catherine Meyer's influential Le Livre Noir de la Psychanalyse, The Black Book of Psychoanalysis, published in 2005, took a critical look at the rise and fall of this intellectual idol of the mid-20th century. Though Freud has been knocked from his pedestal, his legacy lives on in the concepts of permissive education and sexual liberty. All this has significantly shaped the modern West. A column published in the French magazine L'Obs in the autumn of 2019 and signed by 60 psychiatrists and psychologists called for the exclusion of psychoanalysts from France's universities, public hospitals, and judicial institutions. The simultaneous destruction of these three intellectual pillars of materialism was not accompanied by a return to faith, but it did considerably weaken the materialist system of thought. The system was further undermined by the cosmological discoveries referenced earlier, which provide compelling scientific evidence supporting the existence of a creator God. As a result, these theories initially faced significant resistance from atheist scientists who sought to deny this evidence for as long as possible, beginning in the 1930s. We will devote a long chapter to this resistance on the part of certain materialists, a resistance that has taken various forms, from support for alternative speculative theories to counter the Big Bang, such as the Big Crunch or multiple universes, to the deportation and even execution of a number of scientific experts in the USSR and Germany. Such reactions say much about people's limited ability to accept scientific theories that challenge their beliefs. We need this review of intellectual history to situate our discussion within its historical and ideological context. If it was challenging for believers to accept Galileo and Darwin, whose discoveries were not inherently at odds with their faith, how much more arduous must it be for materialists to accommodate concepts like the thermal death or fine-tuning of the universe into their belief systems? These revelations present formidable challenges to their worldview. Accepting these facts necessitates not merely an update in thinking, but a complete re-evaluation of their internal framework. Emotions can get in the way of accepting the truth. Our ability to accept a claim, scientific or otherwise, depends on more than rational evidence. Our emotions also come into play when we evaluate a claim and its conclusions. Some questions science asks today are emotionally neutral: why the dinosaurs went extinct, the origin of the moon, how water on Earth came to be, or why the Neanderthals suddenly disappeared. Of course, these questions spark lively debate among scientists who argue for differing, even opposing solutions. But in the end, everyone accepts the results of their intellectual efforts, since these subjects do not tend to bring our emotions into play. All that changes as soon as we step onto more delicate ground. Issues like global warming, the environment, nuclear energy, and Marxist economics certainly demand scientific answers, but these topics are so politicized that our intellects are not free to think about them in a normal way. Our passions, political opinions, and self-interest get in the way of our reason. The phenomenon is particularly acute when one broaches the subject of the existence of God, because what is at stake is not just some point of scientific data, but the very meaning of our life. The prospect of having to recognize, at the end of a long search, that they are creatures created by and dependent upon a creator is seen by many as a fundamental threat to their autonomy and freedom. For many people, the desire to be free and autonomous, to be able to determine their course of action entirely on their own with neither God nor master, takes precedence over everything else. Their inmost self recoils from this idea of God. To defend itself, it mobilizes all its intellectual resources to oppose the search for truth and to protect its own perceived independence and freedom. It is not surprising, then, that instead of stimulating thoughtful discussion, the subject often provokes reactions ranging from annoyed indifference to ridicule, contempt, and even violence. It is telling that we invest vast amounts of time and resources in searching for extraterrestrial life, as the Search for Extraterrestrial Intelligence Institute SETI program does, rather than dedicating even a fraction of that effort to exploring the hypothesis of a creator God. If God exists, is he not, in a sense, a supreme form of extraterrestrial? And yet, God's existence is more likely and more readily admissible, and the traces of his action in the universe are far more tangible than those of potential extraterrestrials. This imbalance points to a kind of fear. For a materialist, collecting traces of far-off extraterrestrial life is definitely thrilling, but it does not demand a re-evaluation of the meaning of existence. Becoming aware that God exists, on the contrary, carries the risk of serious interior disruption. So it is that ideology and emotion can prevent us from accepting facts and keep us from a clear-headed examination of evidence that might require us to revolutionize our understanding of the world. To make our intentions perfectly clear from the outset, the purpose of this book is not to militate for a particular religion, much less to engage in an analysis of the nature of God or his attributes. The goal of this book is to gather into one volume the most up-to-date rational arguments for the possible existence of a creator God. Defining what scientific evidence is. In order to firmly establish the value of the evidence we present, we must begin by looking at the nature of scientific evidence. To that end, we will examine the nature of evidence in general and in the field of science in particular. Next, we will consider the consequences that flow from two opposing theses or viewpoints: belief in the existence of a creator God versus belief in a purely material world. Materialism is, after all, a belief just like any other. We will see that these two beliefs have a variety of implications, each of which can be easily proved or disproved by measuring them against our observations of the real world. Part 1. An inventory of the most up-to-date scientific evidence. This portion of the book will consider the revolutionary discoveries mentioned earlier: the heat death of the universe, the Big Bang, the fine-tuning of the universe, and the anthropic principle, and finally, the question of the leap from inert to living matter. We will treat each of these topics in depth. Part 2. Evidence from reason outside the realm of science. Part 2 will study fields of knowledge other than science which nonetheless pertain to reason. In science, as in history or philosophy, it is always worth paying attention to anomalies or contradictions, that is, to facts that have no reasonable explanation in a purely material world. We will ask questions like, what is the basis for the Bible's often puzzling claims? Jesus, who could he be? Can the destiny of the Jewish people be explained in purely natural terms? What really happened at Fatima in 1917? Or, does mankind have complete freedom to define good and evil? We will also take a look at the current status and value of philosophical proofs for the existence of God and the renewed interest taken in them by mathematicians like Kurt Gödel. These considerations will furnish the reader with a varied survey of probative arguments that, taken as a whole, constitute a converging and convincing body of evidence. Part 3. Putting an end to the usual objections. We will conclude by addressing a range of arguments, both historical and contemporary, that assert the impossibility or unknowability of the existence of a creator God. We will consider claims like, if there were proof for God's existence, we would already know it. We don't need God to explain the universe. The Bible is nothing more than a collection of old legends riddled with historical errors. Religion causes wars, and, if God exists, how can we explain evil? We will address these questions sincerely, even if they are cliched, and provide thoughtful responses that rectify these common intellectual missteps. A sign of the times. You may notice that the greater part of the knowledge upon which we base our arguments dates from after the beginning of the 20th century. This was not a deliberate choice on our part, but rather serves as a confirmation that times are changing and that we are on the cusp of an intellectual revolution. A project based primarily on reason. The makeup of this book might seem unusual. Some readers may be surprised to find modern scientific knowledge alongside reflections on the Bible or the story of a miracle in Portugal. However, each of these concepts has its place in this book. The theory that nothing exists beyond the material universe implies that miracles do not occur and that even the most astonishing events in human history must be explained without relying on supernatural explanations. If we observe evidence to the contrary in the real world, then this would serve as strong evidence that the materialist theory is flawed. In the end, either God exists or he doesn't. The answer to these stark alternatives exists independently of us, and it is binary, either yes or no. Until now, our lack of knowledge has been a serious obstacle to answering the question with confidence. But the emergence of a vast array of convergent evidence from various independent fields of knowledge has shed new and perhaps decisive light on the question. The Great Reversal. 5 centuries of scientific discovery behind the rise and fall of materialist thought. Copernicus, 1543, Heliocentrism. Galileo, 1610, Strengthening Heliocentrism. Newton, 1687, Universal Gravitation. Buffon, 1787, Calculating the Earth's Age. Laplace, 1805, Determinism. Lamarck, 1809, Evolution. Darwin, 1859, Natural Selection. Marx, 1870, Dialectical Materialism. Freud, 1896, Psychoanalysis. Thermodynamics, 1824–1906, Carnot, Clausius, Boltzmann, Kelvin. Quantum Mechanics, 1900–1930, Planck, Dirac, Bohr. Relativity, 1905–1915, Einstein. Big Bang, 1922–1931, Friedmann, Lemaitre. Mathematics, 1931, Gödel. Biology, 1950–1980, Watson, Crick. Fine-Tuned Universe, 1935–2025, Dick, Carter, Feynman. 2. What is evidence? The purpose of our book is to provide an overview of the current evidence for the existence of God. It seems natural to start with evidence emerging from recent scientific discoveries, since science is universally regarded today as the most reliable source of knowledge. However, we will not limit ourselves to scientific evidence alone, as the importance of this question requires that we explore other areas of reason to see if they also support the arguments provided by science. While the meanings of the words God and science are generally clear, the terms evidence and proof are more complex. According to the Oxford English Dictionary, evidence is defined as the available body of facts or information indicating whether a belief or proposition is true or valid. However, further clarification is needed since evidence can be categorized into 2 types. Absolute proofs, often referred to simply as proof, exist in theoretical or formal domains such as mathematics, games, and logic. These proofs are definitive and incontestable because they result from a finite set of clearly defined principles, axioms, and rules. It should be noted that the well-known philosophical proofs for the existence of God discussed in Chapter 23, are considered by many to be absolute proofs, even if this view is not shared by everyone. Additionally, the renowned mathematician Kurt Gödel developed a mathematical proof for the existence of God, intending for it to be an absolute proof. While this proof remains debated, its reasoning has, to date, not been found faulty. See the chapter on Gödel. Relative proofs, often simply referred to as evidence, are those that exist in the real world. They are never absolute, since they rely on our inherently imperfect and incomplete understanding of reality. The purpose of this chapter is to clarify the nature and logical mechanisms of evidence and to assess the level of conviction or certainty that evidence can provide, especially in relation to our subject of investigation. This chapter is written to be as accessible as possible. However, readers who find it too technical may skip it, as it is not essential for understanding the subsequent chapters. Absolute proofs. Absolute proofs are familiar to us from our school mathematics, where we encountered examples like the Pythagorean theorem. This theorem demonstrates that, in Euclidean geometry, the square of the hypotenuse of a right triangle equals the sum of the squares of the other two sides. Demonstrated over 2,500 years ago, this proof has remained unchanged ever since. This example helps us immediately understand the characteristics of absolute proofs. They are accepted by everyone. One absolute proof is enough to demonstrate a proposition. Additional proofs are not necessary. They are universal. They are unchanging over time. They exist only in theoretical domains such as mathematics, games, and pure logic, fields of abstraction where there is complete knowledge of rules, axioms, and data. The principle of logic asserts that correct reasoning, when applied to data that are fully known and exact, leads to a valid conclusion. For example, in Euclidean geometry, it can be demonstrated that a triangle with 3 equal sides has 3 equal angles, or that, in a particular chess scenario, a checkmate in 3 moves is inevitable. An absolute proof remains absolute regardless of the number of reasoning steps required to reach it. However, absolute proofs do not exist in the real world, as we will soon explore. The 125 pages required by English mathematician Andrew Wiles to prove Fermat's famous theorem are a remarkable example of mathematical dedication. To demonstrate this theorem, stating that x to the n plus y to the n equals z to the n is impossible if n is greater than or equal to 3, Wiles worked for years weaving together arguments from various branches of mathematics before publishing his proof in 1995. Each argument was rigorously examined by experts in the relevant fields, and the proof's accuracy was unanimously accepted by the scientific community. Yet an experimental verification of this theorem remains impossible, making this achievement all the more extraordinary. Relative proofs. Relative proofs, or evidence, cannot be absolute because, in the real world, correct reasoning applied to accurate data does not necessarily yield a correct conclusion. Ignorance of this counterintuitive fact has, unfortunately, frequently led to terrible mistakes. Reaching a correct conclusion requires that accurate reasoning be applied not only to some correct data, but to all data relevant to the problem. Unfortunately, in the real world, we never have complete knowledge of reality. As a result, we never possess all the necessary data. Even if we did have all the data, the huge volume would be too vast to fully account for. A true and tragic anecdote illustrates this surprising reality. In the 1950s, wheat harvests in China were very poor. Agricultural officials explained to Mao Zedong, the founding leader of the People's Republic of China and chairman of the Chinese Communist Party, that sparrows were consuming a significant portion of the sown seeds, and this was true. Mao then reasoned that if the sparrows were eliminated, these seeds would no longer be eaten, which was also true. He concluded that the harvest would increase by the equivalent quantity of wheat that would have come from the spared seeds. But this proved to be completely wrong. Mao's reasoning overlooked just one piece of the data. While sparrows do eat some seeds, they also consume worms and insects that are far more destructive to crops. The decision to eradicate sparrows was implemented nationwide in 1958 during the Great Leap Forward without prior experimentation. The result was a catastrophic famine that led to millions of deaths. This story illustrates how a single ignored piece of data can lead to outcomes that are the exact opposite of expectations. Consequently, in the real or empirical domain, absolute proofs do not exist, or if they do, they are generally inaccessible to us. What we have instead is evidence of varying degrees of strength, the accumulation of which can nevertheless lead us to a conviction beyond all reasonable doubt. Since evidence in the empirical world is not absolute, it is essential to address this limitation by increasing the quantity of evidence and diversifying the sources. This approach helps to more firmly establish the thesis that the evidence is meant to support. An example of empirical evidence, the realm of justice. The realm of justice, which depends on the presentation of evidence, serves as an excellent example due to its universal familiarity. In a criminal court trial, the prosecutor must provide evidence of the accused's guilt. This evidence may be physical or circumstantial, and its strength can vary. It might include DNA traces, blood group analysis, fingerprints matching those of the accused, or footprints at the scene. There may also be evidence stemming from a motive, along with testimonies placing the accused at the crime scene. The credibility of a testimony depends on factors such as the witness's personality and reputation. Testimonies from multiple independent witnesses, particularly those who are unrelated and unfamiliar with one another, are generally considered more reliable than those from witnesses within the same family group. No single piece of evidence can be considered absolute. Even strong material evidence, such as a trace of DNA, could theoretically be part of a well-executed conspiracy. However, when the evidence is abundant, compelling, convergent, and independent, jurors may reach an inner conviction beyond any reasonable doubt, allowing them to decide on the accused's guilt. This example demonstrates that in the empirical domain, it is essential to gather as much convergent and independent evidence as possible to achieve a conviction beyond any reasonable doubt. Evidence in science. We have explored two types of proof that are familiar and relatively easy to understand: absolute proofs in mathematics and relative proofs or evidence in the realm of justice. Now we will examine how proofs are approached in science, a field of particular importance for us, as these are the proofs we will use in this book. The natural sciences belong to the empirical domain where, as we have seen, absolute proofs do not exist. According to Karl Popper, in the empirical sciences which alone can provide information about the world in which we live, proofs do not exist, if by proof we mean a fact that establishes the truth of a theory once and for all. Thomas Kuhn suggests that the scientific community operates within paradigms, widely accepted theories that are not absolutely proven. These paradigms persist until a crisis arises, prompting a revolution that leads to the adoption of new paradigms that provide a better explanation of reality. Therefore, in seeking to explain a phenomenon, the scientific approach proceeds as follows. The first step when observing a phenomenon that we want to explain is to create a theory. This theory is a representation of the universe, and it contains its own logic, which usually generates implications. These implications are essential because they allow for testing the theory's validity or invalidity. For example, the theory that the Earth is round has many implications, one of which is that by traveling in a straight line, one would eventually return to the starting point. This implication is verifiable and was confirmed by Magellan's voyage, providing a final proof to complement all the relative evidence already known since antiquity. This implication also allowed Christopher Columbus to set out from the Canary Islands to reach the Indies. The second step is to compare these implications with observable data from the real universe. If observed reality contradicts the predicted implications, it can be concluded that the theory is false. If the implications align with reality, it can be concluded that the theory is possibly true. The more confirmed implications a theory has, the more firmly it can be considered established. These first two steps form the minimal foundation of any scientific theory. Fortunately, in many cases, it is possible to go further. The third step, which is not always possible, is to construct a mathematical model of the theory to study its functioning and examine its predictions. These predictions are then compared to real-world observations. If the model aligns with reality, the level of proof is greatly strengthened, particularly if the model predicts unexpected outcomes that are subsequently verified. The fourth step is experimentation. This final step offers a very high level of proof if the theory can be repeatedly verified. An example: Newton's theory of gravity. Newton's theory of gravitation provides a clear example of this four-step process. According to the story, Newton observed an apple falling and wondered why it fell straight to the ground. Step 1. The theory. From this initial observation, Newton formulated a theory suggesting that bodies attract each other with a force dependent solely on their mass and the distance between them. Step 2. The implications. As the first verifiable consequence of his theory, Newton observed that it was the apple that fell to the ground, not the other way around, since the Earth's larger mass attracted the smaller apple. Additionally, an apple in the southern hemisphere also fell toward the Earth, even though it appeared upside down from the perspective of an observer in the northern hemisphere. Thus, the initial implications of his theory aligned with observable reality. Step 3. The mathematical model. Newton developed a mathematical model for his theory, proposing that the force of attraction between two bodies was proportional to their masses and inversely proportional to the square of the distance between them, expressed as F equals G times m over d squared. Using this model, Newton calculated planetary orbits, predicting elliptical shapes, an insight that neither Copernicus nor Galileo had envisioned, though Kepler had observed them in Mars's orbit. By refining his model, Newton ultimately created a predictive calendar of lunar and planetary eclipses. Step 4. Experimentation. Newton's calculations and predictions, which were verifiable at the time, proved to be remarkably accurate. The theory's alignment with reality was successful and, even more impressively, it yielded unexpected predictions that were later confirmed. As a result, the scientific community regarded Newton's theory as proven to the highest possible extent within its domain. Later, Newton's theory of gravitation was refined by Einstein's theory of relativity. While Newton's model remains an excellent approximation in most cases, Einstein's framework provided a more precise understanding. This progression illustrates how scientific models evolve, with each new theory building upon and improving the accuracy of its predecessor. Scientific theories can be classified into groups based on the level of evidence supporting them. The strength of a theory is determined by the number of validation steps it has successfully passed. Depending on whether it is validated by 2, 3, or all 4 of the steps listed previously, a theory's strength can be categorized into different groups from Group 2, the strongest, to Group 6, the weakest, with Group 1 reserved for absolute proof. Group 1. Absolute proof. This type is found only in theoretical or formal domains. Group 2. Theories that can be tested against reality, that are mathematically modelable, and that are subject to experimentation. This group encompasses fields like physics, mechanics, electricity, electromagnetism, and chemistry. The evidence in this category is so compelling that it approaches absolute proof and is rarely contested, though it may be refined by future convergent models. Group 3. Theories that can be tested against reality, that are modelable, but that are not subject to experimentation. This group includes fields like cosmology, climatology, especially climate change research, and econometrics. While these theories may not be testable in the traditional sense, they can be modeled, and the predictions generated by these models can be verified. The level of evidence supporting theories in this group is strong. Group 4. Theories that can be tested against reality that can be subject to experimentation, but that are not mathematically modelable. This group includes fields like physiology, pharmacology, and biology. Although these theories may not be modelable, their reliability is reinforced through repeated experimentation, which provides strong verification. The level of evidence in this group is high, as with Group 3, but achieved through different means. Group 5. Theories that can be tested against reality, but that are neither modelable nor subject to experimentation. While lacking the probative strength of previous groups, this category encompasses many widely accepted scientific fields. Examples include Darwinian evolution, which for a long time was neither modelable nor subject to experimentation, paleontology, for example, theories about dinosaur extinction and Neanderthal disappearance, and origin-related questions, for example, the origin of life on Earth, the Moon, and water on our planet. These theories are validated solely by comparing their implications with observable aspects of the real world. This group also includes the thesis, there is a creator God, and the thesis, nothing exists beyond the material universe. Although neither of these theories is modelable or testable, they do carry logical implications that can be compared to reality. This topic will be explored further in the next chapter. Group 6. Theories without implications and that are neither modelable nor subject to experimentation. These are purely speculative hypotheses. They generate no observable implications that can be tested against reality and, therefore, hold no level of validation. One example in this group is the multiverse theory, also known as parallel universes. This theory has no observable implications. Another example is the theory of the existence of extraterrestrials, which likewise has no observable implications and therefore remains pure science fiction. Table summarizing the 6 groups of evidence. The table, included in the bonus PDF, summarizes the 2 domains and the 6 groups of evidence, ranging from absolute proof in the formal domain to the absence of proof in the final group, based on a feasible classification. This approach aligns with the views of Austrian-born philosopher of science Karl Popper, 1902 to 1994. According to Popper, for a thesis to be considered scientific, it must stem from a theory grounded in observation and must be potentially refutable. In other words, it should have enough observable implications that could prove it false. For Popper, refutability is the essential criterion for determining whether a theory or thesis qualifies as scientific or not. According to Popper's criteria, multiverse theories would not be considered scientific since they lack observable implications. In contrast, the thesis of God's non-existence would be, as it has many implications. It is worth noting that many scientists and philosophers also consider the existence or non-existence of God to be a scientific question. Richard Dawkins, a leading figure in contemporary atheism, argues this view in his best-selling book, The God Delusion. He writes, "The God hypothesis is a scientific hypothesis about the universe which should be analyzed as skeptically as any other." Page 18. He further asserts, "Either God exists or he doesn't. It's a scientific question. One day we may know the answer, and meanwhile we can say something pretty strong about its probability." Page 54. Dawkins adds, "Contrary to Huxley, I shall suggest that the existence of God is a scientific hypothesis like any other. Even if hard to test in practice, it belongs in the same TAP or temporary agnosticism box as the controversies over Permian and Cretaceous extinctions." Page 56. Following this in-depth exploration of the nature of evidence and recognizing that real-world evidence is never absolute, we find that ultimate conviction arises from the presence of multiple, independent, and converging pieces of evidence. This is why our research cannot rely solely on scientific evidence. It must also incorporate insights from philosophy, morality, history, and even historical enigmas. The chapters in the second part of this book are therefore not digressions from the scientific field, but rather reflect a deliberate intent to gather rational evidence from a variety of independent perspectives. At this point, the reader should understand that the purpose of this book is not to offer absolute proof that compels universal agreement on the existence of a Creator God. Rather, it seeks to present numerous, converging, and independent pieces of evidence that can inspire conviction beyond all reasonable doubt. Ultimately, at the end of this investigation, everyone must reach their own conclusions. If they find the evidence compelling enough, they will act as both judge and jury and make the leap to conviction. With the nature of what evidence is now clarified, the next step is to explore whether the thesis of a Creator God has observable implications in our world. 3. Implications arising from the two theories, a Creator God exists versus nothing exists beyond the material universe. When we reflect on the existence of the universe, two possible theories are on the table. One, the materialist view asserts that nothing exists beyond space, time, matter, and energy, while the other postulates the existence of a Creator God. As discussed in the previous chapter, neither theory can be subject to experimentation or mathematically modeled. Therefore, the only way to decide between them is by comparing their implications with what can be observed in the real world. But do such implications exist? The following table, also included in the bonus PDF, presents the implications associated with each of the two theories. If nothing exists beyond the material universe, which constitutes the materialist thesis, then 1. The universe cannot have had an absolute beginning. 2. The universe cannot end in thermal death. 3. The laws of nature, arising solely from chance and necessity, have no particular reason to favor the emergence of life. 4. Miracles cannot exist. 5. Prophecies and revelations cannot exist. 6. Good and evil, having no transcendent source, are subject to limitless democratic decision-making. 7. Spirits, the devil, angels, demons, etc., do not exist. If the universe originates from a Creator God, then 1. The universe can be expected to have a purpose. 2. It is likely to be ordered, beautiful, and intelligible. 3. It can be expected to have had a beginning. 4. Miracles are possible. 5. Prophecies and revelations are possible. There is a common, though mistaken, belief that the existence or non-existence of a Creator God would have no observable implications in the real world. This chapter will argue that such implications do in fact exist, that they are both numerous and significant, and that some of them, once thought to lie beyond human understanding, have now entered the realm of scientific discussion. Upon examining the two corresponding columns, 3 key observations emerge. First, the reader will notice that the number of observable implications is significantly high, which increases our chances of deciding between the two opposing theories. The more implications we can identify, the greater the likelihood of confirming or refuting one of the two theories. Second, the implications derived from these two theories are not equally attractive. The materialist theory that nothing exists beyond the material universe is particularly interesting since it generates a larger number of implications that are both clear and precise. Therefore, the most promising way to affirm the existence of a Creator God is to try to disprove the materialist theory. Since the two theories are mutually exclusive, disproving one would validate the other. Third, while neither theory can be directly mathematically modeled or tested, both have implications that can be compared with observable reality, placing them in Group 5 of our evidence framework. In this group, theories are evaluated based only on how well their implications align with observable facts. Thus, the theories, there is nothing beyond the material universe, and the universe originates from a Creator God, can legitimately be included in Group 5. Each of these implications will now be analyzed in depth to assess their origin and value. 1. Study of the implications of the thesis, nothing exists beyond the material universe. If there is nothing other than the material universe, then 1. The universe cannot have had an absolute beginning. This is true for two reasons, one philosophical and the other scientific. A. Philosophical. As early as 450 BC, the Greek philosopher Parmenides argued that, from absolute nothingness, nothing can emerge. Ex nihilo nihil fit. And no other philosopher has ever seriously challenged this principle. B. Scientific. One of the most established laws of the universe states that nothing is lost, nothing is created, that matter and energy are linked, and that their total remains constant. Consequently, any variation in total mass energy is deemed impossible. This is, however, not entirely accurate in the case of an expanding universe like ours, because the resulting creation of space leads to the generation of vacuum energy and causes photons traveling over long distances to lose energy, redshift. Therefore, the emergence of mass energy from nothing at the beginning of the universe would directly violate this law. This implication is critical to our study because it presents a binary choice. If we accept the proposition that if there is nothing beyond the material universe, it cannot have had an absolute beginning as true, the corollary follows. If the universe had an absolute beginning, then a creator exists. Although this idea has been known since time immemorial, it was long dismissed as having little merit, since it was regarded as undecidable and beyond the reach of human knowledge. What is remarkable today is that the question of the universe's beginning has become a scientific matter, supported by substantial evidence, which will be discussed in Chapter 7. This development has transformed it into a question that can be answered. It is unsurprising that materialist scientists contest these statements as they are driven by necessity to do so. An absolute beginning to the universe implies the existence of a creator, an unacceptable conclusion for many. Consequently, they often favor alternative hypotheses, even those lacking a solid scientific foundation, such as the multiverse theory. 2. The universe cannot end in thermal death, since such an end implies an absolute beginning. The second law of thermodynamics, as established by Carnot and Clausius, states that in any closed system, entropy increases over time unless there is an external input of energy or information. This law applies to the universe in the same way it applies to a candle that gradually burns down and will eventually be entirely consumed if left to burn. Looking forward, entropy increases, leading to a future in which the universe is completely worn out. Conversely, when we trace entropy backward in time, we see that order increases, but only up to a finite point. This suggests that it is inconceivable for an isolated system to have been degrading indefinitely. As materialists like Ernst Haeckel noted in response to the findings of Boltzmann and Kelvin, if the second law of thermodynamics holds, it implies a beginning for the universe. If the universe had existed eternally, it would already be used up. Convinced by this line of reasoning, the Marxist philosopher Friedrich Engels wrote to Karl Marx on March 21, 1869, "The original state of great heat from which everything cools is absolutely inexplicable. It is even a contradiction and thus presupposes the existence of a God." Engels further argued that the second law of thermodynamics must be false because accepting it would imply a beginning to the universe and, by extension, a creator, an idea incompatible with his dialectical materialism. 3. Deterministic laws apply universally and things are distributed randomly. If there is no creator God and the universe is purely material, it must be governed by immutable laws, excluding any purposeful design. All processes within the universe would therefore operate solely through chance and necessity, and, as a result, the laws of the universe could not be particularly favorable to human existence. Consequently, the existence of fine-tuning and the anthropic principle can only be explained by adopting the highly speculative multiverse theory. 4. Miracles cannot exist. If the laws of the material universe apply universally, miracles are impossible, and reported miraculous events must be attributed to errors in judgment or deception. 5. Prophecies and revelations cannot exist. For similar reasons, prophecies or revelations, foretelling improbable and unpredictable future events, are impossible. Any that do arise can only be attributed to luck, credulity, or scheming. 6. Good and evil are not absolute and are therefore open to unlimited democratic decision-making. 7. The spirit world, including devils, angels, evil spirits, possessions, exorcisms, does not exist. 2. Study of the implications of the thesis, a creator God exists. Conversely, if the universe originates from a creator God, then 1. The universe can be expected to have a purpose or end goal. If the universe's creation is the result of intelligent intent, it would be logical for its evolution to be guided by an underlying order, progressing toward a predetermined direction. 2. The universe can be expected to be ordered, beautiful, and intelligible. If a perfect and intelligent God created the universe with the intention of fostering complexity and the emergence of humanity, it is logical to find order, harmony, and intelligibility within it. 3. The universe can be expected to have had a beginning. If the universe originates from a creator, it is reasonable to assume it had a beginning. 4. Miracles are possible. Miracles could occur either through primary causes, overriding the usual laws of the universe, or through secondary causes, providential occurrences. 5. Prophecies and revelations are possible. A creator God, being omniscient, would have knowledge of the future. Therefore, prophecies and revelations would be possible. 3. What a coherent materialist must accept as true. Based on the implications we have reviewed, a coherent materialist must first believe in the exclusively material nature of the universe and reject the existence of any spiritual beings, such as God, devils, and souls, beliefs that are relatively simple and easy to uphold. However, to remain consistent, a materialist must also accept and uphold a series of observable and demanding statements such as, the universe had no absolute beginning. The universe is not heading toward thermal death despite widely accepted views to the contrary. Billions of parallel or successive universes exist, even though this hypothesis lacks serious scientific support, as it is the only way to account for the fine-tuning of the universe and its exceptionally favorable conditions for human life. Some of the greatest laws of physics, considered universal and immutable, have been violated. For example, the principle of conservation of mass energy at the universe's beginning. Philosophically, in the absence of a transcendent basis, the concepts of good and evil can be defined indefinitely and solely through democratic consensus. Miracles, prophecies, and revelations are merely illusions or forms of deception. Coherent materialists reflecting on these points will realize the numerous extraordinary assertions and propositions they are required to believe, making the term unbeliever totally inappropriate in their case. We will now begin by examining the two main beliefs underlying materialism, that the universe did not have an absolute beginning and that it is not heading toward thermal death, two statements that, as we will see, are quite likely to be false. Evidence within the sciences. 4. The thermal death of the universe. Story of an end. Proof of a beginning. From the fireplace to the stars, conceptualizing the thermal death of the universe. The universe is like a fire crackling away in a fireplace. Subject to the laws of thermodynamics, both are destined to burn themselves out over time. As we watch the fire, we notice that the logs burn up and are gradually consumed by the flames. Eventually, only a handful of embers are left smoldering, until they too begin to go out one by one. We can deduce that in a few hours' time only a heap of cold ashes will remain in the fireplace. But there is another important conclusion we can draw from our observations. Since the fire is being consumed at a measurable rate, it cannot have been burning forever. If it had always existed, then it would also have burned down and gone out an infinitely long time ago. We can deduce, therefore, that the fire was kindled by someone at some particular point in the past. The same goes for the universe, which is consuming itself at an observable rate. If it had always existed, it would already have arrived at its exhaustion point, and therefore its end. This is why the heat death of the universe implies that there was an absolute beginning. Introduction. Paradoxically, this fascinating, even explosive subject of the heat death of the universe has caused less of a stir among intellectuals than even the Big Bang, itself a source of much debate and controversy. Is it perhaps more anxiety-inducing, even subconsciously so, to study the death of the universe than its causes? Yet the discovery of heat death has several crucial implications and constitutes one of the strongest pieces of evidence for a beginning to the universe. It brings to the fore the complex notion of entropy, which is linked to the irreversibility of time, the common thread that runs through this chapter. What if, to better understand its origin, we leafed through the script of the universe, starting with its denouement? What does the future hold for our universe? After 2 centuries of scientific advances bearing on this question, the near unanimous scientific consensus is that the universe will completely end in an unavoidable heat death. Our Sun, which has existed for 4.5 billion years, will continue burning for about that long again before transforming into a red giant, engulfing the Earth and Mars, and then a white dwarf before finally going out. It's the same story for all stars. All over the universe, they will run out of fuel and burn out, like logs slowly burning down in a fireplace. All stars burn their hydrogen, irreversibly transforming it into helium. The Sun burns 620 million tons of hydrogen every second, transforming it into 615 million tons of helium. The other 5 million lost tons are the energy the Sun radiates into space. Though this important discovery, made in the second half of the 19th century, took several decades to become established, it has since been confirmed by all subsequent theories and observations. It logically leads to a profound change in our vision of the world. 1. History of the discovery of the thermal death of the universe. Sadi Carnot founds the new field of thermodynamics, 1824. It all started in 1824 in Paris. In his first work, Reflections on the Motive Power of Fire and on Machines Fitted to Develop That Power, the 28-year-old Sadi Carnot laid the foundations of an entirely new discipline. Though the term thermodynamics was not coined until more than a century later by William Thomson, later known as Lord Kelvin, Carnot is the true founder of this field of science, which ultimately proved as fundamental from a theoretical point of view as it is productive in its practical applications. To take just one example, we can thank Carnot for the first scientific account of heat engines, the theoretical basis for automotive and jet engines. He died very young in 1832 at the age of 36, leaving behind very promising and fundamental but unfinished work. Rudolf Clausius takes up the torch defining the second law of thermodynamics, 1865. Utilizing the theoretical toolbox left behind by Carnot and building upon his work on thermal machines, Rudolf Clausius integrated the contributions of Lord Rumford, who demonstrated that friction produces heat, and Hermann von Helmholtz, who established the principle of conservation of energy, which includes heat as a form of energy. In 1865, Clausius postulated a new universal law that asserts that, without the input of new information or external energy, every isolated system will experience an irreversible increase in what he termed entropy, derived from the Greek word for transformation, as it evolves from an initial state toward a state of final equilibrium. As a consequence, any return to the original state is impossible. Clausius' daring theory became known as the second law of thermodynamics, and scientists were eager to test the validity and universality of this law. Ilya Prigozhin, the 1977 Nobel Prize winner in chemistry, is undoubtedly the modern thinker who has thought more than anyone else about the second principle and its profound consequences. Therefore, the dynamic eternally opposes the second principle of thermodynamics, the law of irreversible growth of entropy formulated by Rudolf Clausius in 1865. Concerning the determinism of dynamic trajectories, a completely inexorable determinism of the processes that level out the differences of pressure, temperature, and chemical concentration, and which irreversibly lead the isolated thermodynamic system to its state of equilibrium, of maximal entropy. In other words, the notion of entropy is valuable for giving a new momentum, a new perspective on how to envisage the end of the universe. Ludwig Boltzmann creates a model of entropy and arrives at strong conclusions, 1878. Building on the work of Clausius and his own research into the kinetic theory of gases, Boltzmann demonstrated that every isolated system can be modeled as an increasing function, S, as the system moves toward equilibrium, according to the formula S equals K log W. S stands for entropy, K is Boltzmann's constant, and W is the myriad possible states of all atomic or microscopic elements. Einstein called this equation, which is engraved on Boltzmann's tombstone, the most important formula in physics. It is in fact a revolutionary idea which proves that the disorder characterizing this or that object can only statistically increase, never otherwise, never the opposite. Helmholtz, 1854, and Lord Kelvin developed the idea of a thermal death of the universe. In an 1854 article, Prussian scientist Hermann von Helmholtz went straight to the point. The universe has only one possible end, heat death, when the temperature of the whole universe will approach absolute zero. Von Helmholtz explained that the stars will progressively go out one by one, and the temperature of the entire cosmos will decrease until the universe would be condemned to a state of eternal rest. A few years later, Lord Kelvin went on to flesh out this idea of the universe's thermal death. Arthur Eddington summarizes the concept as the arrow of time, 1928. Sir Arthur Eddington demonstrated that the second principle of thermodynamics implies the existence of an arrow of time indicating that time flows in one direction. In other words, there is a forward directionality to time which can be likened to the trajectory of an arrow. We have seen how entropy must increase in an isolated system. Therefore, if we measure the entropy of an isolated system at two different moments, we can tell which moment preceded the other, and therefore which direction the thermodynamic arrow of time is pointing. If we apply this concept on a universal scale, we can talk about a cosmological arrow of time. This was a profound and radical discovery that carried with it important metaphysical and philosophical implications. In one stroke, it invalidated the many cyclical views of the universe, such as the myth of the eternal return in ancient and Hindu metaphysics. The novelty of the concept and its striking consequences go some way towards explaining why this great law of the universe was received with great reticence and even met with stiff opposition. In spite of its important claims, it took more than 50 years for it to be recognized and accepted by the whole scientific community. These implications certainly challenge what we thought we knew. The first explosive consequence for metaphysics: the universe must have had a beginning. From a materialist perspective, the universe is a giant closed system that contains everything there is. Nothing exists outside of it. That means the universe is just like our fire blazing in the fireplace or the candle that slowly burns down. If we look toward the future, all energy will sooner or later be completely used up. By this logic, conversely, if we look toward the past, the universe must have had a beginning because it is impossible to imagine a closed system that has been endlessly consuming itself over an infinitely long span of time. If that were the case, it would have been used up an infinity of time ago, and there would be no one left to tell of it. To put it in mathematical terms, Infinity minus t equals infinity. Whatever finite time t we subtract from infinity, we are always left with infinity. Therefore, if the universe had been expending its usable energy for an infinitely long time, it should already have exhausted it. However, this is not the case. The universe, therefore, must have had a beginning. According to the Kalam cosmological argument, this absolute beginning to the universe must have a transcendent cause. Whatever begins to exist has a cause. The universe had a beginning. Therefore, the universe has a cause. A second, even more revolutionary consequence. From its origin, the universe was highly ordered. In 1878, Boltzmann recognized that the entropy of the universe must have been extremely low at its inception. His insights were later confirmed by the work of Roger Penrose. Remarkably, at the moment the universe reached its lowest entropy, everything in the primordial cosmos was likely organized with an almost unfathomable precision. This raises the question, how could such order arise? Despite Boltzmann's extensive research, he could not provide a formal proof for this phenomenon, and it took more than a century for the concept of fine-tuning to develop. Tragically, even though Boltzmann was undeniably ahead of his time, the intense criticism he faced from some colleagues took a toll on his already fragile psyche, leading to his death by suicide in 1906. A chorus of opposition against Boltzmann's discoveries. Henri Poincaré. Boltzmann's calculations implied that time was irreversible. However, for Poincaré and the majority of scientists at the time, there was nothing at all about mechanics that implied the irreversibility of time. Ernst Mach. The great Austrian scholar Ernst Mach, whom Boltzmann was once expected to follow as head of the departments of philosophy and history of science at the University of Vienna, swore to silence this petty researcher whose ideas are so dangerous for physics. A committed materialist and supporter of the Paris Commune, Mach would not accept Boltzmann's work and contradicted all his public remarks. Ernst Haeckel. Significantly, other experts began to realize that this new concept of the irreversibility of time implied the universe had a beginning, challenging their core beliefs. This realization motivated the esteemed biologist Ernst Haeckel to devote a considerable portion of his academic career to disputing the validity of the second principle of thermodynamics. Friedrich Engels. Friedrich Engels, the co-founder of Marxism, maintained that time was cyclical. He fought with all his might against the idea that there was an origin to the universe, since this idea threatened his arguments for dialectical materialism. Svante Arrhenius. In his Evolution of Worlds, the great Swedish chemist and 1903 Nobel Prize winner betrayed his philosophical prejudices when he wrote, "If Clausius were right, however, this heat death, we may object, should have already occurred in the infinitely long space of time that the universe has been in existence. Or we might argue that the world has not yet been in existence sufficiently long, but that anyhow it had a beginning. In that case, all the energy would have originated in the moment of creation. That is quite inconceivable." This position is surprising coming from a major scientist and a Nobel laureate to boot. His prejudice against the existence of God leads him to claim that since nothing can have been created, the universe could not have had a beginning, and therefore that the discoveries of thermodynamics are incomprehensible. The hypothesis that a God both exists and created the universe clashes with his principles. Marcellin Berthelot. The famous French chemist Marcellin Berthelot joins our long list of famous detractors. He developed an account of chemical phenomena in terms of the general laws of mechanics and was violently opposed to Pierre Duhem, who proposed, in collaboration with Willard Gibbs, a theory of chemical reactions based on the first and second laws of thermodynamics, an approach that has come to be called chemical thermodynamics. Since Duhem's conclusions were in conflict with his own, Berthelot, who was then Minister of Public Education, did not allow Duhem to defend his doctoral thesis, and he was forced to choose another topic. Berthelot later made amends for holding Duhem back. The early Albert Einstein. Albert Einstein was also long opposed to the idea of the irreversibility of time and universal expansion, but once the evidence became undeniable, he changed his mind on both subjects. At the beginning of the 20th century, Planck used the second law of thermodynamics to explain black body radiation. Einstein, who when studying the photoelectric effect in 1905 had interpreted these packets of energy as quanta, ended up declaring the second law of thermodynamics the first law of all science. More consequences of the second law of thermodynamics. Conscious of the philosophical implications of the discoveries of Carnot and Clausius, by the end of the 19th century, many intellectuals had taken a radically pessimistic view regarding the destiny of the cosmos, which seemed doomed to slow and inevitable decay. But others saw this in a more positive light, thinking that the arrow of time and the impossibility of eternal cycles made our history much more interesting. Nevertheless, it would be an error to think of the second law of thermodynamics as only a source of pessimism and anguish. For certain physicists, such as Max Planck and above all Ludwig Boltzmann, it is also the symbol of a decisive turn. Physics could finally describe nature in terms of becoming. Like the other sciences, physics would be able to describe a world open to history. History, it seems, is not doomed to repeat itself after all. Universal recognition of the second law of thermodynamics. The principle of the physical world's increasing entropy, which evolves globally in a single direction, has never been seriously challenged. In fact, today this is one of the most solidly established laws of physics. And with the help of statistics, it is possible to demonstrate that the probability of a return to an earlier state is all but infinitely low, growing less and less probable the larger the system is. The eminent astrophysicist Arthur Eddington is famous for his categorical commentary on the subject. I believe that the law that posits that entropy is perpetually increasing occupies a superior position among the laws of nature. If one of you demonstrates that your theory disagrees with the equations of Maxwell, too bad for the equations of Maxwell. But if your theory contradicts the second principle of thermodynamics, I can offer you no hope. Eddington's absolute conviction is evident beneath his irony. Curiously, at the time when entropy was discovered, most scientists were convinced that the universe was eternal. Surprisingly, none of the logical consequences were drawn from the discovery and acceptance of the second law of thermodynamics. The general belief remained that the universe is eternal, and there was no large-scale discussion of the theoretical hypothesis of a beginning. This definitely had something to do with philosophical a priori assumptions, but it was also due to the simple fact that, in the years 1915 to 1925, cosmology was not yet considered a real science. The following anecdote is revealing. Ernest Rutherford, then one of the most brilliant physicists in Europe, forbade all discussion of cosmology in his laboratory on the grounds that it was pseudoscience. Professor Stephen Weinberg of Harvard University, Nobel Prize-winning scientist, explains that in the 1950s, the study of the early universe was widely regarded as not the sort of thing to which a respectable scientist would devote his time. Nor was this judgment unreasonable. Throughout most of the history of modern physics and astronomy, there simply has not existed an adequate observational and theoretical foundation on which to build a history of the early universe. Hubble's discovery in 1924 that other galaxies exist, along with Lemaitre's initial works on universal expansion published in 1927, rooted in Einstein's theory of general relativity, were pivotal for establishing cosmology as a recognized scientific field. However, it took many more years before a cosmologist was nominated for the Nobel Prize. Friedmann, Lemaitre, Hoyle, and Gamow deserved one, but the Nobel Committee did not yet recognize cosmology as a science. This did not begin to change until 1953, the year Hubble died unexpectedly of a stroke while a candidate for the Nobel Prize. Furthermore, between 1931 and 1965, lively debates on the hypothesis of the Big Bang overshadowed all other approaches, so much so that during these years, the consequences of the second law of thermodynamics were not the subject of debate, and the idea of the beginning of the universe remained unimaginable to most scientists. Specialists in entropy are not the only ones with something to say about the beginning of the universe. Theoreticians of entropy were not the only ones to imagine that the universe had a beginning. Many others had foreseen it, including astronomer Heinrich Olbers in 1823, writer Edgar Allan Poe in his fascinating essay Eureka, published in 1848, astronomer François Arago, mathematician Bernard Riemann in 1854, and astronomers Vesto Slipher, who taught Georges Lemaitre, and Willem de Sitter. Their hypotheses were dismissed as fantasies and baseless daydreams that could not withstand the weight of contemporary certitudes and a priori judgments. Author of the famous eponymous paradox that asks why night is dark, for if the universe were stable and infinite, as was then believed, then every single way we look should point towards the surface of a star, and the night sky should therefore be bright. Upon the confirmation of the Big Bang in 1964, partisans of the eternal universe proposed the Big Crunch. The Big Bang hypothesis was confirmed in 1964 with the discovery of cosmic microwave background radiation, CMBR, which closely matched the predictions made by Gamow and his colleagues. This finding appeared to decisively refute the arguments for an eternal universe, suggesting that the Big Bang represented an absolute beginning. Consequently, this led to the development of the Big Crunch theory, which posits a final collapse that is the opposite of the Big Bang. According to Einstein's equations of relativity, the speed and acceleration of the expansion of the universe depend on its density, its pressure, its spatial curvature, and the value of the cosmological constant. If the density of the universe is large enough, Big Crunch scientists suggested, the universe will, at first, inflate and expand, but then enter a period of contraction and retraction. For decades, this idea of repeated cycles seemed the most promising hypothesis for preserving the idea of an eternal universe. Everyone wanted to predict how the expansion of the universe would slow, and they tried to calculate quite precisely the critical figures beyond which the Big Crunch was inevitable. A dramatic turn in 1998. The accelerating expansion of the universe, 1998, and the collapse of the Big Crunch hypothesis. Contrary to all the hopes and efforts of materialist scientists, it was proved in 1998 by Saul Perlmutter, Brian Schmidt, and Adam Rees that the expansion of the universe was not slowing down as everyone imagined, but rather accelerating. This groundbreaking discovery earned the authors the Nobel Prize in Physics in 2011, and their findings have been further validated by the WMAP 2001 and Planck 2009 missions, which showed consistent measurements of an extremely small spatial curvature of the universe. As a result, it is now difficult to support the Big Crunch hypothesis. If we accept the notion of a permanent cosmological constant, the equations of general relativity align perfectly with the phenomenon of accelerating expansion. This is consistent with all our scientific observations, collectively suggesting that the expansion of the universe will continue indefinitely. Even if the universe contracted and then rebounded into a new period of expansion, it could not be eternal. The second law of thermodynamics in effect stipulates that each new cycle in time increases entropy, which results in longer and longer cycles. Consequently, by going back in time, the cycles would have been increasingly shortened until they got to the point where a cycle couldn't be any shorter, thus marking the beginning of the universe. The necessary hypotheses of dark matter and dark energy, a repulsive force. Our understanding of the evolution of the universe as a physical system is based on the theory of general relativity. According to the equations involved, the expansion rate of the universe is a function of its average energy density as well as of one of its geometric properties, its spatial curvature, and of the famous cosmological constant already mentioned. How can these be determined? Astrophysicists have observed that the structure and motion of galaxies do not align with expectations based on their measured mass. Much of the mass required to explain galactic motion appears to be missing. This paradox has led to the idea that most of the mass in galaxies exists as so-called dark matter. To explain the observed acceleration of the universe's expansion, the cosmological constant has to exist. Thus, it has been calculated that known matter, observable atoms, make up only 4% of the universe, while a little less than 26% is this dark matter, a mysterious form of matter that would explain the missing gravitational attraction. The remaining 70% is then a no less mysterious dark energy or vacuum energy, which corresponds to the famous cosmological constant and acts as a repulsive force opposed to gravity, explaining the acceleration of the universe's expansion. The existence of this dark matter and dark energy appears certain from the measurements and calculations that allow us to define them, but their nature remains totally unknown. Given that the universe is most definitely and observably expanding, the mystery behind the missing matter and energy just goes to illustrate the fact that a considerable part of the universe remains unknown. An end that seems inevitable, the heat death of the universe. While we still lack complete certainty about the nature of dark matter and dark energy, the best currently available data agrees that unless the laws of nature change over time, the universe will end in heat death. All stars will eventually be extinguished, every source of energy will be consumed, and the universe will grow colder and colder until it tends towards a temperature of absolute zero and a state of maximum entropy in which no further thermodynamic reactions are possible. It is estimated that this dark era will occur around 10 to the 100th years from now. However, even before that, approximately 10 to the 30th years from now, the remaining energy will be insufficient to support life. There are several alternative versions of this final act, such as the Big Rip, a speculative hypothesis proposed in 2003 by 3 American researchers. According to this model, the final curtain goes down a mere 22 billion years in the future. But whatever the precise details of this vast timescale, nearly everyone agrees that the eternally accelerating expansion of the universe will lead to a state of total darkness, cold, and eventual death. Conclusion. At the start of the 20th century, our understanding of the universe underwent a significant transformation. This change was prompted by 2 groundbreaking insights from thermodynamics. First, that the universe had a definitive beginning, and second, that this beginning was characterized by a state of minimum entropy or maximum order, essentially a highly fine-tuned condition. These revolutionary ideas that Boltzmann deduced from the laws of thermodynamics have been verified, and no one has ever seriously called them into question. And yet, even after crossing this crucial line, many great scientific minds hesitated to take one more step toward an ultimate conclusion that, while not scientific in the strictest sense, is nonetheless demanded by reason. If the universe has a beginning in time, there must have been a cause that preceded it. 2. The scenario with the greatest consensus today. The accelerating expansion of the universe is confirmed by observation and widely accepted by cosmologists. The observable diameter of the universe is estimated at around 93 billion light-years and its age about 13.8 billion years. Observations carried out since 1998 by Saul Perlmutter and Brian Schmidt, winners of the 2011 Nobel Prize in Physics, have proven that it is expanding at an ever-accelerating rate. Most cosmologists believe that the universe is undergoing this process of expansion and that it has done so since its origin in accordance with the natural course of the development of the universe as envisioned by astrophysicists. From all this, there is a nearly universal consensus regarding the thermal death of the universe. The heat death of the universe is a logical outcome of applying the second law of thermodynamics to an ever-expanding space. Currently, no widely accepted scientific theory offers a plausible alternative to this scenario, although the modeling of the process and the time frame for its conclusion still require refinement. 10 to the 30th years from now, the end of stars and of all life. Currently, we estimate that 4 to 5 stars are formed each year in our galaxy, corresponding to roughly 300,000 new stars each second in the 2,000 billion galaxies of the observable universe. In 4.5 billion years, 10 to the 9th, The Earth will be destroyed when our Sun transforms into a red giant with a diameter reaching all the way to Mars. The Sun will then consume all its hydrogen and go out. In 1,000 billion years, 10 to the 12th, all the galaxies outside our local cluster, which will by then consist of a single galaxy called Milkomeda, a contraction of the Milky Way and Andromeda, will have passed to the other side of the horizon due to the acceleration of the universe's expansion. Any human civilization remaining in the galaxy will believe itself alone in the universe. In 1,000 billion to 100,000 billion years, 10 to the 12th to 10 to the 14th, stars will stop forming and then begin to go out as they run out of the gas needed to keep burning. In 100,000 billion years, 10 to the 14th, all stars will be extinguished, all white dwarfs and neutron stars will cool, leading to the extinction of all life. In 100,000 trillion years, 10 to the 23rd, the dead stars will be absorbed by the black hole at the center of the galaxy. In 100 to 10 billion, 10 to the 29th to 10 to the 37th, the universe will be made up of 90% dead stars, 9% supermassive black holes formed by collapsing galaxies, and 1% atomic matter, mostly hydrogen. 10 to the 30th to 10 to the 38th years from now, the possible disintegration of protons would cause neutrons to disappear. In 10,000 billion years, particle physics suggests that protons may disintegrate, leaving only neutrons that will then quickly disintegrate into protons, their autonomous existence only lasting 15 minutes. Their disappearance will liberate protons, electrons, and antineutrinos, filling space with a gas so thin that the distance between two particles would be approximately the diameter of our current galaxy. 10 to the 100th years from now, the likely end of black holes. Some scientists think that in 10 to the 68th to 10 to the 102nd years, black holes will dissipate. This astonishing hypothesis on the end of black holes was advanced by Stephen Hawking, based on his research in quantum mechanics. John Wheeler was one of the first to examine more closely the notion of entropy in cosmology, shifting the discussion into the realm of the physics of black holes. Inspired by his reflections, Jacob Bekenstein and Stephen Hawking eventually concluded that a black hole has an entropy proportional to the square of its mass and that it emits a radiation, Hawking radiation, through quantum tunneling that will eventually lead to it breaking apart. Beyond 10 to the 100th years, the probable advent of a dark era of complete thermal death. Beyond 10 to the 100th years from now, we arrive at the complete heat death of the universe. Having reached a state of extreme dilation through its process of expansion, the universe will reach a state of maximum entropy that implies the end of all thermodynamic activity. Then what is quite justly called the dark era will begin, when mostly photons will be left, floating in a gigantic, ever colder space tending towards absolute zero. 5. A brief history of the Big Bang. The Big Bang theory didn't emerge with a bang. There was no definitive eureka moment or overwhelming evidence that shocked the scientific community. Instead, its development was a long and painstaking journey marked from the outset by skepticism. This was followed by a gradual shift in established opinions, accompanied by hesitation and a frantic search for alternative hypotheses, as some scientists grappled with the metaphysical implications of this initial singularity. However, the first thing that the Big Bang shattered was a host of certainties and a priori assumptions surrounding the representation of our universe. 1. The Big Bang and the birth of cosmology in the 20th century. As we have seen, before Einstein, cosmology was not a science, and until 1912 to 1925, it had little claim to scientific legitimacy. Most researchers believed that the universe was fixed, unchanging, and immense, without limit in time or space. At the beginning of the 20th century, the discussion was considered closed. No one dared to imagine that the universe had undergone a series of major changes that could be known through reason and observation. This dogma would soon be shattered by the discoveries of a certain young scientist. Einstein's theory of relativity, a giant leap for our understanding of the universe. For Einstein, then a nobody at the Berne Patent Office, 1905 was the Annus Mirabilis, miracle year. It was in this year that he published his innovative theories as a series of 4 articles in the journal Annalen der Physik. The third of these articles, entitled On the Electrodynamics of Moving Bodies, holds that the speed of light is a constant and an absolute that cannot be surpassed in our universe. Time and space, however, are relative, contracting or expanding based on the frame of reference of the observer. This was a major conceptual revolution. Einstein set the capstone on his work in 1915 when he presented his theory of gravitation, commonly known as general relativity, which encompasses, corrects, and surpasses Isaac Newton's theory of universal gravitation. He theorized that space, time, and matter are linked and that the presence of matter or energy distorts space-time. To put it concretely, in the language of relativity, the planets do not revolve around the sun but move straight ahead in a space locally curved by the sun's gravitational field. Experimental testing of relativity. These daring theories, and the experimental tests that later confirmed them, rocked the scientific world. The great astronomer Sir Arthur Eddington was the first to measure the curvature of space by observing the alteration of the apparent position of the stars visually close to the Sun during a 1919 solar eclipse. Given the mass of the Sun, he was able to verify with great precision that this alteration takes place according to the angle predicted by Einstein's theory. The distortion of space-time was tested in 1954, a year before Einstein's death, by atomic clocks on board a jet plane designed to fly at great speed at very high altitudes, where the gravitational field is weaker. By the end of the flight, the clocks had advanced a few millionths of a second compared to clocks located at ground level, demonstrating the accuracy of Einstein's concept and calculations concerning the dilation or slowing down of spacetime in a gravitational field. Experiments carried out in the early 1960s made it possible to verify that, from the point of view of an external observer, the local time of an object moving at very high speed expands, stretches, and therefore lasts longer, or slows down, as predicted by Einstein's theory of special relativity. Thus, particles from secondary cosmic rays in the upper atmosphere, which have such a short lifespan that they are unobservable if they do not move, can in fact be observed because they move at the speed close to that of the light relative to the observer. Einstein is stubborn, and the facts are too, and they all support the theory of relativity. Cosmology can then take off on completely new and well-established foundations. An unjustified cosmological constant. In 1921, Einstein's fame grew yet again when he won the Nobel Prize in Physics for his work on the photoelectric effect, in addition to the already partially confirmed theory of relativity. But if we follow the implications of his theory, we arrive at an a priori non-stable universe, which was, for Einstein, inconceivable. To solve the problem, he set the cosmological constant in his 1917 equations to a value that yielded a static universe. Einstein did so because he found the alternative unimaginable. He had already dared to postulate an enormous conceptual leap with his new theories, but he was not at all ready to imagine the next leap, according to which the universe could be expanding. It took the audacity of a young Russian researcher to help him take the plunge. Alexander Friedmann versus Einstein, a duel over the expansion of the universe. As early as 1922, the need for this cosmological constant was being called into question by a 33-year-old Russian mathematician named Alexander Friedmann, who was the first ever to publish on the theory of an expanding universe. He mailed his article to Einstein, whose work he had used as the basis for his own arguments. But the father of the theory of general relativity reacted very poorly, declaring, The circumstance of an expanding universe irritates me." In another letter he wrote, "To admit such possibilities seems senseless." An exasperated Einstein drafted a terse letter denouncing Friedman's miscalculations, which was published in the premier journal of theoretical physics, the Zeitschrift für Physik. The results obtained in Friedman's paper regarding a non-stationary universe seemed suspect to me. In fact, it turns out that the solution given does not agree with the field equations. Friedman was deeply hurt by Einstein's reaction, which he did not understand. When he again took up his pen to ask his illustrious correspondent where his error lay, he got no response. Fortunately, his friend Yuri Krutkoff stepped in. With the help of Paul Ehrenfest, Krutkoff's former physics professor and a good friend of Einstein, the three collaborated on reformulating the problem and submitted it to him again the following year, 1923. Einstein then apologized. Friedman had not been mistaken. Without entirely conceding the idea of an expanding universe, he did publish an honest retraction of his earlier article, in which he acknowledged that Friedman's calculations were correct and opened up new avenues of research. Unfortunately, Friedman was not able to explore these avenues as he died prematurely 2 years later. Georges Lemaitre, 1927, priest, cosmologist, and visionary. A few years later, in 1927, a little-known young scientist began to traverse these new avenues. A Catholic priest with a Ph.D. from MIT, Georges Lemaitre had also studied Albert Einstein's work and felt compelled to follow all its consequences to their logical conclusions. His thesis, published in the Annals of the Scientific Society of Brussels and entitled "A Homogeneous Universe of Constant Mass and Increasing Radius, Accounting for the Radial Velocity of Extragalactic Nebulae," presented a theory of universal expansion. Specifically, Lemaitre derived the precise value for the law of proportionality between a galaxy's distance from the Earth and the speed at which it is moving away from it, a law Edwin Hubble would verify in 1929 with a new telescope at the Mount Wilson Observatory equipped with a 100-inch lens, by far the largest in the world at the time. Georges Lemaitre's article made a splash. Albert Einstein read it with wonder, but remained trapped in his prejudices against the idea of the expansion of the universe. "Your calculations are correct, but your physics is atrocious," he told Lemaitre that year at Solvay, a famous congress in Brussels that gathered together the greatest contemporary minds in physics. In private, he disparaged Lemaitre's theory as the physics of a priest. Likewise, most scientists at the time did not accept Lemaitre's hypothesis. Sir Arthur Eddington, Lemaitre's former teacher, believed that the expansion of the universe was so absurd and so incredible that he felt almost outraged that anyone could believe it. Vesto Slipher, 1912, and Edwin Hubble, 1929, A Decisive Observation. In 1929, American astronomer Edwin Hubble, building on the work of Vesto Slipher, made a game-changing discovery. He noticed that the light coming from distant galaxies always shifted towards the red part of the electromagnetic spectrum. He concluded that this red shift must be a Doppler effect resulting from the fact that the light sources are receding relative to us. Since the velocity at which a galaxy recedes from the Earth depends only on its current distance from us, Hubble postulated that galaxies are moving farther apart from one another, picking up speed as they go. With this extraordinary observation, Lemaitre confirmed that the universe was expanding just as Friedman had predicted in 1922, and he himself forecast 5 years later, based on Einstein's theory of general relativity. Of all the great predictions that science has ever made over the centuries, John Wheeler exclaims, was there ever one greater than this, to predict and predict correctly and predict against all expectation a phenomenon so fantastic as the expansion of the universe? Faced with the evidence, leading scientists rally around Lemaitre's ideas. Hubble's observations so strongly confirmed the theory of universal expansion that within just a few years it led to a complete reversal of the scientific consensus. In order to convince himself, Einstein traveled to Mount Wilson in 1931, where he spoke with Edwin Hubble. He emerged defeated and confessed that introducing the cosmological constant into his calculations because of his philosophical preconceptions was the biggest blunder he had made in his entire life. Sir Arthur Eddington also radically altered his opinion, declaring Lemaitre a genius and proclaiming to the whole world that the first serious cosmological argument for the expansion of the universe had arrived at long last. Georges Lemaitre finally got the recognition he deserved. In 1933, American newspapers showered him with praise, and in 1934 he received the Prix Franqui, Belgium's most prestigious scientific award. But this general acceptance of the idea that the universe is expanding did not lead to an immediate consensus as to how it began, even though rewinding the history of the universe is all it takes to show that the Big Bang is a logical necessity. The theory of the primeval atom calls this fresh consensus into question. The great scientific minds rebel again. Scientific consensus on the expansion of the universe had implications for the study of its origin. These consequences were not lost on Georges Lemaitre, who proposed a second theory. In 1931, he put forward a hypothesis that would prove even more impossible for scientists of his day to accept. According to his findings, the universe had originated in a primeval atom, this dense kernel containing what would become all the matter and energy of the entire universe, suddenly entered a period of expansion, and at once space and time were created. Lemaitre summarized his conclusion thus: "We can reason that space began with the primeval atom and that the beginning of space marked the beginning of time." What an outrageous idea! Outrage and disbelief. They called him a genius for the expansion of the universe. They called him crazy for the primeval atom. Georges Lemaitre's new theory was so scandalous that it threatened his hard-won reputation. No one accepted the primeval atom. Lemaitre's revolutionary idea pushed scientists up against a conceptual barrier they absolutely refused to cross. "Philosophically, the notion of a beginning to the present order of nature is repugnant to me," explained Arthur Eddington, who described Lemaitre's hypothesis as forbidding. Any time someone mentioned the primeval atom, Albert Einstein exclaimed, "No, not that. It smacks too much of creation." Georges Lemaitre's priestly vocation brought him under suspicion. Some took it as proof of his partiality. He was accused of being a concordist, of inventing a theory of the universe's origins that corresponded at all costs to the biblical account of creation ex nihilo, from nothing, as described in Genesis. His critics all too quickly forgot that the father of the heliocentric model, Nicholas Copernicus, was a cathedral canon, and that Mendel, founder of the study of genetics, was a Catholic monk. The habit might not make the monk, but neither does the ecclesiastical state make a bad scientist. Be that as it may, atheists soon made the Big Bang enemy number one. From 1947 onwards, world-famous English astrophysicist Fred Hoyle headed the resistance against the theory of the primeval atom and opposed every theory that envisioned anything like a creative act. Instead, he argued for the steady-state model, which imagines the universe as infinite, eternal, and slowly expanding, with a density that always remains the same as new galaxies are created atom by atom, essentially ex nihilo. Hoyle launched a media campaign to discredit Lemaitre, opposing and ridiculing his theory in the Times and over the airwaves of the BBC. Cosmic Microwave Background Radiation, CMBR, long ignored evidence in support of Lemaitre's theory. George Gamow was one of the many students of Alexander Friedmann who managed to leave the USSR for the United States, in his case, on the pretext of attending a 1933 scientific conference. In 1948, with his pupil Ralph Alpher, he published a foundational article that argued that hydrogen, helium, and deuterium atoms must have been created within the first several minutes of the universe's existence. As a small aside, Gamow included the name of Hans Bethe, future Nobel laureate in physics, as a co-author of the article, despite the fact that Bethe had not really contributed. The inclusion of Bethe meant that the article was authored by the first three letters of the Greek alphabet, Alpha, Beta, Gamma, Alpha, Beta, Gamow. Definitely a scientist's idea of a joke. Following his research with Gamow and with the help of fellow student Robert Herman, Alpher concluded that the first light that the emerging universe put out, corresponding to the electromagnetic radiation emitted by a blackbody in thermal equilibrium at 3000 Kelvin, should still be detectable at every point in the universe, but at a temperature 1,000 times lower, since the universe is now 1,000 times larger. He ultimately calculated this at a temperature of 5 Kelvin in the microwave frequency range. Gamow presented his findings in a book called The Creation of the Universe, but only a few noticed his sensational prediction, and most cosmologists undervalued his contribution. Hoyle coins the term Big Bang, 1949, to disparage the concept. Fred Hoyle, then president of the Royal Astronomical Society, remained one of the staunchest opponents of the theories of Alexander Friedmann and Georges Lemaitre, and later those of George Gamow. He used the phrase Big Bang for the first time in 1949, live on BBC Radio, to poke fun at Friedmann and Lemaitre, and subsequently fell back on it often, to devastating effect. Once, as Father Georges Lemaitre arrived at a conference in Pasadena in 1960, Hoyle introduced him as the Big Bang Man. The term was a smashing success and helped sow contempt for the idea from the start. The Big Bang sinks into oblivion, 1953. For a long time, the idea of the Big Bang sat shelved. The ironclad prejudices of the scientific authorities had outlasted the tenacity of the few researchers who defended the concept. By 1953, the battle seemed lost. With a heavy heart, the three discredited pioneers gave up their research on the Big Bang. Gamow gradually moved away from physics. Alpher left the university, wounded by the contemptuous mockery of his colleagues. His student Herman changed careers, entering the automotive industry. Expansion? Who cares? The Big Bang? A preposterous hypothesis without the slightest proof. Galaxies are moving in space, sure, but the cosmos itself? Come on. An unexpected rebirth thanks to the chance discovery of cosmic microwave background radiation, CMBR, 1964. The Big Bang had been discredited, but a few tenacious researchers still thought it worth their while to examine Gamow's research. Among these were Robert Dicke and Jim Peebles, researchers at Princeton who resolved to try to spot the famous cosmic microwave background radiation predicted by Gamow. While they were at work one day in 1964, they got a phone call from two engineers at Bell Laboratories, only 30 miles away, where Arno Penzias and Robert Wilson, both former students of Fred Hoyle, were putting the finishing touches on what was then to be the world's largest directional antenna. While trying to improve the reception of signals sent from the earliest satellites, they had identified a strange signal, a parasite coming from all directions of the universe at 2.725 kelvins. They had already carefully checked off, one by one, all the possible causes of this parasite, going so far as to climb into their huge horn-shaped antenna to expel a couple of resident pigeons they suspected were the culprits. Without the slightest intention of doing so, Penzias and Wilson had in fact managed to pick up the echoes of the electromagnetic signal emitted after the Big Bang. This discovery earned them the Nobel Prize in Physics in 1978. George Gamow was pleased to learn of this result 3 years before his death. As for Georges Lemaitre, only a few weeks before his death in 1966, his friend Odon Godard told him about the discovery of this extraordinary fossil radiation which Lemaitre had called the vanishing brilliance of the origin of the worlds. From his hospital bed, where he had already lain for 2 weeks dying of leukemia, he simply said, "I am glad now. We have the proof." Except for pockets of residual resistance, the theory is unanimously accepted. Faced with this experimental observation, soon widely confirmed, and an accumulating body of proof, most scientists finally surrendered to the evidence. The composition of the oldest gas clouds in the universe was analyzed in the 1960s, and the abundance measurement corresponded exactly to the predictions: 75% hydrogen, 25% helium with traces of deuterium, lithium, beryllium, and boron. This was a second brilliant confirmation of the Big Bang theory. But the opponents of the Big Bang would not completely lay down their arms for the 3 decades between 1950 and 1980. Scientists of the opposition camp seemed most alarmed by the existential questions raised by the Big Bang. In 1963, the chair of cosmology at the Collège de France in Paris, Alexandre Duvillier, said about the Big Bang, "This is rubbish. The universe has no beginning. To think that the universe has a beginning is no longer physics, it is metaphysics." As late as 1976, the Swedish astronomer Hannes Alfvén, winner of the Nobel Prize in Physics, compared Big Bang cosmology to Ptolemy's mythical geocentric model and criticized those who defended it, claiming that the prevailing attitude is to ignore all objections to the Big Bang theory. But today, the Big Bang is unanimously accepted. Ironically, even its fiercest detractor, Fred Hoyle, ended up moderating his criticism and, after years of atheism, died a deist. Alexander Friedman, Georges Lemaitre, and George Gamow were right. The Big Bang had happened, and it looked like an absolute beginning. The Face of God, 1992. In the decades since, a series of confirmations have verified what is today called the Standard Model of the Big Bang. The COBE, WMAP, and Planck satellites made it possible to draw up an increasingly precise picture of the universe at the time it emitted its first light, as measured today by the CMBR, Cosmic Microwave Background Radiation. The image reveals a universe in almost perfect thermal equilibrium, with minute variations that are at the origin of all future developments of the universe. George Smoot was the first to publish this image in 1992, and it earned him the 2006 Nobel Prize. In his reception speech, directed at his colleagues in the American Physical Society, he projected photos of the first cosmic light on the screen and used this phrase, "It's like seeing God." The failure of all alternative theories only strengthens the standard Big Bang model. Half a century after the standard account of the Big Bang was confirmed by the discovery of CMBR, there is still no alternative theory supported by experimental observation. See Chapter 6 on the subject. We wait in vain. The failure of alternative theories led American philosopher William Lane Craig to conclude the following in his book Reasonable Faith, 2008. The history of 20th century cosmogony has, in one sense, been a series of failed attempts to craft acceptable non-standard models of the expanding universe in such a way as to avert the absolute beginning predicted by the standard model. This parade of failures can be confusing to the layman, leading him mistakenly to infer that the field of cosmology is in constant flux as new theories of the universe's origin continually come and go, with no assured results. In fact, the Standard Model's prediction of an absolute beginning has persisted through a century of astonishing progress in theoretical and observational cosmology and survived an onslaught of alternative theories. With each successive failure of alternative cosmogonic theories to avoid the absolute beginning of the universe predicted by the Standard Model, that prediction has been corroborated. It can be confidently said that no cosmogonic model has been as repeatedly verified in its predictions and as corroborated by attempts at its falsification, or as concordant with empirical discoveries and as philosophically coherent as the standard Big Bang model. 2. In the beginning was the Big Bang. From polemical to popular. Fred Hoyle didn't quite get what he expected when he coined the term Big Bang in 1949. His crude alliteration was intended to mock Lemaitre's concept of the primeval atom. He thought the term Big Bang sounded childish and unscientific. Ironically, this derogatory label, meant to belittle the idea, played a significant role in its eventual success. Big Bang was easy to remember. Once Lemaitre and Gamow's theories were confirmed, the term became widely recognized by both scientists and the general public. Big Bang. But this familiarity confuses our idea of how the universe came to be almost as badly as Hoyle's sarcasm did. The Big Bang was nothing like the random, messy, or dangerous explosion its nickname suggests. It was, in fact, an extremely organized, multi-phased development. All the elements that constitute our universe came to be through an amazingly regulated and gradual process. a moment impossible to imagine. According to the standard model of the Big Bang, there was neither time nor space nor matter before the event. All physical space and all the elements of the universe, or more precisely their precursors, originate from a primeval atom that expands, stretches, and spreads out. Imagine the universe as the surface of an inflating balloon. Then think of the matter and energy particles of the universe as stickers applied to the surface of the balloon. The expansion of the universe is like the expansion of the balloon as it inflates. As the balloon expands, the stickers move away from each other. In the same way, particles in an early expanding universe, and galaxies today, all move apart at rates roughly proportional to the distances between them. And those rates are constantly increasing. The bigger the balloon gets, the faster the stickers move apart. According to the standard model, this is the beginning of space, time, and matter. From the point of view of physics and the standard conception of time, there was no time before the Big Bang because physical time, the kind we measure on a watch, was created instantly at that moment of the event, as Georges Lemaitre realized in 1931. Georges Lemaitre described this first instant thus: "This origin appears to us in space-time as a background that defies our imagination and our reason, opposing them with a barrier that they cannot break through. Space-time appears to us like a conical cup. We progress towards the future by following the generating lines of the cone towards the outer edge of the cup. We move through space by traveling along a circle perpendicular to the generating lines. When we think our way back through time, we approach the base of the cup, that unique instant that wasn't there yesterday because yesterday space did not exist. The natural beginning of the world, an origin for which thought cannot conceive of a pre-existence, since it is space itself that begins, and we cannot conceive of anything without space. Time seems able to stretch at will towards the past and the future. But space can begin, and time cannot exist without space. We could therefore say that space strangles time and prevents it from extending beyond the bottom of space-time. Neither was there any place outside it. No one could have observed the Big Bang, since the only physical space that exists is our own, which emerged concurrently with time and matter, then, in the form of energy, starting out extremely dense. Indeed, according to Einstein's theory of general relativity, space, time, and matter are so intimately linked that we speak of space-time, and it is this space-time that arose all at once alongside the energy that would give rise to matter. This point is crucial because if science confirms that time, space, and matter had an absolute beginning, it becomes clear that the universe proceeds from a cause that is neither temporal, spatial, nor material. In other words, it proceeds from a transcendent, non-natural cause at the origin of all that exists and, as we shall see, at the origin of the extreme fine-tuning of the universe's initial parameters and the laws of physics and biology, which are indispensable for the existence and evolution of atoms, stars, and complex life. A fantastic process as finely tuned as a professional orchestra. This extraordinary event began 13.8 billion years ago and took place according to several different, very ordered chronological phases, the main outlines of which are given below. The first instant. The instant the Big Bang happened is impossible to describe in terms of the laws of physics. T equals 0. During the so-called Planck era, which is the first unimaginably small fraction of a second after the Big Bang, 10 to the minus 43rd seconds, or 10 million billion 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 times less than 1 second, much shorter than a blink of an eye in the 13.8 billion years of life of the universe, the four fundamental interactions, electromagnetism, weak interaction, strong interaction, and gravitation, were possibly unified. Our models are incapable of describing these interactions since general relativity and quantum physics are incomplete theories which can only be mobilized when gravitation and quantum effects are studied separately. In addition, Planck's instant is the smallest unit of time that is physically meaningful according to our current understanding of physics. And so it is that the ordinary notions and laws of physics in our universe do not allow us to describe time zero. Indeed, whatever came before the Planck epoch is inaccessible to physics, and some think that it will remain forever so. So, is there anything we can say about it? Yes and no. No, because, as we have seen, while it is possible for science to affirm that the cause of the Big Bang is non-spatial, non-temporal, and non-material, which is already a lot, the approach science takes is apophatic. That is to say, we are talking about realities that we can only deduce indirectly and qualify only in a negative way without having the slightest knowledge of the phenomenon at stake. By relying on the principle of causality, though, which is an integral part of science, we can, in a very scientific way, conclude that our universe is incomplete. One cannot therefore have a priori knowledge of before the Big Bang, and this state before space-time no doubt will always remain outside the realm of experimental science. Nevertheless, this does not mean that there was nothing before Planck's wall. One such theory was developed around 2010 by Sir Roger Penrose of Oxford University, 2020 Nobel laureate in physics. This long-time intellectual companion of celebrated Cambridge physicist Stephen Hawking wrote a series of scientific articles on the subject, as well as a fascinating book entitled Cycles of Time, with What Came Before the Big Bang blazoned across the cover of the first English edition. Also braving the obstinate skepticism of his colleagues, astrophysicist George F. Stotheu, director of the prestigious Kavli Institute for Cosmology at Cambridge University, claimed in 2013, "It's perfectly possible that there was some phase of the universe before the Big Bang actually happened where you can track the history of the universe to a pre-Big Bang period." As early as 1993, 13 years before he won the Nobel Prize, George Smoot posed a risky but prophetic question in his Wrinkles in Time. What was there before the Big Bang? What was there before time began? An excellent question, but what to make of it? Here is where our investigation really gets interesting. Since physicists rightly believe that space, time, and matter, as we know them in our universe, came into existence together, this means that before the Planck era, time, space, and matter did not yet exist. This logical conclusion is shared by all scientists versed in the Standard Model of physics. If we push the reasoning a little further, we deduce that instead of time, only something atemporal could exist before the Big Bang. Likewise, since matter did not yet exist, anything we found to exist before the Big Bang would be immaterial. But how can we understand this timeless and immaterial reality? What type of entity has attributes like these? Is not the existence of an immaterial creator God located outside space and time the most natural explanation? Some scientists have believed it possible to sketch out some answers. Let's begin with time. What might it have looked like before the Big Bang? The response given in particular by Stephen Hawking in the 1980s is surprising. For him, before the Big Bang, time was not real but perhaps imaginary. Everyday time, the time we measure on our watches, is measured in numbers that mathematicians call real, that is, numbers whose square is always positive. For example, 2 or -2 squared is always 4. On the other hand, mathematics has postulated numbers whose square is always negative. As early as the 17th century, the philosopher Descartes called these unique numbers imaginary. In the 21st century, some scientists, including Stephen Hawking, have employed this concept of imaginary time to rule out a cosmic beginning or temporal singularity. However, Hawking's use of imaginary time does not achieve this. Imaginary time is only a neat way to solve one of Einstein's equations, temporarily obscuring the temporal singularity. But in an intermediate step where the imaginary numbers are converted back into real numbers, as they must be for the equation to pertain to reality, the singularity reappears. Regardless, it is not unreasonable to consider that time was fundamentally different before the Big Bang, possibly of a nature that could be measured using imaginary numbers. In this scenario, matter as we understand it would not have existed. What might we conceive instead? Perhaps something intangible like information. Before the Big Bang, more precisely at instant zero, time would have been purely imaginary, and reality at that stage could have existed only as pure information, resembling an essential mathematical code. This primordial information would have programmed the birth of the universe at the time of the Big Bang and then its evolution throughout billions of years with dizzying precision. This reasoning leads us to a clearly legitimate question. If there was mathematical information before the Big Bang, who is the incredible programmer behind such a code? This question comes up regularly, and we will return to it frequently later. After 10 to the minus 43rd seconds, Planck time, we can begin to describe the evolution of the universe with some precision using inflation theory, which, though it still lacks formal confirmation, is held to by a majority of cosmologists, the theory of general relativity to explain the action of gravity, and the standard model of particle physics to account for the other three forces. With the universe crammed into a tiny space of 10 to the minus 35th meters at the inconceivable temperature of 10 to the 32nd Kelvin and an energy of 10 to the 19th GeV, there is no stable matter. This extremely dense space contains only a form of pure energy. Since this moment, the primordial quantity of mass energy in the universe is fixed and varies only under the effect of the expansion of the universe. The energy of the vacuum of space created by expansion brings a slight increase, balanced by the loss of energy linked to the redshift of photon emissions. After 10 to the minus 35th seconds, inflationary epoch, the tremendous energy contained in the hypothetical inflation field causes space to enter into accelerating expansion. The universe expands by a factor of at least 10 to the 26th between 10 to the minus 35th and 10 to the minus 32nd seconds. During this period, the strong nuclear force separates from the electroweak force, the combination of the electric and weak nuclear forces. This separation ushers in the electroweak epoch when that force dominated. After 10 to the minus 12th seconds, quark epoch, the electroweak force splits into electromagnetic interaction and weak interaction. This weak interaction is probably behind the nanoasymmetry between matter and antimatter which lasts to the present day. The four fundamental forces are then definitively separated. The universe is filled with a hot, dense quark-gluon plasma containing quarks, electrons, and other leptons and their antiparticles. Between 10 to the minus 6th and 10 to the minus 4th seconds, hadron epoch, the quarks combine to form the total amount of hadrons, that is, protons and neutrons, that will constitute all matter. Neutrons, which are unstable and live for only 15 minutes on their own, must rapidly associate with protons in stable nuclei. After this short hadron phase, the creation of new protons and neutrons will never again be possible in the universe. At 1 second, disappearance of antimatter, the nanoasymmetry between matter and antimatter leads to the near total destruction of antimatter. Between 1 second and 15 minutes after the Big Bang, first nucleosynthesis, the nucleosynthesis of all light elements takes place once and for all. Hydrogen, 75% of the universe's current matter, helium, 25%, and lithium, beryllium, and boron, in small quantities, come into existence. These elements could only be created in the extreme conditions of the Big Bang's first minutes. At 15 minutes, matter setting, the composition of the material universe is almost determined. It is essentially made up of hydrogen nuclei, 92%, a bit of helium, 8%, traces of deuterium, 0.002%, and lithium in infinitesimal quantities, 1 to 10 to the 12th. Once the temperature drops below 1 billion degrees, the number of these light nuclei is set for all time. Between 15 minutes and 380,000 years, photon epoch, the rapid expansion of the universe is dominated by the agitation of high-energy photons that slow the creation of atoms by preventing the stable association of electrons with existing nuclei. By 380,000 years, formation of the first atoms and light, the temperature has dropped to 3,000 kelvins, and photons no longer have enough energy to dissociate atoms formed when existing nuclei capture electrons. At this point, the universe becomes transparent to light and therefore observable, as photons can now travel freely in a straight line in space. With visible light comes the first radiation, which is emitted from all points of the universe in all directions. This primordial radiation is the famous cosmic microwave background radiation, CMBR, discovered by Penzias and Wilson in 1964. We may not realize it, but we are surrounded by these particles from the Big Bang, 411 photons in every cubic centimeter of space. Now that we know that a small percentage of the interference on a cathode ray tube television set goes back to the cosmic microwave background, we'll remember those bug races in a new light. These photons from the CMBR are now at a temperature of 2.725 Kelvin because the universe has increased in volume by a factor of about 1,000 since the release of the first visible light, and so the temperature has decreased by the same proportion. Between 380,000 years and 1 billion years, first cosmic dark age and first stars, the universe enters a first dark age, but slight variations in the density of matter, an anisotropy factor of only 1 to 100,000, lead gradually to the production of clumps of dust that eventually, after 150 to 200 million years, will make it possible to ignite the first stars. These early stars grouped together in the first galaxies, observable today as quasars. After 3 to 5 billion years, formation of heavy elements, the first generations of stars end their lives as supernovas, creating the conditions for the formation of the heavy elements in Mendeleev's periodic table. Besides the hydrogen, helium, deuterium, and lithium that formed in earlier ages, all the atoms that make up our planet, our body, and the things we use every day come from this stardust. After 9 billion years, our Sun begins to form as a third generation, population 1, star. And this is how the solar system, our Earth, life, and each and every one of us came into being after a history of almost 13.8 billion years. The Standard Model of the Big Bang, a very solid theory tested and confirmed by observation. The Standard Model of the Big Bang is thus supported by such a large number of probative observations that the vast majority of cosmologists now accept its central claims. It very precisely describes a universe whose structure came to be at the dawn of time. This universe has not existed for all eternity. It came into existence at a finite point in the past. The origin of the universe, suggested by this model, is an absolute beginning. This is a radical claim whose implications deserve to be fully investigated. Matter and energy, even time and space, came into existence in this instant of initial cosmological singularity. Is it really such a leap, then, to entertain the possibility of a creative act behind this singularity? Where is God in all this? The Big Bang forces us into a corner. To put it bluntly, it brings us face to face with the idea of God. The absolute beginning of the universe is where physics meets its maker, a creative cause exterior to the universe. Now that science has largely resolved the mystery of the universe's origin from the Planck moment, it is necessary to ask the question concerning the before and the why. For those who believe that the universe was created, there are, in theory, two possibilities. Either we live in a static universe that emerged in a single instant just as it is today, or The universe was created to be dynamic and has evolved from an absolute beginning of space, time, and matter. In this case, we might expect that everything began from a single point. But now we know that the universe is not static and that it unfolds in an extremely precise and organized manner, much like a plant, animal, or human develops from a single cell. Further, the initial laws and data of the universe give structure to and inform all future development. We dare to say that the picture painted by the Big Bang model is remarkably consistent with the idea of the creation of the universe by God. The fact that we can't really think about the time before the Big Bang, as the categories of time, space, and matter simply do not apply, lends credence to the idea of a creative act. Finally, let's pause to admire the researchers who made these discoveries. To be able to imagine our universe at 10 to the minus 43rd seconds of life and to describe it precisely from 1/10,000,000th of a second or 10 to the power of minus 10 seconds onwards. They have brilliantly solved the question of how our universe was formed, and this description corresponds perfectly to what believers have always claimed: a creative will made the universe arise from nothing. A few quotations on the subject. Arno A. Penzias, 1978 Nobel Prize in Physics. To be in accord with our observations, we must understand that not only is there a creation of matter, but also the creation of space and time. My argument is that the best data we have are exactly what I would have predicted had I had nothing to go on but the 5 books of Moses, the Psalms, the Bible as a whole. Astronomy leads us to a unique event, a universe which was created out of nothing. Alexander Vilenkin, physicist at Tufts University, co-author with Arvind Borda and Alan Guth of the great cosmological theorem confirming that the universe had a beginning. It is said that an argument is what convinces reasonable men, and a proof is what it takes to convince even an unreasonable man. With the proof now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. There is no escape. They have to face the problem of a cosmic beginning. Max Planck. All matter originates and exists only by virtue of a force which brings the particle of an atom to vibration and holds this most minute solar system of the atom together. We must assume behind this force the existence of a conscious and intelligent mind. This mind is the matrix of all matter. Igor and Grisha Bogdanov. But then, if the singularity at the origin of the universe is now well established scientifically, why does it arouse so much passion, not to mention rejection? Surely it is because it forces us to make an impossible choice between a universe without cause or the face of God. As you can imagine from reading these quotes, the kind of beginning proposed by the Big Bang Theory simply did not sit well with materialists. One way to get around the problem was to create alternative theories, and that is indeed what happened, as we will see in the pages that follow. 6. Attempts at alternatives to the Big Bang model. As well established and supported as it is, the standard model of the Big Bang continues to annoy some scientists, much like a metaphysical pebble in their materialist shoe. How do they get rid of it? By developing alternative theories. None of these has withstood the weight of evidence and verification. Each has either been found invalid at the outset, or has advanced so little beyond the first stages of conceptual formulation that even beginning to seek confirmation for it is impossible. A quick look at the most popular alternative theories. 1. The tired light hypothesis, proposed by Fritz Zwicky in 1929, sought to challenge the notion of an expanding universe, which was inferred by Hubble and Lemaitre from the redshift of distant galaxies. This redshift is a result of the Doppler effect, indicating that the sources of light are moving away from us. In contrast to this theory, Swiss-American astronomer Fritz Zwicky suggested that the redshift occurred due to energy loss in photons as they traveled vast distances. This led to the term tired light, which was coined by Richard Tolman the same year. Frenchman Jean-Claude Picquet, member of the Academy of Sciences and the Rationalist Union, defended this theory until 1978. He stubbornly clung to his opinion in the face of mounting evidence to the contrary, and as late as 2004 even signed a letter against the standard model of the Big Bang. However, observations carried out in the 1990s by the COBE satellite have definitively disproved the theory of tired light. 2. Around 1940, the steady-state model assumed the existence of a phenomenon of continuous creation of matter, making it possible to imagine a universe in eternal and immutable expansion. Proposed by Fred Hoyle, Thomas Gold, and Herman Bondi, the idea was debated in the 1960s but has fallen into obscurity today. 3. In 1957, the many worlds interpretation attempts to explain the phenomenon of wave function collapse, according to which, once measured, a physical system sees its state reduced to what was measured. Before it is measured, what we call reality has an infinite number of possible states. But once we measure it, it is reduced to whatever state it had when measured. Where do the other possible states go? To resolve this difficulty, Hugh Everett devised the many worlds interpretation. He postulated that parallel universes are created at every moment and with each measurement, evolving independently from that point onward. The hypothesis has not been taken seriously, though the idea of parallel universes has flourished in science fiction. 4. In 1960, plasma cosmology was formulated as an alternative to the Big Bang. It suggests that electromagnetic phenomena play a more important role than the force of gravitation in explaining the structure of the universe. It suggests that expansion takes place in only a small part of the universe. Despite the fame of its principal supporter, Swedish Nobel laureate Hannes Alfvén, the model, which shares certain similarities with the tired light theory, was quickly abandoned. 5. In the 1970s, after the discovery of fossil radiation, which confirmed the Big Bang, the Big Crunch hypothesis came into vogue. It predicted that the expansion of the universe would slow down and eventually enter a phase of contraction, ultimately returning to the size of the primitive atom. Friedman had the idea in 1922, and Lemaitre echoed it by introducing the term Phoenix universe to describe a world that oscillated between expansion and contraction. Following them, some scientists investigated the possibility of cyclic big bounces, but this hypothesis was abandoned. In fact, it was observed that the spatial curvature of the universe was insufficient. More importantly, in 1998 we discovered that the expansion was even accelerating. The Borda-Guth-Vilenkin theorem, published in 2012, challenged the theory of the Big Crunch by confirming again, and in another way, the impossibility of perpetual inflation in an infinite past. 6. In 1980, cosmic inflation theory proposed a scenario of very rapid expansion of the universe at its beginning in order to explain why it is surprisingly flat, homogeneous, and isotropic. This interesting explanation is now accepted by a majority of cosmologists. Developed by Alan Guth, the first of these theories also postulated, however, that the size of the universe is at least 10 to the 23rd times greater than we can observe. In that as yet unaccounted for space, other universes are developing like bubbles, separate from our own universe and governed by different physical laws. Following in Guth's footsteps, more than 50 variants of inflation theory have been developed, with more popping up all the time, but none of them have received experimental confirmation. 7. In 1983, the boundless universe theory was formulated by James Hartle and by Stephen Hawking. According to this model, the universe, while not infinite in space and time, nevertheless has no temporal boundaries and thus perhaps no beginning. It depicts the universe as something like the surface of a sphere which has no clear starting point. To defend this model, also sometimes called quantum cosmology, Hawking and Hartle solved the Wheeler-DeWitt equation, which describes possible universes that could exist or emerge from the cosmological singularity. Though Hawking's popular work suggests that his use of imaginary time in his mathematical calculations might eliminate the need to invoke such a singularity, the technical papers he co-authored with Hartle presuppose the reality of such a singularity and never eliminated it. 8. In 1984, early string theory picked up 1970s research hoping to resolve the fundamental problem of quantum gravity. The researchers hope to unite the part of Einstein's general relativity that describes the force of gravitation with the insights of quantum mechanics, which deals with the three other fundamental interactions on the microscopic level. They wanted to understand the physical laws that govern singularities, like the Big Bang or black holes, on both the infinitely large and infinitesimally small scales. 9. In the next 20 years, 4 more versions of string theory or superstring theory were elaborated, each demanding extremely complicated mathematics. String theory requires us to imagine the existence of supersymmetric particles and a universe in 10 dimensions: time, the 3 known dimensions of space, and 6 other hypothetical invisible dimensions that are folded back onto themselves. String theories have gained popularity in recent decades, but they are extremely complex and highly speculative. Some of their specific predictions have been disproved by experiments at the Large Hadron Collider, LHC, in Geneva, and others are unverifiable on a human timescale. Currently, the number of researchers who believe in them and work on them is diminishing. 10. Around 1990, quasi-steady-state theory again postulated that the universe creates matter over time, but introduced the innovation that this expansion occurs cyclically. This theory, put forward by Jayant Narlikar, Fred Hoyle, and Jeffrey Burbridge, was swept aside by the analysis of cosmic microwave background radiation in 1992, and its lack of simplicity and predictive power led to a general rejection of it. Staunch atheist Fred Hoyle, who opposed George Lemaitre and coined the term Big Bang to mock him, eventually became a deist himself after the discovery of the fine-tuning of the universe. See Chapter 9. He was, however, one of the few who continued to believe in the steady-state theory he had championed against all evidence right up to his death in 2001. Proof, as if any were needed, that people do not change their minds easily. In addition, the discovery in 1998 that the expansion of the universe is accelerating put a final nail in its coffin. 11. Around the same time, a new model called chaotic inflation put forward the hypothesis that new universes could spontaneously appear at different spots in an existing universe, and these, in turn, could naturally generate other universes, doing this in an eternal way without limit to the process. In this model, which was defended by Andrei Linda, a Russian scientist working at Stanford University after the fall of the Soviet Union, this chaotic inflation was initially thought to have occurred forever in the past. Consequently, the universe might not have had a beginning. But this possibility was refuted by the Borda-Guth-Vilenkin theorem, which demonstrated that inflationary cosmologies, as well as any other realistic cosmology, might be eternal in the future, but not into the past, since the process must have had an absolute beginning. 12. In 1995, M-theory was developed by Edward Witten as an attempt to unite the 5 different versions of superstring theory. The M signifies magic, mystery, mother, monster, or membrane, according to taste. It speculates about the existence of bidimensional membranes that vibrate in a space of 11 dimensions. The theory has the advantage for its supporters of conceptual simplicity and coherence from the mathematical point of view, but its calculations are highly complex and incomplete, and it has never been confirmed. In addition, attempts to apply string theory to cosmology cannot eliminate the beginning due to the Borda-Guth-Vilenkin theorem. 13. Beginning in the late 1980s, loop quantum gravity, LQG, was developed as another attempt to formulate a theory of quantum gravity that unifies general relativity and quantum mechanics. Introduced by Abhay Ashtekar, a researcher in theoretical physics from India, The theory modeled space as a network or fabric of minuscule granules of finite size. This quantization of space limits how small the universe can become, eliminating a spatial singularity and leading to a rebound when, in a big crunch-type contraction of the universe, a particular density, 5 × 10⁻96 kilograms per cubic meter, impossible to surpass, is reached. Nevertheless, today the theory remains only an unconfirmed attempt, and though it has advanced over the decades of its development, it has not managed to eliminate a temporal singularity. It thus leaves the question of the ultimate origin of the universe unanswered. 14. In 2005, conformal cyclic cosmology, CCC, was proposed by renowned cosmologist Roger Penrose. The theory postulates that after approximately 10 to the 100th years, once all black holes have evaporated, the universe will be reborn as a new universe in a kind of Big Bang event. This process is eternally cyclical. At the end of each cycle, only photons and massless particles remain, floating in the same eternal space in which the cycle began, and in which the next will begin. Penrose attempted to verify CCC by analyzing the cosmic microwave background radiation, but most cosmologists have dismissed CCC due to a lack of convincing evidence and other problems. 15. In 2010, in his book The Grand Design, Stephen Hawking argued that because there is a law like gravity, the universe can and will create itself from nothing. Despite the media interest it garnered, the theory did not convince anyone in the scientific community because gravitation needs a universe to exist. Stephen Hawking's strange position earned him the following caustic remark from his Oxford colleague John Lennox. What all this goes to show is that nonsense remains nonsense even when talked by world-famous scientists. But Hawking's statement reveals a confusion about what the laws of nature are and what they can do. As philosopher of science Stephen Meyer explains in his book The Return of the God Hypothesis, Hawking's statements about the laws of nature explaining how the universe originated betray a confusion of categories, a philosophical misunderstanding about what the laws of nature do and don't do. The laws of nature are our descriptions, typically framed in mathematical terms, of what nature ordinarily does. They have no objective existence in the universe independent of our minds, still less would they cause the origin of the universe itself. Saying they do is like saying that the longitude and latitude lines on the map explain how the Hawaiian Islands popped up in the middle of the Pacific Ocean. 16. In 2012, Lawrence Krauss published his book A Universe from Nothing, in which he proposed that the universe could have come from a deep nothing. The book was endorsed by militant atheist Richard Dawkins for purportedly eliminating the need for a creator God to explain the universe. But Krauss's model was really a popularization of a cosmological model developed by Alexander Vilenkin, in which Vilenkin attempted to show that the universe is the result of some pre-existing physical law. Vilenkin's model was similar to that of Hawking and Hartle in that it explained not how the universe came from nothing, but how it emerged from a pre-existing mathematical law, or, more precisely, a pre-existing mathematical description of possible universes that could exist. Yet neither Vilenkin nor Hawking ever explained how this realm of mathematical abstraction could cause an actual universe to come into existence. 17. In 2023, Thomas Hertog, the last scientist to work closely with Stephen Hawking, laid out Hawking's final theory on the origin of time. Hertog explains that the big question that obsessed Stephen Hawking was the mysterious biophilia of the universe, that astonishing fact of the fine-tuning of the laws of the universe, which needs an explanation. However, according to Hawking, as quoted by Hertog, it's obvious that the multiverse doesn't explain anything, and he even asserts that for Hawking, scientific explanations like the idea of the multiverse or a theory of everything are dead. Hence the need for materialists to find something else. That's why Stephen Hawking came up with a new theory in which time does not exist, a theory based on the hypothesis that our human observations modify the origin of the universe and thus enable Darwinian selection of its laws. But nobody has followed up on this surprising thesis. Though the theories we've reviewed above are certainly creative, we've seen that some are completely off base and others are just pure speculations without any confirmation. Though this research may be of intellectual and scientific interest, it is important to notice the incredible amount of brain power and time that has been put forth in the effort to topple or circumvent a simple, verified, and well-documented theory through complex alternatives that completely lack convincing arguments. This is another indirect argument that allows us to affirm that the standard model of the Big Bang can be counted as evidence for the existence of a creator God. The need to work through so many alternative theories has slowed the start of metaphysical inquiry, but in the domain of understanding the universe, the Big Bang remains the big boss. 7. Convergent evidence for an absolute beginning to the universe. The growing conviction that the universe had an absolute beginning stems not only from the confirmation of the Big Bang theory, which is only a single piece of evidence, but also from the convergence of many discoveries made in various fields of knowledge. This chapter aims to present these discoveries in a comprehensive way and give the history behind them to demonstrate their strength and coherence, without diving again into those we have already discussed in detail. 5 different fields of thought and science today lead us to the inescapable fact that the universe had an absolute beginning. 1. Thermodynamics. If our universe is heading towards its thermal death and this death has still not happened yet, this means that time in the past is not infinite. This point has been discussed in detail in Chapter 4. 2. Cosmology. The expansion of the universe and the Big Bang naturally point towards a beginning to the universe. Certainly many scientists still contest this idea, but their position has become especially difficult to maintain since the work of Borda, Guth, and Vilenkin. After Penrose and Hawking's work on singularities, these scientists demonstrated in 2003 that any universe that has been, on average, in expansion throughout its entire history cannot be infinite in the past and therefore must have a limit in its past space-time. Consequently, even if other singularities happened in the past, that is, other Big Bangs, the universe which is expanding cannot be infinite in the past and must necessarily have had a beginning. See Chapters 5 and 6. 3. Philosophy. In 6th century Egypt, a Christian commentator on Aristotle named John Philoponus was the first to confirm that an infinite time in the past is impossible. His reasoning is simple yet completely valid. It states that we can imagine infinity into the future with today as our starting point, but we will always remain in a potential infinity. That is, if we count 0, 1, 2, 3 without ever stopping, we will stay on track towards infinity, but we will never reach it. The number will increase without ever hitting a maximum. Likewise, just as it is impossible to set out right now to reach infinity in the future, it is impossible to depart from infinity in the past to reach our time. Traversing an infinite greatness is no more possible than coming from a place to which one can't return. Progress that cannot be made in one direction cannot be made in another. An infinite time in the past is therefore a logical impossibility. See Chapter 23, Section 3. This line of reasoning was developed further by Muslim thinkers al-Kindi, 9th century, and al-Ghazali, 12th century. Their methodology is known today by the Arabic word kalam, discussion. This method of reasoning reached maturity in the West in the 13th century with Saint Bonaventure and Saint Albert the Great. However, after a long debate, Albert's student St. Thomas Aquinas chose not to support it. Due to this, Kalam did not enjoy significant recognition in the West. St. Thomas Aquinas holds that real infinity cannot exist, but he also maintains that an infinite time in the past does not imply a real infinity, an argument which would later be disputed. Indeed, if there were an infinite time in the past, the number of hours elapsed would add up to a truly infinite number, which is not possible. The assertion that the infinite past does not imply the existence of a real infinity, but only of a potential infinity, is therefore impossible. In sum, real infinity does not exist, only potential infinities exist. However, a potential infinity is an infinity we can only move towards bit by bit, never reaching it. But the past is frozen. It's impossible for it to grow further and further away from the current present. There can therefore be neither real infinity nor potential infinity in the past. 4. Mathematics. In the field of mathematics, the famous mathematician Georg Cantor, 1845 to 1918, developed a transfinite mathematics manipulating infinite sets, demonstrating that some infinite sets are infinitely larger than others. But this idea of an abstract infinity that works in mathematics cannot be translated into the real world, as David Hilbert and the mathematicians at the conference of the Mathematical Society of Westphalia confirmed in June of 1925, stating, "Our principal result is that the infinite is nowhere to be found in reality. It neither exists in nature nor provides a legitimate basis for rational thought. The role that remains for the infinite to play is solely that of an idea." Otherwise, one arrives at absurdities like Hilbert's infinite hotel, which has an infinite number of rooms. Even when all of the rooms are occupied, it is always possible to find a solution that allows us to have an infinite number of empty rooms. 5. Physics. Physicists tend to chase down infinities. Every time they encounter equations that diverge and head off towards infinity, they say to themselves, "No, this is not physics. The models must be revised." In the 20th century, these intuitions would be confirmed again and again. In the realm of the infinitely large, the theory of relativity leads to the conclusion that infinite speed does not exist. The speed of light cannot be exceeded. Conversely, in the realm of the infinitely small, it is not possible to divide quantities such as distance an infinite number of times. The process is limited by quanta. Finally, even if our data is not yet precise enough to assert this with certainty, it is likely that the universe is a hypersphere in shape, the four-dimensional equivalent of the surface of an ordinary three-dimensional sphere. In fact, the most recent measurements from the Planck satellite, taken in 2013, seem to confirm, with a confidence level of 99%, the notion of a very small but slightly positive spatial curvature to the universe, which does indeed mean a spherical universe. By analogy, we might note that the same problem could have been raised in the past about the Earth, which at first glance seems to be flat. Does it extend to infinity or does it have an edge? Neither, in fact. The Earth is spherical and could not be otherwise, since real infinity does not exist and the idea of edges is nonsensical. The same may well go for the universe. It is very hard to believe that it has an edge and real infinity does not exist. Space-time is therefore quite probably spherical in 4 dimensions, as measurements seem to confirm. That is to say, if we could go completely straight ahead at infinite speed, we would end up back where we started, arriving from behind. Only models that failed to take all elements of reality into account could imagine the contrary, and neither a flat universe with no curve nor a hyperbolic one with a negative curve has any meaning in physics. Nor, most probably, as we've seen above, is there infinite past time. The standard model of the Big Bang, based on Einstein's theory of relativity, suggests that time, space, and matter started together, and coherent support for the thesis of an eternal universe has become extremely difficult to maintain. A brief historical overview of the question and its philosophical significance. For most of history, almost everyone, with the striking exception of readers of the Bible, have thought that the universe was infinite in time for these 2 reasons. The first is because this intuitive feeling notion seems like common sense. We humans perceive the Earth as flat, the Sun as revolving around the Earth, and the universe as infinite in space and time for the simple reason that from our vantage point we can't see any limit, or even how there could be a limit. Unfortunately, sometimes our intuition deceives us. Convincing us it's wrong takes great scientists and major discoveries. The second reason is that the very fact of acknowledging the absolute beginning of the universe amounts to admitting the existence of a creator God because, as was first noted by Parmenides and taken up by Lucretius, ex nihilo nihil, nothing can come from absolute nothingness. It is therefore evident that there has never been absolute nothingness and that something has always existed. There are then only two possibilities. Either the universe has always existed or a transcendent God has always existed outside of the universe, its creator, in short. It is therefore understandable that materialists from all eras have consistently defended the eternity of the universe because they simply had no other choice. From Parmenides, Heraclitus, Democritus, Epicurus, and Lucretius, to Marx, Engels, Lenin, Mao, and Hitler via Nietzsche, Schopenhauer, Feuerbach, Hume, Sartre, the atheist philosophers of the 19th century, and even Spinoza, Auguste Comte, Mach, Arrhenius, Haeckel, Berthelot, Russell, Crick, etc., they have all been obliged to affirm that matter is, in one sense or another, eternal in the past and that the universe never began. This historical panorama and the description of the philosophical issues at stake allow us to better understand why the atheist regimes of the 20th century reacted with such incredible violence for reasons which were exclusively ideological, as we shall see in the next chapter. 8. The Big Bang, a noir thriller. Theories to be shot down. Who could have ever imagined that the history of certain scientific theories, elaborated in the studious silence of laboratories, would end for some researchers in the icy anonymity of the Gulag or the bitter roads of exile? Landau, Kozyrev, Bronstein, Friedrichs, Hausdorff, and Stern, so many broken or maltreated souls. What brought tragedy to these peaceful men who were content to bury themselves in their cerebral equations, so far from the calculations of political intrigue? To understand these events, we have to go back to the discovery of the thermal death of the universe. This theory, derived from the second principle of thermodynamics, had obvious metaphysical implications that, despite the scientific nature of the question, did not escape the attention of philosophers and ideologues. Heat death implies that the universe had a beginning, implying the existence of a creator God. But these conclusions undermine the doctrines of contemporary materialist ideologies, especially Marxism. The expansion of the universe, verified soon after, went further in the same direction. A short time later, the discovery and dating of the Big Bang completed the demonstration. The ideological persecution of Big Bang supporters is telling. It reveals how strong and dangerous this evidence was considered from the beginning. The materialists' outrage was proportionate to the danger the Big Bang posed to their fundamental beliefs. To save their ideology, they had to silence at all costs the scientists researching and publishing these theories. Herein lies the great interest of the history of these persecutions. The materialists would not have unleashed such extreme violence upon scientists who theorized the expansion of the universe and the Big Bang had they not been convinced that these theories made a strong case for the existence of God. The use of force is, here more than ever, an admission. Soviet Russia and Nazi Germany represent two sad and emblematic cases of this scientific witch hunt, which squeezed leading scientists in a vice between a red and a brown terror. Even after 1945, the Big Bang continued to tear the scientific community apart, and ideological violence against its supporters smoldered on in a more insidious form. As we turn the sad pages of this little-known history, we see that reality is often more outrageous than fiction. We find denunciations and summary executions, threats and escape attempts, all provoked by nothing more than scientific discoveries and scholarly demonstrations. We hope the reader will forgive this break from the more academic style of the previous 4 chapters. Writing the thrilling story of the Big Bang demands a style verging on that of a spy novel. But in the midst of the story's diversion and suspense, we must not forget the real human tragedy that lies behind it. Unfortunately, All these stories are true. 1. Soviet suppression of the Big Bang Theory. 1. God is dead. Sharp as the crack of a whip, searing as a cold flame, this cry was first raised by Nietzsche in The Gay Science, 1882. Of all the thoughts penned by the great German philosopher, this one would have the greatest influence on a certain young student who passed the entrance exam for St. Petersburg State University in 1891, earning the highest mark in every subject. His name, Vladimir Ilyich Ulyanov, better known as Lenin. The 21-year-old law student was still a long way off from the smoking barricades of the October Revolution. His ideas were still embryonic, but his voracious intellect had already devoured several of the works that would prepare him for his fateful plunge, especially the 1,000 pages of Karl Marx's Kapital. Furthermore, he already had a model to follow. In 1887, his older brother Alexander, an anarchist affiliated with the terrorist group People's Will, had been hanged at age 21 for his involvement in a plot to assassinate Tsar Alexander III. Haunted by the sacred chants and prayers that accompanied the execution, Lenin was slowly gripped by the conviction that religion is the opiate of the masses, and that a new social order would arise only when the idea of God was annihilated. Unbeknownst to the young agitator, this renunciation would form the core of the Bolshevik ideology that would blaze a trail of iron and blood through all of Russia in the 1930s, dialectical materialism. The famous term Marxism was not coined by Marx himself, he never used the phrase, but by Lenin and his followers, most notably Stalin. Matter alone. The new philosophical trend called for a reordering of reality within a strict materialist framework. According to Marxist-Leninist ideology, reality exists in matter alone and not in any other dimension, least of all the spiritual. More precisely, dialectical materialism uses the dialectical method to analyze reality within the framework of materialism, taking as axiomatic the eternal nature of matter. Materialist thought, therefore, consists in relying on Hegel's dialectic, stripped of its idealist dimension, to represent the eternal transformation of reality without beginning or end. The spirit? A fantasy. God? When asked this question at the start of the revolution, while he was preoccupied with dismantling the Tsarist order, Lenin merely shrugged his shoulders. But by the early 1900s, science had already turned to a completely different understanding of reality. The great Austrian physicist Ludwig Boltzmann had demonstrated that the universe's entropy, in other words, its loss of heat, increases with the passage of time as coffee gradually cools in a mug. This observation necessarily leads in the very distant future to the thermal death of the universe. The consequence of this phenomenon is therefore that the universe cannot be eternal. In 1917, the revolutionaries of the October Revolution, led by Plekhanov and Lenin, had already recognized the threat posed by this scientific advance. Lenin explained to anyone who would listen that if matter were not eternal, some people, perhaps even non-believers, might be tempted to think that it was created by that transcendent cause that some called God. Therefore, the churches became the enemy to be destroyed. Emboldened by their new master, the Bolsheviks wasted no time in wiping out their enemies. The State Political Directorate, GPU, a fearsome political police apparatus created in 1922, relentlessly persecuted Orthodox priests and bishops, from one day to the next throwing them into prison, deporting them to Siberia, or roughly shoving them against a wall to die by firing squad. This murderous repression would continue until Lenin's death on January 21, 1924, drowned in his own blood from a stroke. The death of the father of the October Revolution did nothing to abate the struggle against God and religion. On the contrary, repression took on an ever more terrifying aspect, and its violence was redoubled. Over the next 2 decades, the man who took the reins of power in 1925 would become one of the bloodiest dictators of the first half of the 20th century. The byname he gave himself describes him well: Stalin, Russian for man of steel. For the man of steel who in his youth, after 4 years in the Tiflis seminary, had almost become a priest, One thing was clear: God does not exist. Despite searching for 4 years, he had failed to find him. The human race had to be freed of this pernicious illusion. After taking power in 1925, Stalin brought the persecution of priests to a new level, systematically burning and destroying monasteries and churches. On May 15, 1932, the Soviet government unveiled an atheistic 5-year plan with the brazen slogan, "No more God," by 1937. To accomplish this veritable theocide, Stalin came up with a radical program to bring to completion the liquidation of the reactionary clergy in our country. Despite systematically destroying the clergy, church property, and the public expression of religion, the ideologues of Stalin's party soon faced a new enemy. True, the Bolsheviks had torn down the holy places, waded gleefully through the blood of murdered priests, and obliged their comrades to take courses in atheism. Nevertheless, beneath the surface still smoldered the idea that someone or something created the universe. But how? In the 1920s, scientists had begun to publicize discoveries that suggested the universe is not static, as so many people had come to believe. Rather, it was actually growing every minute. In other words, it was expanding. If true, then at some time in the remote past, the cosmos had a beginning, and this beginning inevitably had a transcendent cause, which some would not hesitate to call God. The Light of Alexander Friedmann. The story begins in 1922 at St. Petersburg State University with a then unknown mathematician named Alexander Friedmann. This modest scholar who worked quietly in the Meteorological Center in St. Petersburg had two impressive assets. First, he was a class above his contemporaries in the field of mathematics. At just 17 years old, he had published his first article on number theory in the prestigious Annales de Mathématiques, along with his high school friend Jacob Tamarkin. Second, he spoke and read several languages, including, significantly, German. He was also one of the very first Russian scientists to learn in the autumn of 1917 of a monumental theory that was about to change the world: general relativity. As he quickly scanned the sea of equations, he noticed almost effortlessly that Albert Einstein had made a mistake. Worse, Einstein had employed a fudge factor, assigning an ad hoc value to the cosmological constant in order to yield a static universe, in line with his expectations. Let's go back to 1916. At the time, Einstein was adamant that the universe had been fixed in size for all eternity, that it never had a beginning, and that it would exist forever. For this stance, he was welcomed with open arms by the Bolsheviks, who praised him to the skies, though they hadn't read a single line of his work. Upon closer examination, the equations of relativity did not at all demonstrate that the size of the universe is fixed. Quite the contrary, Einstein reworked the equations backwards and forwards, but to no avail. The solution stubbornly indicated that the universe is expanding. But in his view, the result was absurd. In the interest of removing this absurdity and ensuring that the equations yielded a static universe, Einstein introduced what he called the cosmological constant into the equations to yield a static universe. He assigned it the precise value necessary to balance the force of gravity in order to represent the universe as stable, that is to say, without expansion or contraction. He played this card in 1916. Until 1922, no one had detected this sleight of hand. No one, that is, except Friedmann, who at first glance noticed that this famous constant had no reason to be there other than forcing the equations to say something they would not otherwise say. Irritated and determined to find out the truth, Friedmann recopied the interminable lines of calculations one by one. Then, with a stroke of his pencil, he crossed out the cosmological constant. At last, he was free to plunge into the equations unencumbered. The calculations were terribly long and complex, but with the help of his old friends, the brilliant mathematician Jacob Tamarkin and the talented Yuri Krutkov, he was able to find that the equations of general relativity naturally lead to the possibility of a dynamic universe. Friedmann was the first to discover that unless the cosmological constant were arbitrarily fixed at an extremely specific and improbable value, the field equations would yield solutions that lead to a dynamic universe, not a static one. an expanding universe. The claim was mind-boggling. Ignoring colleagues who urged him to hush up this discovery, which was so contrary to everything the prevailing regime tried to drum into the Russian people, Friedman decided, as already mentioned, to publish his work on June 29, 1922 in Zeitschrift für Physik, the most renowned journal of the era. With its direct style and unapologetic message, the article hit the journal's main readership like a ton of bricks. One morning, Einstein received the famous publication and came across Friedman's article. This Russian he had never heard of was suggesting his calculations were faulty. Stung to the quick, he published a scathing response on September 18, 1922, in the same journal. The results obtained in Friedman's paper regarding a non-stationary universe seemed suspect to me. In fact, it turns out that the solution given does not agree with the field equations. For Friedman, Einstein's rebuttal came as a heavy blow. He had already sensed a silent hostility growing between himself and certain colleagues affiliated with the Communist Party. But if Albert Einstein himself, a recent winner of the Nobel Prize, had spoken against his theory, he could not do much to make his voice heard. On the evening of December 6, 1922, Friedman called upon the aid of one of his students, Vladimir Fock, who had a stake in the fight because his thesis director was none other than Friedman's faithful supporter, Krutkov. Together they wrote the following note: "Considering that the possible existence of a non-stationary world has a certain interest, I will allow myself to present to you here the calculations I have made, for verification and critical assessment. Should you find the calculations presented in my letter correct, please be so kind as to inform the editors of the Zeitschrift für Physik about it. Perhaps in this case you will publish a correction to your statement or provide an opportunity for a portion of this letter to be published." It worked. In early May 1923, Krutkov set out to find Einstein, meeting him in Holland. Walking Einstein through the calculations step by step, on May 7, 1923, Krutkov succeeded in convincing him, with the aid of indispensable theoretician Paul Ehrenfest, an old friend of Einstein's, that Friedman's approach was sound. As soon as he returned to Berlin on May 21st, the father of relativity sent what was to become a historic note to the Zeitschrift für Physik, published June 29, 1923. My criticism, as I became convinced by Friedman's letter communicated to me by Mr. Krutkov, was based on an error in my calculations. I consider that Mr. Friedman's results are correct and shed new light. A calculation error, a thundering admission. The note was published Friday the 29th of June, 1923. With these few lines, modern cosmology was born. The Big Bang pioneer triumphs. Friedman could finally savor his victory. Straight away in that same year, with the help of Vsevolod Frederiks, he published a work entitled The World as Space and Time. His readers were astounded to discover that the universe had a beginning billions of years ago. What sort of a cosmos do we live in then? At the dawn of time, the entire universe with its billion stars was contracted within a point of zero volume, and then, from this point, it increased its radius to a maximum value, then it decreased again to become a point again, and so on. This kind of conclusion was simply insupportable for the Bolsheviks, all the more so since Einstein himself now seemed to recognize its validity. The murmurs that had spread slowly throughout the St. Petersburg University halls had subsequently grown into a roar threatening the tenets of Marxism-Leninism. For although the authorities had up till now tolerated this scholar's writings, every line they contained starkly contradicted dialectical materialism, which held that the universe is static, eternal, and without beginning. For the new masters of the regime, the solution was simple: end the myth of creation once and for all, along with anyone who dared to propagate it. Destroying the myth of creation. Thenceforth, the order of the day was to eliminate any scientist even vaguely suspected of violating the teachings of dialectical materialism. The regime accused them of anti-Soviet propaganda. These supposed enemies of the Bolshevist state began to disappear to far-off Siberia or fall before the firing squad. The merciless hunt commenced in the winter of 1923. Measures were taken to silence Friedman. Several of his seminars and courses were inspected by agents of the political police who came to the lecture halls armed to the teeth. But Friedman would not be bullied into silence. Clashes broke out between the Bolsheviks and the mathematician students, in particular 4 talented young men who were seen together so often that they were known by all Leningrad as the Musketeers. The youngest was a mathematical genius named Lev Landau, who earned his bachelor's degree at the age of 13 and was still an adolescent in 1924. His best friend, George Gamow, knew the theory of relativity better than anyone. Matvei Bronstein had already begun to write a book on the origin of matter, and Dmitry Ivanenko knew all there was to know about what was then coming to be known as the Friedman equations. These brilliant mathematicians enthusiastically spread far and wide the astonishing news that the universe is not fixed and that, therefore, it had a beginning. In packed lecture halls, Friedman was greeted with thunderous applause each time he uttered in a hushed voice, "Gentlemen, we have demonstrated that the universe has not existed forever. It had a beginning several billion years ago, in a far-off age when it was no bigger than a speck of dust." He was a resounding success even among non-scientists. The party leaders were not pleased. The fearsome chief of the political police, Felix Dzerzhinsky, ordered his men to start tailing Friedman in 1924. In spring 1925, the university directors who were affiliated with the party tried to prevent him from teaching his theory of cosmic expansion. But this pioneer of the Big Bang abruptly died the following September at age 37, reportedly of typhoid fever. The young George Gamow was convinced that his teacher had been the victim of a conspiracy. He confided his suspicion one autumn evening in 1925 to mathematician Jacob Tamarkin, Friedman's most faithful companion. Tamarkin never forgot those nights spent together when the two friends demonstrated that space-time had been created in a single instant in the distant past. In the 70s, the Nobel Prize-winning Russian Andrei Sakharov would call this instant the Friedman singularity. After his clandestine conversation with Gamow, Tamarkin realized that his highly suspect ideas and his proximity to the Friedman group made him a prime target for the political police. He made up his mind just a few hours later. He would leave the Soviet Union. So it was that in 1925 Russia lost 2 of its most brilliant scientific minds, Friedman, who was carried off in September by a suspicious fever contracted upon his return from his honeymoon, and his close friend Tamarkin, who secretly emigrated to the United States, where he began a new life. Unfortunately, Gamow was not so lucky, nor were Friedman's other students, least of all the ones most closely associated with him. These faithful disciples would soon begin to feel the weight of the regime's iron fist. But not quite yet. After Friedman's death, the campaign of repression and intimidation against scientists who believed in the creation of the universe was put on hold for several years. First of all, since the death of their leader, his students, now well aware of the danger, began to act more discreetly. For another thing, during this period the Soviet regime had to grapple with 2 recent scientific events whose impact resounded throughout the whole world. The first took place in 1927, the bombshell publication of Father Lemaitre's new theory of cosmic expansion. The scientists of the regime swatted away the Belgian Canon's article with a backhand stroke. What a waste of time! 2 years later, in 1929, American astronomer Edwin Hubble actually observed the expansion of the universe using the huge Hooker telescope on Mount Wilson. Here was the first observational confirmation that Friedman had not been mistaken. Stalin and his lieutenants reacted at once, officially disparaging the monumental discovery as American propaganda and silencing any proponents of expansion. Russian astrophysicists, led now by Gamow, could no longer speak out. As Stalin slowly took over the Soviet Union's enormous state apparatus with the aid of the fearsome Molotov, the campaign against ideas threatening Marxist materialism's sacrosanct doctrines became more and more brutal. In 1926, Vyacheslav Menjinsky succeeded Felix Dzerzhinsky as head of the secret police and at once unleashed his bloodthirsty agents upon the supposed dissidents. Meanwhile, Stalin had found his bearings. He secretly began to prepare the grand show trials and mass executions that from the early 1930s would successfully reduce to silence those they now called Lemaitre's henchmen. 2. Mass Crimes Against Cosmologists. In the early 1930s, under pressure from the man who now referred to himself as the Little Father of the People, the machinery for eliminating these scientists was set in motion and quickly spiraled out of control. One particularly striking example of the new mass repression was the Pulkovo affair, a long series of state-sponsored murders organized in the 30s against astronomers and astrophysicists, most of whom had been close to Alexander Friedman and were firmly convinced that the universe was not eternal. It was no accident that this murderous repression was centered in Leningrad. For one thing, Leningrad was Friedman's native city, the place where he had discovered and circulated his ideas. But there was another reason. In 1934, one of Stalin's devotees, Andrei Zhdanov, was named Secretary General of the Communist Party of Leningrad. A self-proclaimed ideologue of the regime and the methodical organizer behind the great Stalinist purges, Zhdanov summed up the Soviet stance toward the Big Bang in a few vitriolic words, calling Lemaitre and his crew imposter scientists who seek to bring back to life the fairy tale according to which the world came out from nothing. His objective was to savagely hunt down Lemaitre's reactionary scientists. Anyone who spoke or wrote about expansion was systematically eliminated. By 1931, Gamow and his friends in Moscow knew that Western scientists had begun to discuss the possibility of matter itself having a beginning. They were resolved to open the conversation in Russia, but the Soviet Empire's new masters, Stalin, Molotov, Bukharin, Beria, were now openly hostile to Western science. They believed matter was eternal, and no one, especially not Friedman's former students, was allowed to say otherwise. Gamow was the first to sense the danger. When his passport was confiscated in 1931, he felt the walls of his country close in around him like a prison. In the spring of 1932, he attempted to cross the Black Sea in a kayak with his wife, hoping to reach Turkey. A few months later, he tried to flee to Norway, but this attempt nearly ended in shipwreck. All seemed lost until 1933, when the regime miraculously granted him a visa requested by Niels Bohr and Paul Langevin to attend the prestigious Solvay conference in Brussels. He would never again set foot in Russia. Immediately declared a traitor to the regime, he was sentenced to death. But through the help of Marie Curie, Gamow and his wife left Europe for good and moved to the United States in 1934. Unfortunately, the other musketeers were not so lucky, as we shall soon see. Landau, Ivanenko, and Bronstein followed a different path, falling into the clutches of the repressive regime. The tragic Pulkovo affair. It is March 1935, the end of a long winter. It is night, but a man has been at work for a long time. His name is Vladimir Fock. This brilliant mathematician and physicist is a chip off the old block. He is the son of Alexander Fock, a surveyor and the USSR's chief engineer of waters and forests. But that's not all. While studying physics at the University of Leningrad, he was a loyal student of Alexander Friedman. Though his relation to Friedman was a maddening thorn in the Bolshevik side, Fock skillfully navigated the pitfalls of Leningrad University life and became chair of the Department of Theoretical Physics in 1934. That year, he gave a series of conferences at the celebrated Astronomical Observatory of Pulkovo, well known as the premier center for astronomical research of the Academy of Sciences of the Soviet Union. His arrest by police officers takes place in the middle of the night. Fock is accused of high treason and of plotting against the ideology of the state. After 3 extremely trying days of isolation, during which he was denied food, Fock learns that he has been linked to the Pulkovo conspirators, traitors to the state who claimed that the universe had a beginning billions of years ago. However, for his torturers, dialectical materialism epitomizes the triumph of reason. The universe has always been just as it is, and so it will be forever. If the universe did indeed have a beginning, who then set it all in motion? Fock senses that they want to extort a declaration of faith from him to make him say that God created all that exists. But the physicist knows the price for such an admission. The penalty for such a crime would be death. At the end of this kangaroo court, the Bolsheviks told him that he would be shot. His crime was to have been Friedman's student and to think, as he did, that the universe was in expansion, to believe that in the distant past the universe was no larger than a speck of dust. He is accused, like Friedman, of having fudged his calculations to yield a false result for the field equations of general relativity. Faced with a situation simultaneously horrible and absurd, disbelief weighs heavily on Fock's shoulders. But even as the execution day approaches, a miracle happens. The miracle worker's name is Piotr Kapitsa, an extraordinary scientist in the USSR. Kapitsa would go on to win the Nobel Prize in Physics in 1978, the same year as Arno Penzias and Robert Wilson, who discovered the famous trace left in space by the Big Bang, fossil radiation. Kapitsa was also the only scientist outside of the Communist Party to be admitted to the Russian Academy of Sciences, and thus the only Russian scientist of note opposed to Stalin. Having already saved the life of Lev Landau, one of Friedman's four musketeers, he also saves Fock in 1935. Once freed, the physicist goes right back to work. The nightmare begins again. On a frigid night in 1937, Fock is again arrested and thrown into prison. He screams that he has already been tried and cleared, but to no avail. More charges have been brought against him. First of all, he had been seen revisiting the Pulkovo Observatory, that astronomical sanctuary where Friedman and his students had passionately worked in the early 1920s, a place literally cursed by the regime. And then, wasn't it a spy at Leningrad University who discovered that he had delivered a scandalous lecture on the alleged origin of the universe? Kapitsa moves heaven and earth to secure an audience with Stalin and once more obtains an order for Fock's release. This time, the nightmare is finally over for good. Yevgeny Perepyolkin, sent to the Gulag and shot. Most Russian astronomers weren't so lucky. The first of all was a young physicist named Yevgeny Perepyolkin, who had followed Friedman since 1922 and was a passionate participant in the debate sparked by the controversy between his teacher and Einstein over the origin of the universe. In 1934, when he was only 28, he was named professor of astronomy and then chief of the astrophysics lab at the Pulkovo Observatory. He became a champion of Friedman's teachings. Reworking his teacher's calculations step by step, the young Perepyolkin again demonstrated beyond a shadow of a doubt that the field equations of general relativity point necessarily to a dynamic universe rather than the static one conceived of by Einstein. In other words, the cosmos is not set and eternal, it is growing with every passing instant. The conclusion is inevitable. The universe had a beginning long ago. In his courses, the young astrophysicist hammered this great discovery into his students. But he did not recognize the danger that hung over his own person. In the middle of the night, on May 11, 1937, he was suddenly snatched from his bed and arrested. He was accused of being an accomplice to Leon Trotsky's anti-Soviet activities and, after a rushed trial, was sentenced to 5 years in prison. But this was not enough. One morning, while he was still serving his sentence, the terrible NKVD, predecessor of the KGB, decided to retry him, this time for much graver crimes, undermining the regime's ideological basis by denying the eternity of the universe and refusing to admit that the idea of God is completely without merit. He was shot the next day, on the frigid morning of January 13, 1938. He was barely 30 years old. Soon to meet the same fate was a school friend he knew well and deeply admired, Matvei Bronstein. Bronstein, tortured and shot. The young man was one of the four musketeers of Leningrad, a disciple of Friedman alongside Gamow, Landau, and Ivanenko. A mathematician more than half a century ahead of his time, he had tried to develop a physics that united the infinitely large and infinitesimally small in a single theoretical body, in other words, combining general relativity and quantum mechanics. Bronstein's quantum gravity remains mysterious to this day. As a youth, Bronstein befriended Nobel laureate Andrei Sakharov. A few years later, he wrote wonderful books of popular science for children. Alongside his friends Gamow and Landau, he broadcast the news far and wide that the universe had a beginning billions of years ago. In 1937, as he was working peacefully at home, he was dragged away by officers right in front of his wife. She never saw him again. Sentenced to death by the military collegium of the Supreme Court of the Soviet Union, Bronstein was shot in the back of the neck on February 18, 1938. He was only 31 years old. but the regime's hit list had many more entries. Dmitry Europekin, condemned and shot. On September 4, 1936, astrophysicist Dmitry Europekin, who also found Friedman's revolutionary ideas intriguing, was arrested in the middle of the night just like the others. On May 25, 1937, he was sentenced to 10 years in prison without right of correspondence or visitation. But the NKVD thought the sentence too light. Only death could put an end to the contagious heresy that everything in existence originated with a God more powerful than the Soviet Union. Accused of spreading anti-Marxist propaganda among his fellow detainees, Europekin was shot on January 20, 1938, at just 29 years old. Boris Numerov, deported, tortured, and shot. A month after Europekin's arrest, it was the turn of one of his best friends, Boris Numerov. But this man was not just any scientist. First of all, he was a brilliant mathematician, a quality he shared with Friedman, whom he had known for many years and with whom he spent long hours working out equations on the blackboard. Since 1920, the whole university had used the famous Numerov method to resolve difficult second-order differential equations in the blink of an eye. Always in good spirits and ready to help others, he climbed swiftly at the university. At age 21, he was already the president of the Russian Astronomical Society. 2 years later, he was made head of the Astronomical Institute at Leningrad, where he immediately invited Friedman to give a series of conferences. But Friedman's success had reached Stalin's ears. Although the man of iron was not yet in the grip of that murderous folly which set off a terrifying wave of purges in the 1930s, the little father of the peoples had a long memory. Numerov's friendship with Friedman left faint traces of suspicion in Stalin's mind. On the night of October 22, 1936, Numerov was arrested and then placed into solitary confinement in the terrorist wing of Kresty prison northeast of Leningrad. He did not see another human being, nor did he leave his cell until the day of his trial, May 25, 1937. On that day, he was sentenced to 10 years of forced labor for espionage and anti-Marxist propaganda. But once again, the regime found the punishment too light. In the autumn of 1941, Numerov was blindfolded and led into the forest of Medvedev. On Stalin's personal orders, Numerov's torturers broke his legs with the butt of a rifle before beating him to death like a dog. Maximilian Musselius, condemned, imprisoned, and shot. From 1937 onward, the repression intensified against the adversaries of the theory of an eternal universe. On February 11, 1937, Professor Maximilian Musselius was arrested and sentenced to the usual 10 years of prison. Again, as usual, this light sentence attracted the NKVD's bloodhounds, who decided to review the earlier trial. Condemned a second time for anti-Soviet propaganda, the unfortunate astronomer fell before the firing squad on January 20, 1938. Vsevolod Frederiks, arrested, condemned, and dead after 6 years in the Gulag. The same treatment was reserved for Vsevolod Frederiks, one of Friedman's most faithful intellectual companions. In the 1920s, his seminar on general relativity at St. Petersburg University had packed the lecture halls. Frederiks had also contributed to the calculations for the dynamic solution of Einstein's equations. Thus he was absolutely convinced, and had the math to prove it, that the universe had a beginning. He continued to defend this position long after Friedman's death. Accused of creationism in 1937, he was similarly sentenced to 10 years in chains. Miraculously, he was spared the firing squad, but hunger and the ill treatment he received in prison left him gravely weakened. He died in 1944 after 6 bitter years of forced labor. Innocenty Balanovsky, denounced and shot. Another of Friedman's colleagues, Innocenty Balanovsky, was denounced to the police in the same period for defending Friedman's ideas. At first he was sentenced to 10 years in a labor camp. According to some, his life ended with an execution by firing squad in 1937. Nikolai Kozyrev, sent to the Gulag and sentenced to death. Nikolai Kozyrev, initially sent to a forced labor camp in 1937, was also sentenced to death, accused by Zhdanov's men of teaching the detainees that the universe was born in an explosion more than 10 billion years ago. Miraculously, he was not shot for the simple reason that on the morning of the fatal day there were not enough executioners to form the firing squad. The Stalinist regime had intended to make a chilling example out of these towering intellectuals, but in April 1948 the Big Bang Theory took a giant leap forward. George Gamow, Friedman's closest disciple, burst back onto the scientific scene from across the Atlantic through the joint publication, along with Ralph Alpher and Hans Bethe, of an explosive article in Physical Review. Its provocative claims quickly spread across the globe like wildfire. What do the authors assert? They propose that the light elements of matter, protons and neutrons, could only have formed during an extremely hot phase of the universe, with temperatures soaring to billions of degrees, far exceeding those of stars. And they calculated the relative abundance of the lightest elements, 75% hydrogen, 25% helium, along with traces of lithium and beryllium, which in itself constituted an extraordinary finding and which was a compelling new way to prove that the Big Bang took place. Just as they had suppressed Hubble's discovery in 1929, for a time the Soviets were able to stifle Gamow's article, along with all serious research in cosmology. In fact, in the 40s and 50s, nearly all astronomers scrupulously towed the party line, led by physicists like Boris Vorontsov-Velyuminov of Moscow, who shouted down every hall in the Academy of Sciences that Gamow was an Americanized apostate. Then there was V.E. Loew, who supposedly referred to the Big Bang as a cancerous tumor that corrodes modern astronomical theory and is the main ideological enemy of materialist science. Censure and condemnation lasted into the second half of the 20th century, a dark period in which Bolshevik repression would assume its final form. 3. The fall of dialectical materialism. Spring 1963. The early 1960s marked a sea change for scientists, especially those who studied the universe. 10 years earlier, the Great Purge had ended with Stalin's death, and the new leaders of the USSR were committed to radical de-Stalinization. A new generation of physicists emerged in the more tolerant atmosphere that now prevailed, and this fresh crop of scientists was delighted to rediscover the research of Friedman and Gamow on the origin of the universe. They were led by Igor Novikov and Andrei Dorishkevich, two young researchers from the University of Moscow. Both were students of the legendary theoretician Yakov Zeldovich, one of the fathers, along with Sakharov, of the hydrogen bomb. In 1964, Novikov and his colleague made a prediction that Zeldovich gladly supported. Following the main points of Gamow's theory, they advanced the thesis that, though the wave of intense heat from the Big Bang, 100,000 billion degrees, has cooled down, a trace of it remains in the sky. The two young researchers were also the first to propose that this ultra-cold relic is blackbody radiation. In other words, it is in thermal equilibrium and therefore extremely uniform at every point in the cosmos. Quite sure of themselves, they added that it is possible to detect this fossil radiation in the microwave range of the spectrum. These two extraordinary predictions could have propelled the USSR to the front of the Big Bang race, but the regime's passive hostility to cosmology meant that the field was ceded entirely to American scientists. In May of the same year, 1964, two young American astronomers, Arno Penzias and Robert Wilson, using an immense radio telescope in their work for Bell Telephone Company, made what is often considered the greatest discovery in history: fossil radiation, a faint echo of the Big Bang. The pair would go on to become Nobel laureates in physics in 1978, alongside the courageous Russian scientist Pyotr Kapitsa, who had stood up to Stalin in the 30s and snatched Landau and Fock from certain death. Deeply impressed by the discovery of fossil radiation, the leading lights of nuclear physics turned toward cosmology in the 1960s, more or less openly adopting the Big Bang model. But the game was still far from over. Despite its crucial importance, Penzias and Wilson's discovery did not radically change the doctrine of the Soviet regime, which obstinately clung to the belief that the universe is composed of eternal matter. This ideological blind spot meant that Soviet scientists were practically forced to keep silent about the Big Bang until the collapse of the USSR. While death sentences and deportations to the Gulag stopped with Stalin's death in 1953, the regime devised other methods such as house arrest, or worse, commitment to a psychiatric hospital. Psychiatric prison. The year is 1968. A fresh breeze of liberated thought is blowing across France, and certain gusts travel as far as student groups in Russia. In that year, a young mathematician, Leonid Ploosh, a researcher at the Moscow Institute of Cybernetics, became a dissident. The Ploosh affair caused a stir throughout Europe, especially in France, and was typical of dialectical materialism in its death throes. The affair began with 4 students receiving the harsh sentence of forced labor for the crime of anti-Soviet agitation and propaganda. Disgusted by this, the young mathematician joined a group of intellectuals who, like him, were determined to put an end to indoctrination. Keen on cosmology and convinced that fossil radiation definitively resolved the question of the Big Bang, Ploosh could not stomach the regime's refusal to let him organize scientific conferences or speak the truth about a subject he loved so much. Heedless of the consequences, he sent a letter to the United Nations Commission on Human Rights, demanding an investigation into the USSR's violations of the rights to freedom of conviction and to propagation of ideas through legal means. The regime's reaction was swift. He was immediately dismissed from the Institute of Cybernetics and interrogated by the KGB, who also confiscated his manuscripts. After a period of increasingly strict surveillance, accused of anti-Soviet activities, he ended up being arrested in 1972 and thrown in prison. 1 year later, after a secret trial he was not even allowed to attend, the hammer fell. Ploosh was declared insane and sentenced to treatment at the special psychiatric hospital at Dnipropetrovsk, where patients with the most serious cases of psychosis were confined. Overnight, Ploosh was locked in a windowless, padded cell, which he left only to undergo frightful sessions of electroshock therapy. Little by little, his mind began to falter, and for a time he lost the power of speech. As he explained after his liberation in 1976 in his book History's Carnival, although I tried to spit out the drugs when I could, they were killing my desire to read or think. My memory was slipping away, and my speech became jerky and abrupt. I was overcome by autism and tried to sleep. I was increasingly afraid that my deterioration was irreversible. I, too, was losing my will to live. I maintained a grip on myself only by saying over and over, I must not become embittered. I must not forget. I must not give up. After a year of detention, the psychiatrists commissioned by the regime were told to examine the patient and provide a diagnosis. The special commission concluded that Ploosh was suffering from reformist delirium exacerbated by messianic elements. Like the scientist martyrs who came before him, his case centered around the question of God. This is what he confided in 1992 to Alexander Ginsberg, the young student for whom he fought in 1968 and who was the origin of his condemnation. When I was 11 years old and a devout believer, one of my teachers managed to prove to me that God did not exist. With this denial, I became an educated man. In the early 1970s, clearly still no room for God. The imprisonment of Ploosh set off international waves of protest. 650 American mathematicians wrote a letter to the Soviet ambassador, and Henri Cartan brought the matter before the 1974 International Congress of Mathematicians held in Vancouver. But the most notable intervention was that of physicist Andrei Sakharov, who had just completed his model of the universe based on the Big Bang. He even dared to call the origin of the universe the Friedmann singularity, the ultimate provocation. Sakharov denied that matter was eternal and held that the universe was finite in both its past, the Friedmann singularity, and its future. In particular, he was the first to postulate the disintegration of the proton, the particle of matter previously assumed to be eternal. This claim earned him the wrath of the Academy of Sciences. As his ideas continued to find confirmation, the great physicist increasingly chose the path of dissidence, undeterred by repeated calls to order from the regime's tribunals. In the West, his actions met with praise and the highest recognition of the Nobel Peace Prize. As might be expected, the Soviets forbade Sakharov from crossing the Iron Curtain, and his wife had to go accept the prize in his name. He kept up his activism. The day of the prize ceremony, Sakharov traveled instead to Vilnius to advocate for Leonid Plush at his retrial, an act that proved decisive for Plush's liberation and expulsion to France. In the same period, the father of the H-bomb increasingly turned away from hard physics and towards cosmology. He grew close to researchers committed to the Big Bang and organized conferences and gave seminars on the origin of the universe. But the subject remained dangerous. In the end, his outspoken defense of Plush, his widely publicized research on the Big Bang, and his other activities would cost him dearly. On the morning of January 22, 1980, Sakharov was arrested in the middle of the street. A few hours later, without a trial, he was deported to Gorky, today Nizhny Novgorod, a city off-limits to foreigners. There he was put under house arrest, with armed police at his door night and day. He was forbidden to correspond or meet with anyone and was effectively reduced to silence. His rooms were searched each week. Anything he wrote or hid from his guards was inevitably confiscated. In May 1984, he began a hunger fast that left him hospitalized. At the hospital, he was force-fed and kept for 4 months in total isolation. Upon returning to Gorky, he was still denied the right to any contact with the outside world. In April 1985, he began a second hunger strike and was again brought to the hospital to be force-fed. The ordeal ended on December 19, 1986, when Mikhail Gorbachev called Sakharov to tell him that he was free to return to Moscow. He was the last on the long blacklist of scientists persecuted by the regime for their conviction that matter is not eternal and that it does not constitute the whole of reality. In Soviet Russia, most scientists who believed in the Big Bang suffered physically for spreading a revolutionary theory that challenged the eternity of matter. This noir thriller has had its heroes and hangmen, its reversals and tragic twists. Between the lines, we can read the doubts and inner conflicts these scientists endured for their faith in this scientific phenomenon, a drama reminiscent of the novels of Dostoevsky. In Nazi Germany, the violence exercised against partisans of the Big Bang took on an administrative and procedural guise more reminiscent of a Kafka novel, until the mask was dropped to reveal a face twisted by the fanatical brutality of the Nazi regime. 2. Nazi opposition to the Big Bang. 1. Hitler declares war on God. As we shall now see, while persecution was less widespread, the fate reserved for supporters of the Big Bang in Nazi Germany was hardly more enviable. Our story begins with certain German scientists oppressed since the early 1920s by the rising tide of a then obscure movement. No one suspected the future danger it posed to society, nor how it would expand and organize itself into the second most bloody totalitarian regime of the 20th century. Right from the start, it was also willing to use its iron boots to stamp out all science supporting the idea that matter was not eternal. February 1920. It is the second time the tiny German Workers' Party, founded by the ultranationalist Anton Drexler, has met this year. Perched on a crate, the orator unleashes a torrent of black oaths against the villains who have banded together to bring the great nation of Germany to its knees. The man's name is Hitler. A few sharp cries hammer his point home. The time has come to replace the German Workers' Party with the National Socialist German Workers' Party. The galvanized audience roars its approval. On this night, the Nazi Party is born. November 1922, at the Friedrich Wilhelm University in Berlin, the most popular physics course in the university has just ended. The students leave the lecture hall in small groups. They know they are fortunate. Their professor is none other than Albert Einstein. 2 electrifying discoveries in less than 3 years have made him a household name the world over. The first came in 1919 when Sir Arthur Eddington experimentally verified the famous theory of general relativity. Then, in 1921, Einstein won the Nobel Prize, making him an intellectual celebrity. That evening, Esther Salomon, a student studying theoretical physics, approaches Einstein's desk. After a moment's hesitation, the burning question escapes her lips, and she dares to ask the great scientist what it is exactly that he is looking for in his equations. Einstein answers the student in little more than a whisper. I want to know how God created this world. I am not interested in this or that phenomenon, in the spectrum of this or that element. I want to know his thoughts. The rest are details. God's thoughts. The phrase caught on. It traveled around Germany, enraging some members of the newly created National Socialist Party. In 1922, the Nazi terror was still a ways off. But that year, Einstein began receiving anonymous death threats by post. His fate, and that of a great number of scientists and experts on the evolution of the universe, was already sealed. Only when he came upon Soviet scientist Alexander Friedman's famous article did Einstein at last begin to suspect, though he did not yet admit it, that his own equations of general relativity might describe an expanding universe. They might mean that the universe had a beginning. In the early 1920s, this foolish idea was nothing more than a rumor. But as we shall see, this faint spark would ignite into a fire greater than anyone could have imagined. In December 1923, Einstein's shocking declaration about God made its rounds at the university. Privately, the students mocked their professor for mixing God and science. But it also ruffled the feathers of the Prussian professorial elite, backs ramrod straight under their wing collars. The majority had been gradually won over by the theories of the folkish thinkers, that is, by German far-right populism, and so had become proponents of a pantheist or animist conception of the universe, hostile to the idea of an intelligible God. This new mystical and anti-scientific view of the German race sought to return to pre-Christian Germanic sources in which nature is eternal. In this context, any ideas that placed limits on the power of the gods in German mythology, represented, for example, by Wagner's Wotan, became increasingly suspect. The worst was yet to come. As we have already seen, on June 29, 1923, Einstein published a note in the famous scientific journal Zeitschrift für Physik, in which he confirmed Friedman's hypothesis that the universe is not fixed. Even worse, he recognized that the equations of relativity describe an expanding universe. The publication had made waves in the Soviet Union, but its reverberations were also felt in Germany, making their way to the ears of the leaders of the newly formed Nazi Party. Einstein saw threatening clouds gathering on the horizon. Who was his main enemy? The agitator we met earlier, Adolf Hitler. Hitler. Although he didn't understand a word of it, he found its suggestion that matter is perishable disgusting. According to his close friends, Bormann, Heydrich, Himmler, Goebbels, and Speer, Hitler, seething with rage over the bad luck that had landed him in prison and profoundly influenced by party ideologues Alfred Rosenberg and Gottfried Feder, became increasingly viscerally materialistic. Despite his facade of Christianity, Hitler began to distance himself from both the Church and Christianity in 1925, as reflected in his book Mein Kampf and his public speeches. From the 1930s onward, under the influence of the violently anti-clerical Himmler, he rejected any idea of an immaterial God outside nature. Matter, he was now convinced, is eternal, and any attempt by science to question this principle should be, in his own words, killed in the cradle. It comes as no surprise, then, that the Jewish Einstein would become a target of the Nazi regime. Einstein was more or less aware of all this. He had already been heckled by a group of nationalists for presiding over the Third Congress of the World A-National Association, SAT, held in the university town of Kassel, Germany in 1923, with the aim of promoting universal supranational bonds between peoples. The ultranationalists took this decision as a direct provocation. That same year, Einstein's difficulties began to mount. He had already weathered the furious attacks of experimentalist Johannes Stark, winner of the 1919 Nobel Prize in Physics. His goal, which he shared with many of his colleagues, was to utterly destroy general relativity, the product of what they called Jewish physics. This group vaunted themselves as the only representatives of pure Aryan physics, and they harshly criticized relativity for opening the door to the possibility of a non-eternal universe. They remembered how the Russian mathematician Alexander Friedman had burst through that door in 1922 by publishing his famous article on the Big Bang Theory in the German review Zeitschrift für Physik. Stark and most of his colleagues were part of the National Socialist movement. One Thursday evening, the professor had just finished his lecture. With his notes tucked under his arm, he hastens in short steps down the interminable corridors of the university. He is soon joined by his longtime friend, physicist Paul Ehrenfest, who is a Jew like himself. Ehrenfest speaks Russian fluently and for years gave courses at St. Petersburg State University. He often met with a young Friedman, one of his best students, and knows his model of an expanding universe like the back of his hand. He is ready to defend it against all comers. Soon the two scholars hear patriotic chants coming from the inner courtyard. Next, far-off cries as if a brawl has broken out in the darkness. Slightly worried, Ehrenfest takes Einstein by the arm and leads him toward the exit. But Einstein is nervous. Something has to be done, he says, about the rise of anti-Semitism, which is growing stronger by the day. Ehrenfest nods his approval, but something else is bothering him. He confides to Einstein that a famous Russian mathematician named Friedman might be right about his new solution to the equations of general relativity, a dynamic solution demonstrating that the universe is not fixed and that it had a beginning. Ehrenfest is completely convinced that Friedman is right and had already broadcast this fact loud and clear a few weeks ago during a conference at the university in Berlin. It had earned him a flood of insults from a band of brown-shirted youths huddled in the back of the lecture hall. Even worse, he had been reprimanded by the vice president of the university, who advised him to moderate his opinions. But what can be done? How can we not recognize that Friedman's solution is the most logical and that we have to rethink the equations of relativity? When he hears the word relativity, Einstein raises an eyebrow but is only half listening. To hell with calculations. What worries him is the violence against Jews, against science. Autumn 1925. Einstein learns that Alexander Friedman, who 2 years earlier had verified the calculations demonstrating that the universe had an origin, had just disappeared. Everyone at the university knows that he has been entertaining Friedman's notion that the universe is not eternal. One evening, Rosenberg told his Nazi comrades that renegade Einstein is giving credence to the mad theories of these Russian scientists who believe matter came to be at some time in the distant past. In fact, this same year sees the first serious rifts appear between Einstein and the German scientific community. Every day, at the university and elsewhere, he is forced to defend his ideas against a stream of vicious attacks. He ignores none of the increasingly bitter critiques raised against the theory of relativity even after he won the 1922 Nobel Prize. Day by day, a growing number of extremist physicists view his scientific constructs as an insult to nature, as the regrettable result of typical Jewish thinking. Gradually, the opposition organizes and begins to operate openly against Einstein. First, we have the particularly caustic assaults from the two German physicists mentioned earlier, Philipp Lenard, whose work on light quanta had inspired Einstein in 1905, and especially Johannes Stark, already mentioned, who had discovered the shifting or splitting of spectral lines in the presence of an electric field. These two well-respected Nobel laureates had become staunchly anti-Semitic. Further, since their studies focused entirely on matter, they were adamantly convinced that matter had neither beginning nor end. Together they swore to purge science of the very idea that atoms and other elementary particles were not eternal. And of course their first target was Einstein, who had dared to commit to writing that Friedman was correct. For the adversaries of a finite universe, this was a stunning blow. Relativity had done nothing less than usher in a new cosmology based on the concept of an expanding universe, a cosmos finite in space and time. Faced with this new danger, the cohort of Nazi ideologues was forced to look for an appropriate response, all the more so as in 1927 Einstein would give a new provocation that would further radicalize the movement against him and the science he represented. On October 29, 1927, the finest minds in theoretical physics gathered at the Hotel Metropole in Brussels, an elegant 19th-century palace smelling of leather and wax. That year, 18 Nobel laureates had met for the famous Solvay Conference, a meeting whose grand goal was to assist in the birth of a new physics. Einstein met a physicist in a cassock, the Belgian canon Father Lemaitre, who had just put the finishing touches on a strange theory that suggested, like Friedman's, that the universe was expanding. Einstein was strangely moved by this encounter. It was the second time that a physicist besides Friedman had spoken to him about the possibility of a cosmic origin. But he was not in the mood to listen today. Earlier that morning, he'd had a furious discussion with the formidable theoretician Niels Bohr, who that very year founded a brand new mechanics of the infinitely small quantum theory. Bohr had become his worst enemy. As the tone of the debate between the two giants of physics became more heated, Einstein had abruptly concluded, "God does not play dice." Once more, the catchphrase made the rounds and proved impossible for partisans of the Nazi regime to bear. Stark and Leonard knew that Einstein had an enormous influence on the whole world. To permit him to say that God governs the universe was therefore unthinkable. But what could they do? Yet upon reflection, the father of relativity did have one vulnerable point. He was Jewish. This fact made their job easier. Above all, they had to retake the upper hand. As good physicists, Stark and Leonard knew it would be difficult to eliminate Einstein and his ideas. To assure the triumph of their Aryan physics, the two agents of the regime launched their anti-Einstein campaign by founding the German Scientific Work Group. Its sole aim? To destroy Jewish physics. On the evening of December 11, 1927, the famous working group opened their inaugural conference with great fanfare in the hall of the Philharmonie Berlin, intending to purge physics once and for all Jewish theories like those of Einstein. A serious attack to come from two Nobel laureates. Curious to understand his enemies' motives and, more importantly, their arguments, Einstein decided to attend the famous conference in the company of physicist and chemist Walter Nernst, himself a 1920 Nobel laureate. Concealed in the back of a private box, the professor listened attentively to every word as colleagues in the first throes of Nazi delirium dragged his reputation through the mud. These fanatics accused him of deceiving the human race with false beliefs. Concerned for his personal safety, Einstein asked Nernst to accompany him back to Haberlandstrasse. He spent the walk back plunged deep in thought, uneasily recalling how in 1922 his friend Walter Rathenau, then a minister in the Weimar Republic, had been murdered in his car merely because he was a Jew. America, January 29, 1931. Einstein has just arrived at the peak of Mount Wilson in California, more than 2,000 meters above sea level. Einstein is exhilarated by the fantastic photos that the American astronomer Edwin Hubble has spread out before him. They were taken using the giant Mount Wilson telescope with its 100-inch lens. He has even glued his eye to the eyepiece of the colossal instrument, and the verdict was clear. The universe is indeed expanding. But far from convincing the Nazi ideologues, Hubble's fantastic discovery had radicalized them even further. Their only objective was now to convince the German people at all costs that general relativity was a deception based on a jumble of errors. A dozen determined physicists got to work. Once again, Stark and Leonard proposed an ideal solution to counter Einstein, a lethal blow from which they hoped he would never recover. October 1931, Berlin. One morning while Einstein was at his home at 5 Haberlandstrasse, the faithful Ehrenfest knocked on his door. Visibly agitated, he waved under the professor's nose a fat volume entitled 100 Autoren gegen Einstein, 100 Authors Against Einstein. Einstein leafed through the publication and furrowed his brow. Not a single well-known scientist had contributed to the volume, but the pamphlet's tone was inversely proportional to the scientific quality of its authors. Riddled with vitriolic personal attacks against Einstein, the work exuded breathtaking aggression, but it was also careless. Once more, the father of relativity was treated as an ignoramus and a traitor to German science, his theory consigned to the flames. Among other choice obscenities, Einstein found himself portrayed as an ass and a weathercock who had once defended the idea of an eternal universe and now had reversed course, pretending to believe the opposite. Shrugging his shoulders, the Nobel laureate returned the volume to Ehrenfest and replied gravely, "To defeat relativity, one does not need the word of 100 scientists, just one fact." Einstein may have dismissed the work with a wave of his hand, but the publication's effects spread like wildfire. A few months later, he was removed from the Bavarian Academy of Sciences under the excuse that his erroneous teaching had perverted the German people. Next, Friedrich Wilhelm University closed its door on him definitively. Pressure against those who defended relativistic cosmology began to mount outside the sacred groves of academe. Realizing that simply writing a book would not be enough to eliminate their sworn enemy, the advocates of Aryan physics decided to shift their campaign into a higher gear. On an autumn night in 1932, Einstein and Ehrenfest met as usual in the Café House. Suddenly, two baton-wielding figures appeared out of the darkness, banded and black-booted men dressed in the brown uniforms of the SA. Swiftly, one of them picked up a paver and hurled it through the window, shattering it and breaking the crockery on the scientist's table. Tied to the rock was a message that Einstein knew was meant for him. "We'll have your hide, you dirty Jew." But these were only the first dark clouds presaging a terrible storm. It would break 1 year later. January 30th, 1933, midnight. After brutally seizing power, supported by Ernst Röhm's SA street fighters, Hitler is elected Chancellor of the Weimar Republic. His iron fist swiftly fell on Germany. Within a few weeks, he dissolves and burns the Reichstag, Germany's parliament building, and unleashes his stormtroopers to murder or remove all his political opponents, in particular the previous Chancellor Kurt von Schleicher. Hitler's dream of making all Germany march together in goose step was about to become a reality. At the same time, the police apparatus was set to work crushing dissident scientists. There was nothing to stop him. First stage: sweeping away deceptive theories about a cosmos limited in the past and in the future. Hitler already had a pretext close at hand: freeing Germany once and for all from the infection of Jewish science, a science dominated by perverse manipulators who dared to suggest that no race was superior to any other and that the eternity of nature is a myth. Results were not long in coming. In January 1933, while Einstein was traveling in the United States, a bounty was put on his head. In Germany, his books were thrown in the street and burned alongside his effigy. Hitler would not budge. This filthy Jew had to be eliminated, together with theories that supported the idea that the universe had an origin. But what did he propose to take its place? Hitler ordered Alfred Rosenberg, the party's ideological leader at the time, to find a solution. Like his master, Rosenberg was violently opposed to Christianity and any appeal to God. He believed only in the immutable superiority of the Aryan race and in the eternity of matter, and it was with this harsh creed in mind that he turned to Philipp Lenard. Immediately, Einstein's tireless adversary once more took center stage. With physicist Hermann Oberth, he fabricated a bizarre theory to please Rosenberg and the Nazi theorists called the world ice theory, or glacial cosmogony. This pseudo-scientific cosmogony of eternal ice was forged in the beginning of the 20th century by an obscure engineer named Hans Hörbiger, with the support of amateur astronomer Philipp Vogt. Hörbiger proposed that the universe has existed for all eternity and will exist for all eternity, as it rests on the beginningless and endless rule of the eternal ice, an ever-renewed struggle of fire against cold that finds, with every cycle, ice the victor. Of course, this insane theory would have remained in the shadows if it were not for Philipp Lenard. As it happened, Hörbiger made his task easier since, in his cosmogonic delirium, the engineer insisted that from the heart of the cosmic ice a superior race emerged, giants with blonde hair and blue eyes, the seeds of a new humanity. Thus, in 1932, turning a blind eye to the profound absurdity of the model, Lenard presented Hans Hörbiger's sound German science to Heinrich Himmler, a top official of the Third Reich and Hitler's right-hand man. Himmler, completely ignorant of science, immediately fell in love. As a result, in March 1933, the preposterous glacial cosmogony became the official doctrine of the Third Reich. In the wake of this decision, Himmler decided to issue a new uniform to the SS soldiers under his command. His SS would wear, what else? A glacial uniform, a sinister black outfit meant to evoke the eternal reign of the Third Reich at the heart of a universe with neither end nor beginning. Meanwhile, upon returning from their voyage to America, Einstein and his wife Elsa docked at Antwerp on March 28, 1933, only to receive two pieces of bad news. First, a bounty had been put on Einstein's head, and there was real fear he would be assassinated. Second, the German Reichstag had just adopted a resolution that transformed Hitler's government into a de facto legal dictatorship. Einstein could never again set foot in Germany. To make matters worse, the professor's summer retreat, a small house in the Brandenburg countryside, had been pillaged and sacked by the Nazis. This was too much. Einstein went straight to the German consulate to give up his passport, officially renouncing his German nationality. 3 days later, he sent a scathing letter of resignation to the Prussian Academy of Sciences. When, on the following day, the Nazi authorities initiated a formal exclusion procedure against the scientist, they found he had anticipated them with his letter of renunciation. The physicist Max von Laue, who was present that day at the Ministry of Research, noted in his journal that the fury of the directors at having been outmaneuvered was indescribable. Will the escalation stop there? Of course not. In April 1933, while he was living for several months in the small Belgian village of Coq-sur-Mer, Einstein was alarmed to discover that the new German government had adopted laws forbidding Jews, and also certain suspect non-Jews, from occupying official posts, particularly from teaching in the universities. Overnight, thousands of Jewish scientists were forcibly obliged to renounce their university positions. On May 6, 1933, hoping to staunch this terrible hemorrhage, Max Planck met with Hitler in person. After shouting that "a Jew is a Jew," the Führer went on, "Rather than arguing with me, why don't you go see Stalin? Jewish science is perverting thinking about the universe and is trying to convince us that it has not existed forever." Planck tried to argue further, but Hitler roughly cut him off. "People say I suffer occasionally from nervous debility. This is slander. I have nerves of steel." Planck was forced to beat a hasty retreat without achieving his goal. Science met with another disaster that day. But repression of those who refused to stomach the indigestible cosmic ice theory was only beginning. At the end of March 1933, German mathematician Ludwig Bieberbach, fiercely anti-Semitic and an extreme Nazi zealot, took matters into his own hands. First, he chased out all his Jewish mathematical colleagues at Friedrich Wilhelm University in the name of the party. Next, it was the physicist's turn. In April 1933, Einstein's works were among those targeted by the German Student Union. On April 27th, in Berlin, without the slightest qualm, the SA and other henchmen of the regime threw thousands of books written by Einstein and other relativist astronomers onto a huge bonfire. Intoxicated by this spectacle, the arsonists under the orders of Röhm's men set fire to the houses of 2 astronomers accused of betraying the German workers. Applauding these crimes, the Nazi Minister of Propaganda, Joseph Goebbels, took the stage and proudly proclaimed, "Jewish intellectualism is dead." As for Einstein, even though there was already a bounty on his head, a German magazine put him on a blacklist of criminals most dangerous to the regime with a subtitle, "Not Yet Hanged." They offered an additional prize to the person who turned him in to the authorities, dead or alive. Shaken to the core, Einstein wrote to his friend Max Born, who had already prudently fled to England some months earlier, "I must admit, however, that they have surprised me not a little by the degree of their brutality and cowardice." Day by day, the air around his Belgian refuge became more tense. Strange figures lurked on his street at night, and the death threats accumulated to the point that King Albert decided to place a cohort of policemen and bodyguards at his guests' disposal. Einstein found their constant presence oppressive. He could not take it any longer, and so he made a radical decision to go to America and never again set foot in Europe. October 7, 1933. The American liner Westernland weighs anchor, and the port of Southampton slowly disappears on the horizon. On board, Einstein turns his back on Europe for good, like many other scientists fleeing the barbaric folly that has taken over Germany and threatens to push the whole world over the brink. 2. The Nazi war machine targets the Big Bang. Nuremberg, September 5, 1934. For more than an hour, Hitler has been unleashing an unrelenting flood of anger upon the immense crowd, which stretches as far as the eye can see in the courtyard of the colossal monument designed by regime architect Albert Speer. The Führer would not have missed this grand spectacle for anything in the world. He had designed it as a pagan cult celebration at which, each year, he would speak directly to the people, to all Germany, in this grandiose style, like a god addressing his creatures at his feet. Between two flights of soaring rhetoric, he returns with a mix of delight and rage to what he considers one of his sweetest victories, the expulsion of the Jew Einstein from the Reich, with a kick in the gut. A roar of enthusiasm rises from the crowd, rolling in waves to the immense balcony on which the orator is perched. The time for purification had arrived. Germany had freed itself of one of its worst enemies. The Führer launched into a mystical tirade, exclaiming, "From this day forth we will rule the universe forever." With this astonishing statement began the second phase of the regime's offensive against those who denied that matter and eternity are one. In contrast to the years before the Nazis came to power, the elimination of scientists now proceeded efficiently and methodically, starting with notes and pamphlets targeting Einstein's close associates. One of the first victims of this reign of terror was Otto Stern, an old traveling companion of Einstein. Enchanted by the theory of special relativity, he was only 23 years old when, in 1912, he decided to go to Prague to become Einstein's assistant at the university. When Einstein became the chair of physics at the prestigious Swiss Federal Institute of Technology in Zurich, he accompanied him as his assistant. He spent hours in discussions with Einstein, witnessed his progress towards the theory of general relativity, and shared all of his ideas with him. Stern's advice would prove invaluable to Einstein. While the brilliant scientist could navigate the currents of theoretical physics with ease, Stern had a practical mind. He was an unmatched experimenter who, using his equipment bristling with indicator needles and electroluminescent tubes, had succeeded in penetrating the most intimate secrets of matter. Among other things, as early as 1922 he had succeeded in quantifying spin, the rotation of elementary particles, and had also provided proof of the wave nature of atoms. However, Stern is best known for measuring the magnetic moment of the proton, a feat that earned him the Nobel Prize in 1943. In 1923, he was named titular professor at the University of Hamburg and director of the Physics Institute. His performance in both positions was widely lauded in Germany and beyond. But the Nazis cared nothing for his stellar career. One morning in April 1933, the university's vice-rector paid Stern a visit, flanked by two heavily armed SA officers. When he did not immediately open the door, one of the SA began beating it down. Surprised by the violence of the intrusion, the physicist hurried toward his visitors. Without one word of apology, the grave vice-rector handed Stern a piece of paper and told him that he was no longer director of the Physics Institute, effective immediately. As Stern tried to reply, the SA officer cut him off, warning him, "It's in your interest not to resist." Ill at ease, the vice-rector clarified, "Nevertheless, this measure applies only to the Institute. Until further notice, you will remain a professor at the university." Until further notice. This made Stern's blood boil. He submitted his letter of resignation to the rector the following morning. 15 days later, he fled to America, never to return. Many others share Stern's fate. The first was 1954 Physics Nobel laureate Max Born, whose influence in the early 1930s was considerable. A brilliant teacher, he had directed the theses of the famous Robert Oppenheimer, Victor Frederick Weisskopf, Max Delbruck, and even Pascual Jordan, all leading physicists who contributed decisively to the establishment of quantum mechanics, a field concerned with the infinitely small. His assistants included the renowned researchers Werner Heisenberg, Wolfgang Pauli, Enrico Fermi, Eugene Wigner, and Edward Teller, among many others. And yet, as we shall see, Max Born had all the qualities necessary to displease the Nazi authorities. He had begun his meteoric ascent in 1904 at the University of Göttingen in Lower Saxony, one of the foremost universities in the world at the time. There he met the teachers who became his mentors, the mathematicians David Hilbert, Felix Klein, and Hermann Minkowski, Einstein's former professor of mathematics at Zurich, whom he helped in the formulation of the geometrical structures of space-time. Gradually, he became one of the most indispensable supporting actors on the Göttingen scene. Later, he met Einstein in Berlin. Dismissed due to respiratory failure in 1914, he was available to help Max Planck and Einstein with the difficult calculations of general relativity. By 1925, Born had, like Stern, entered the inner circle of Einstein's immediate confidants. It is no surprise that Born and Einstein were interested in the same subjects and had the same worldview decried by the Nazis as mystical. In 1922, Born was researching the physical constants of the universe, the pure numbers at the basis of physical reality. In the long list of dimensionless quantities, constants that operate independently of the system of units employed, his attention was particularly drawn to the mysterious fine structure constant 1 over 137, which quantifies the strength of electromagnetic force, responsible, among other things, for the good old light that illuminates the pages you are reading right now. The great German physicist was the first to discover that this irrational number, with its incredibly fine-tuned series of decimals, has a close relationship with the speed of light, the charge of an electron, Planck's constant, at the heart of the infinitely small, and even, strangely, with the non-physical constant pi. How can this be? After extensive discussions with his colleagues and countless calculations, Max Born reached a troubling conclusion. If alpha, the fine structure constant, were bigger than it really is, we should not be able to distinguish matter from ether, the vacuum, nothingness, and our task to disentangle the natural laws would be hopelessly difficult. The fact, however, that alpha has just its value 1 over 137 is certainly no chance but itself a law of nature. It is clear that the explanation of this number must be the central problem of natural philosophy. He had said it all. The value of this constant is certainly no chance. Born drove the point home. To his mind, the number could be associated with a power of selection and organization operative in the universe. A power of organization. Born's phrase sounds quite similar to the mind of God evoked by Einstein in Berlin, 1922. Thus it also raised the eyebrows of Rosenberg, Rohn, and their uniformed minions. Nevertheless, Born made a great comeback in 1923 when he was named titular professor of theoretical physics at the extremely influential University of Göttingen. Protected by his mentors, especially by the friendly mathematician David Hilbert, he advanced the physics of his age by leaps and bounds. And yet, in May 1934, as he hurried down a university corridor, 2 members of the SA arrested him and dragged him unceremoniously before the university's new vice president. Dispensing with all courtesy, the stern functionary announced that all Born's activities were suspended and that he had 2 hours to vacate the premises. A few days later, under the strict surveillance of the SA, he fled to the United Kingdom, first to the University of Cambridge and then to Edinburgh, where he succeeded Charles Galton Darwin, the grandson of the great naturalist Charles Darwin, as the chair of natural philosophy. He would receive the 1954 Nobel Prize there, rather than at home in Germany, where he had made most of his discoveries. 1934 marked a turning point in this history. It was the end of an age and the start of a darker and more worrisome period, of which the affairs at Göttingen were emblematic. For half a century, 1880 to 1930, this town in Lower Saxony had dominated the world of mathematics under the unchallenged reign of mathematicians Felix Klein and David Hilbert. Hilbert. Thanks to his essential contributions to a broad range of mathematical disciplines, David Hilbert is one of the most influential mathematicians in history. He wrote the celebrated Hilbert's Problems, a list of 23 vexing mathematical questions, many of which remain unsolved to this day. In quantum mechanics, he lends his name to Hilbert space. Rigorous to the point of obsession, but also abounding in imagination, he was limitlessly bold. One evening in 1934, he was invited to an official banquet in the presence of Bernhard Rust, the Reichsminister of Education, who turned to him with a friendly smirk and asked, "So, Professor, How is mathematics going at Göttingen now that it is free of Jewish influence? Hilbert did not respond immediately. Finally, shrugging his shoulders, he muttered, "Mathematics at Göttingen? What mathematics?" Then he left the table. The purge of intellectuals only intensified. Thus a number of eminent physicists who supported the theory of relativity and a finite universe found themselves, like Einstein, Stern, and Born, expelled from German territory. Such was the case of James Franck, Victor Francis Hess, Lise Meitner, Carl Gustav Hempel, and many others, all expelled at the end of 1933. Others preferred to flee like Einstein, including the legendary physicist and mathematician Hermann Weyl, who had succeeded Hilbert in 1930 as the chair of mathematics at Göttingen. While he was not a Jew, he was close to Einstein. Predictably, therefore, Rosenberg found his conception of a universe finite in space and time intolerable and proclaimed to all Berlin that he considered it his personal duty to bring the renegade Weyl to account. His vulnerable point was his wife Helen. She was Jewish. Soon Helen received the first anonymous letters with insidious threats. It was too much. Frightened by this incomprehensible hate and feeling the danger mount, Weyl took Helen by the hand and decided to leave the university under cover of night. They immediately embarked for America, where they joined Einstein at Princeton's prestigious Institute of Advanced Studies. 1936. Nazi anti-scientific repression takes a sudden, more dangerous turn. Until now, the regime's pariahs had been given the chance to flee, but not all would be so lucky. As the 30s wore on, it became increasingly difficult to leave the Reich. Passports were confiscated and fugitives arrested at the border. Soon Himmler and Hitler, followed by Bormann, Eichmann, Rosenberg, Heydrich, and others, took a new line. From now on, they would eliminate the Reich's enemies by sending them to concentration camps or, even worse, slating them for execution. The mathematician Felix Hausdorff's tragic fate clearly illustrates this downward slide into darkness. Hausdorff was a brilliant mathematician, regarded as the father of modern topology. Today's students of mathematics will recognize his name in the Hausdorff spaces. However, after first considering his ideas a nuisance, the Nazis later set them down as disgusting. Deep in his calculations, Hausdorff took no notice of the impending danger and continued his scientific work as if nothing had changed. The first warning signs came in 1935 when he was suddenly removed from his position. His works were progressively condemned as un-German, then harmful, and ultimately vile. But again he chose to close his eyes to these portents. Soon his family's passports were confiscated, and it became impossible for him to leave the country. One night in 1942, as he was working late in his office at the University of Bonn, police entered, threw him to the ground, and tied his hands behind his back. His wife and sister-in-law received the same treatment. That same night, they were taken to the Bonn transit camp. They would not survive the night. On January 26, 1942, Hausdorff and the two people most dear to him swallowed barbiturates and died under the guard of their tormentors. These tragic events were not isolated incidents. Dozens of brilliant scientists were ruthlessly eliminated by the barbaric regime. This systematic campaign of violence aimed to eradicate not just men but their ideas. The detested proposition that neither the universe nor nature had existed forever, so ruthlessly repressed in the Soviet Union, was among the chief targets of Nazi ire, since it meant that the Germanic race could no longer appeal to an eternal destiny. The fate of mankind was, in the final analysis, inscribed within something much greater than itself. But the fall of the 20th century's two great totalitarian regimes did not end this violent and scarcely comprehensible struggle against the idea of a cosmic origin. The following pages will tell the surprising story of repression that continued even after the end of the Second World War. 3. The Big Bang in the West after 1945. Autumn 1945. A fresh wind now blows across the world, dissipating the haze of murderous chaos that racked Nazi Germany and snuffed out 100,000 Japanese lives in the blink of an eye. Slowly, humanity recovered from the deluge of fire and iron that had washed over it during wartime. Ideas gradually began to flow and circulate once again in their proper channels. And yet, The hypotheses about the origin of the universe continued to struggle to make headway. There were, of course, no more efforts to eliminate, imprison, torture, or execute the adherents of cosmic origin theories, as had occurred under the totalitarian regimes. Efforts to limit the diffusion of ideas about the beginning of the universe set off by a transcendent cause became much more insidious and invisible, but they were no less ferocious in their case against its originators. And Friedman? Missing and forgotten. Lemaitre? Nearly no one believed his theory of the primitive atom. In 1948, George Gamow, Friedman's student you will recall, tried to clarify matters, but he met with little success. Gamow and his doctoral student Ralph Alpher published the famous article in the Physical Review mentioned above, The Origin of Chemical Elements. They claimed that the universe began billions of years ago when it was very small, very dense, and very hot. More precisely, they told their audience, most of them skeptical, that the light elements, especially hydrogen nuclei, emerged in the first few minutes after the Big Bang. This article caused a sensation that hit the newsrooms of all the leading papers. For example, on April 1, 1948, stunned Americans read the following arresting headline in the Washington Post: "World began in 5 minutes." Would the faithful proponents of the Big Bang now come out of the woodwork? Not really. The sensational article on the nucleosynthesis of the light elements had the great misfortune of appearing on April 1, 1948. The idea that the article was nothing more than an April Fool's joke spread quickly, deeply coloring its reception. The Big Bang theory tottered. What came next was the coup de grace. On March 28, 1949, Sir Fred Hoyle, the influential astronomer of His Majesty King George VI at St. John's College, Cambridge, was once more in his London studio at the BBC. Unlike Gamow, who was ignored by journalists, the witty and humorous Hoyle was a media darling. When asked whether he agreed with Gamow that the universe could have begun in a distant past, he was at no loss for words. A beginning? Hoyle threw back his head and heaved a long laugh that echoed in the studio and broadcast to antennas around the world. Catching his breath, he shifted to a confident tone, as if to assure his audience that Gamow was spinning an enormous hoax. When pressed with questions, he doubled down, swelled his chest, and laughed sarcastically. The cosmos didn't begin with some sort of Big Bang. A Big Bang. Once launched, the expression shot like a firework all across England and soon around the whole world. The catchy phrase left a permanent mark on scientific vocabulary, since it was ironic and came from a sworn adversary of the idea of an origin to the universe. The royal astronomer did not back down. "The universe is eternal." Debonair and smiling, he repeated loud and clear that everything Gamow and his students were saying to the poor Americans who listened to them was so much smoke and mirrors, an elaborate ruse calculated to fascinate mere dilettantes in the grove of academe. Firmly convinced he was right, Hoyle rolled up his sleeves and went to work. Through a slew of conferences and articles, he managed to impose his theory of a static universe, one that is fixed and has existed always, without beginning or end, on England and the rest of the world. This was a grievous blow to Gamow and his disciples, but it affected many others as well. Down the gentle slope of the 1950s, the idea of a cosmic origin receded into the distance, drowned in the same wave that had swamped the Big Bang. The Big Bang notion slowly faded from public discourse and even private conversation. Soon, almost no one was talking about it. In peacetime America, as much as in the rest of the war-torn world, people were settling into new rhythms of peace and prosperity. They wanted nothing to do with a band of crackpot intellectuals and their far-fetched musings on the possible creation of the universe. At any rate, the proof for the so-called Big Bang was not convincing enough. Thus, schools and learned societies everywhere kept drilling it in. Matter is eternal, and the Big Bang is a farce. Pushing the rejection of a beginning to the point of caricature, David Bohm went so far as to claim that the partisans of the Big Bang effectively turn traitor to science and distort scientific facts to reach conclusions that are convenient to the Catholic Church. The British physicist William Bonner did not mince words. The underlying motive is, of course, to bring in God as creator. It seems like the opportunity Christian theology has been waiting for ever since science began to depose religion from the minds of rational men in the 17th century. As we have already seen, Sir Arthur Eddington, one of the greatest astronomers of the first half of the 20th century, was equally insistent and seemed to come unhinged when he heard the term Big Bang. Philosophically, the notion of a beginning of the present order of nature is repugnant to me. The violence of these counterattacks will mark a turning point in the lives of these researchers who, at the time, teetered under the blows of their adversaries. Deeply shaken by the barrage of criticism, George Gamow began to disengage from physics and move towards biology, and Ralph Alpher, his best student, universities shut their doors in his face. After skimming the classified ads, he ended up working for General Electric. As for their companion, Robert Herman, he turned his back forever on research to pursue a more prosaic career at General Motors. The man who predicted the Big Bang spent his days designing smaller cars to reduce traffic congestion. Barely a decade later, however, the famous proof was about to explode. Something had created the universe in the very distant past. In 1964, Penzias and Wilson discovered the fossil radiation of the CMB, the mysterious echo of creation that would become the first major evidence for the Big Bang. And today? On January 25, 2018, the prestigious Journal for the Scientific Study of Religion published a compelling article entitled Perceptions of Religious Discrimination Among U.S. Scientists. In the article, Dr. Elaine H. Eklund and Dr. Christopher P. Scheitel, both university professors, showed that American scientists who identify as religious report higher rates of religious discrimination relative to those who do not identify with a religion. Even today, scientists who identify as religious are at greater risk of encountering resistance and mistrust in the workplace than are scientists who profess no religious affiliation. This robust study was conducted with a sample of 879 biologists and 903 physicists belonging to American research institutions as classified by the National Research Council. It found that 33.8% of biologists and physicists who identify as Roman Catholic say they have been subjected to more or less explicit discriminatory practices in the context of their labs or research teams, and 40.3% of researchers who identify as Protestant claim to have regularly felt pressured or even been sidelined in their work. The violent, dark story of the reception of the Big Bang Theory and the weakness of recent alternative theories only serve to underscore the strength of evidence for the expansion of the universe, its heat death, and its beginning. At this point in our argument, it is clear that the first two implications of materialist theory are both false. The universe did indeed have a beginning, and it will end. But a creator God's non-existence has a third implication, namely, that we should not expect the universe to be fine-tuned with conditions hospitable to the emergence of life. In the following pages, we will show that this third implication is also contradicted by reality. 9. The fine-tuning of the universe. You sit down at the breakfast table to read your favorite newspaper over a cup of coffee. As usual, there is plenty of bad news. Global temperatures are projected to climb another deadly degree or two over the next few years, accelerating the melting of the polar ice caps, raising sea levels, and causing climate disasters all over the world. On the next page, there is a worrisome report on just how fragile the thin layer of ozone protecting us from the deadly radiation of the sun has become. On the last page of today's issue, you find devastating statistics about how herbicides are decimating the bee population. If the bees disappear, then plants won't get pollinated, and most of the world's vegetation will go extinct. During your commute to work, you reflect on the extreme fragility and sensitivity of all these precisely regulated processes, each one so essential to our life on Earth. Isn't it incredible that our existence requires such a specific temperature, or that terrestrial life requires such a specific proportion of oxygen in the atmosphere with an ozone layer precisely this thick? With even a slightly lower percentage of oxygen in the atmosphere, life would be impossible, and at a slightly higher ratio, everything on the face of the Earth would burn up. Perhaps a number of other vital parameters come to mind, such as the Earth's protective magnetic field or the perfect inclination of its axis of rotation. All at once, the question occurs to you, could such precise fine-tuning be proof of the existence of a creator God? You might think that while it's true that the conditions necessary for life on Earth are very numerous and very precisely regulated, the observable universe probably has millions of billions of other planets. Isn't it statistically likely that some of these other planets have conditions just as precisely optimized for life as those of our planet? But what about the universe as a whole? Does its existence also depend on such precisely regulated conditions? That would be very interesting indeed. Since there is only one universe, maybe chance isn't such a satisfactory explanation. In fact, many great thinkers have asked the same question you have. If the Earth's fine-tunings surprise you, the fine-tuning of the universe will blow you away. To dive into the fantastic fine-tuning that made possible the evolution of the universe and eventual emergence of life is to discover that chance is not a credible explanation. This revolutionary new realization underlies what is known as the problem of the fine-tuning of the universe. I cannot imagine how the clockwork of the universe can exist without a clockmaker. Voltaire is thought to have said these words in the 18th century, when scientific understanding about the world and its origin was still embryonic. Extraordinary discoveries over the past few decades have sharpened our understanding of cosmic evolution, making his analogy of the clockmaker even more timely. The universe now looks like a big setup, an incredibly precise piece of machinery whose every part shows stunning fine-tunings of design, complex cogs that mesh together miraculously, creating the conditions necessary for the existence and functioning of the whole. Someone who takes only a quick glance at his watch may feel no wonder at how perfectly its hands turn and mark the hour. But if he cares to open the case to inspect the mechanisms and complicated machinery that make up this delicate instrument, then the evidence stares him right in the face. The watch must have had an intelligent designer. In this chapter, join us as we pry open the case of the massive watch that is the universe to marvel at the delicate fine-tuning that keeps it running. Our inspection will reveal how the initial data and physical constants that have regulated the universe since its origin are unlikely, ultra-precise, and extremely sensitive. In the words of George Smoot, 2006 Nobel laureate in physics, the Big Bang, the most cataclysmic event we can imagine, on closer inspection appears finely orchestrated. What is fine-tuning? The origin, evolution, and continued functioning of the universe depend on around 20 parameters or constants. The values of these numbers were fixed at the moment the universe came into being and are invariable in time and space. Here are the main ones. The force of gravity, defined by the constant uppercase G equals 6.67418 times 10 to the minus 11 cubic meters per kilogram per second squared, with a coupling constant alpha lowercase g equals 10 to the minus 39th power. The electromagnetic force, defined by the fine structure constant alpha equals 0.0072973525376. The strong force or strong interaction, which assures the cohesion of atomic nuclei and of nucleons, defined by the coupling constant alpha S equals 1. The weak force or weak interaction within the atomic nucleus, defined by the coupling constant alpha W equals 10 to the minus 6th power. The speed of light, c equals 299,792,458 meters per second. The Planck constant, h equals 6.626070040 times 10 to the minus 34 joule seconds. the Boltzmann constant. K equals 1.380649 times 10 to the minus 23 joules per Kelvin. The charge of the proton plus and the electron minus. E equals 1.6021766,208 times 10 to the minus 19th coulombs. The mass of the proton, 1.6726219 times 10 to the minus 27 kilograms, or 0.14% greater than the mass of the proton. The mass of the electron, 9.10938,356 times 10 to the minus 31 kilograms. The mass energy density of the universe at its origin. The velocity of expansion of the universe at its origin. The cosmological constant that contributes to the acceleration of the universe. 1.289 times 10 to the minus 52 meters squared, or 1.38 times 10 to the minus 122 Planck units squared. The density and mass of the universe just after the Big Bang. The speed of expansion of the universe just after the Big Bang. Where do these numbers come from? What is their purpose? What would the universe have been like if they had been even slightly different? 3 questions, 3 answers. Where do these numbers come from? There are only 2 possible responses. Either they are the result of chance, or they proceed from the complex calculations of a highly intelligent creator God. What do they do? The laws, constants, and initial conditions that these numbers describe shape every aspect of the material universe, including its evolution, from the very beginning. What would the universe have been like if they had been even slightly different? As surprising as it might sound, we can actually answer this question. For some of these numbers, a very slight variation by even a distant decimal point would have yielded an unrecognizable universe, and we would not be here to talk about it. This is the essence of the fine-tuning principle. We should note in passing just what fantastic scientific progress we have made. Today, when we ask such crazy questions, we can expect to get good answers. With the help of powerful computers, scientists have been able to mathematically model the universe and say what would happen if certain parameters had been different. If, for example, the 20th decimal place of the initial density of the universe were changed. Let's take the force of gravitation as a familiar example. This force acts between the masses of every object in our universe according to the formula discovered by Newton, F equals uppercase G m1 m2 over d squared. Its value depends on the value of the constant g, which we can measure up to the 4th decimal. G equals 6.6743 times 10 to the minus 11 cubic meters per kilogram per second squared. But why does g have this exact value? Its value cannot be explained by any existing theory, the astronomer Jacques Desmarais declares. Like all the other constants we have seen, it has an arbitrary and inexplicable value. Further, the force of gravity is fine-tuned to 1 part in 10 to the 35th of a range extending from an upper value set as the strength of the strong nuclear force, the strongest of the forces, to a lower range of 0. If its ratio with the strong nuclear force were not close to 10 to the 39th, all life in the universe would be impossible. The same holds for the 20 or so other constants that form the structure of the universe, which are also incredibly fine-tuned, as we shall see. This astonishing fact, verified by numerous computer modelings, is universally recognized today. The fine-tuning, to use Fred Hoyle's 1953 coinage, of the initial data, laws, constants, and structures of the universe is an inescapable fact that practically no one contests today, as it is recognized by the greatest thinkers, often themselves agnostic, whose opinion therefore holds particular value. Lee Smolin, a materialist physicist, recognizes this strangeness and is just as astonished as everyone else. we must understand how it came to be that the parameters that govern the elementary particles and their interactions are tuned and balanced in such a way that a universe of such variety and complexity arises. We should ask just how probable it is that a universe created by randomly choosing the parameters will contain stars. The answer, in round numbers, comes to about 1 chance in 10 to the 229th. Richard Feynman, 1965 Nobel laureate in physics, adds, "We use the numbers in all our theories, but we don't understand them, what they are, or where they come from." Physicist Paul Davies, professor at Arizona State University, likewise confesses his discomfort. "I belong to the group of scientists who do not subscribe to a conventional religion, but nevertheless deny that the universe is a purposeless accident. The physical universe is put together with an ingenuity so astonishing that I cannot accept it merely as a brute fact. There must, it seems to me, be a deeper level of explanation. Whether one wishes to call that deeper level God is a matter of taste and definition." Paul Dirac makes a similar argument at a conference in 1971. "If physical laws are such that, to start off, life involves an excessively small chance, so that it will not be reasonable to suppose that life would have started just by blind chance, then there must be a God." The celebrated American astronomer Alan Sandage, winner of the prestigious Crawford Prize in Astronomy, enters the fray with the following consideration. In the final analysis, he tells us, the mysterious tuning of the universe leaves us no choice. "I find it quite improbable that such order came out of chaos. There has to be some organizing principle. God, to me, is a mystery, but is the explanation for the miracle of existence, why there is something instead of nothing." At the risk of upsetting his materialist colleagues, Steven Weinberg affirms, "Life as we know it would be impossible if any one of several physical quantities had slightly different values." Arno Penzias, winner of the 1978 Nobel Prize in Physics, writes, "Astronomy leads us to a unique event, a universe which was created out of nothing, one with a very delicate balance needed to provide exactly the conditions required to permit life, and one which has an underlying, one might say supernatural, plan." Fred Hoyle, English astronomer who coined the term Big Bang, and who was a contemporary of Robert Dicke, had already concluded at that time that a common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. The numbers that we calculate from the facts seem to me overwhelming enough to make this conclusion almost indubitable. He also summed up his position in a blurb from the magazine Nature. "The chance that higher life forms might have emerged in this way is comparable with the chance that a tornado sweeping through a junkyard might assemble a Boeing 747 from the materials therein." John Lennox, professor of mathematics at Oxford, explains, "The fundamental constants that govern what the universe is like have to be within very, very finely defined limits in order to have a universe like we have, in which carbon-based life is possible, and we call that the fine-tuning of the universe. For example, the ratio of the electromagnetic force to gravity in the early universe has to be accurate to about 1/10 to the 40th in order that we can have the chemistry of the universe as we now see it. Now, 1/10 to the 40th, to get some idea of that, let's imagine that we covered, say, the whole of Russia with small coins, and we built the piles of coins over the whole of Russia to the height of the moon, and then we took 1 billion systems like that, and we painted one of the coins red, and we asked you to blindfold a friend and go and find it. They'd have about 1/10 to the 40th of finding it, so it's a very small probability." Similarly, Max Planck, the legendary founder of the science of the infinitely small that is quantum mechanics, affirmed, "All matter originates and exists only by virtue of a force which brings the particles of an atom to vibration and holds this most minute solar system of the atom together. We must assume behind this force the existence of a conscious and intelligent mind." Freeman Dyson, physics professor at Princeton, admits, "The more I examine the universe and the details of its architecture, the more evidence I find that the universe in some sense must have known we were coming. Cosmic fine-tuning is thus a centerpiece of our panorama of proofs for the existence of a creator God. There exists no reasonable materialist response to the extreme improbability of the universe's structure and functioning. We will first review the history that led to this discovery before describing in detail the astonishing improbabilities that mark the various stages of the development of our universe. 1. The story of the discovery of the anthropic principle. John D. Barrow, professor of mathematics at Cambridge and expert on the anthropic principle, wrote the standard reference work on the subject in 1988 together with Frank Tipler. Entitled The Anthropic Cosmological Principle, this extraordinary 600-page tome details 200 examples of fine-tuning. In the book's introduction, Barrow and Tipler insist that the last few decades have witnessed the most impressive discoveries about the universe ever made. Although the concept of the anthropic principle was not officially proposed until the 1970s by Australian physicist Brandon Carter, the emergence of this new proof for God's existence took almost a century. It all began at the legendary Princeton University toward the end of the 1930s. There, young physicist Robert Dicke first conceived the idea of incredible settings in our universe that led inevitably to the birth and evolution of life. At a series of talks in 1937, Dicke heard the great Paul Dirac, 1931 Nobel laureate, speak about certain strange coincidences between the great physical constants upon which the universe is based. For example, the ratios of the cosmic ray to the proton ray and that of the force of gravity to the electromagnetic force are close to 10 to the power of 40. In that same year, Dicke had the opportunity to meet Einstein, who had been a professor at Princeton since 1933. On this question, the theorist of relativity already held a clear position. God does not play dice. Chance does not rule the world. As the years went by and these speculations continued to swirl in his mind, Dicke kept coming back to the same question: what role does chance play in the universe? This and similar thoughts would irresistibly lead Dicke to discover one of the most astounding principles in physics, even if he did not himself name it, the anthropic principle. In the 1960s, Dicke's reputation at Princeton was on the rise. He sounded the depths of the universe with radio-astronomical tools of his own invention. He had carefully read George Gamoff's works on the hot Big Bang and the traces this primordial explosion had left in space. With the help of his student James Peebles and his colleagues Roll and Wilkinson, he made the first precise predictions regarding the existence of fossil radiation, which was ultimately detected in 1964 by Robert Wilson and Arno Penzias only a few miles from Princeton. Peebles would go on to win the 2019 Nobel Prize for revisiting and refining Gamoff's calculations of this fantastic discovery, which Stephen Hawking considered to be the most important of all time. While still in the thick of his research into the very first instance of the universe, Dicke spent his spare time cataloging a host of bizarre observations. In the first place, he was intrigued by the fact that the universe's age, about 14 billion years, is not a matter of chance. Why? Because the fundamental physical laws observed from the Earth link the lifespan of the Sun to the evolution of intelligent life. Dicke and several of his more audacious colleagues became convinced that the evolution of intelligent life had required the universe to be at least as old as it is today. 1 year later, Dicke took another step. This time he spoke out more vocally and to a wider audience, claiming that Fred Hoyle's witty remark that the universe is a big setup had more to it than met the eye. He threw himself into his calculations. After a series of complicated equations, he concluded that the initial conditions at the moment of the Big Bang were tailored with dizzying precision and that our existence is something of a miracle. Naturally, his colleagues were somewhat unsettled by his conclusions. Many turned their backs on him. But the facts were there in the equations. Even the tiniest variation in a single one of the numerous cosmological parameters at the basis of the universe, a 2 instead of a 3 in the nth decimal place of a number, and neither space-time nor life as we know it would ever have emerged. For Dickey, the case was closed, and he never changed his mind. The universe is not a result of chance. Subsequently, a number of researchers and scientists would observe the same fact. The fine-tuning of the initial conditions, laws, forces, constants, and structures that make up our universe are very finely adjusted, sometimes with breathtaking precision, and if this were not the case, we would not be here to speak of it. 2. What are these mysterious fine-tunings? It is time to look into the details of the recent scientific discoveries that reveal this incredible adjustment of the initial data, constants, structures, and laws of our world. We will present a dozen examples following the same stages of the development of our universe that we did in Chapter 5 on the Big Bang. 1. In the beginning, the coupling constants that determined the relationships between the four fundamental interactions were very precisely fixed. Most scientists believe that at the beginning of time, that is, at the moment of the Big Bang, the four fundamental forces that shape our reality were united as one. After 10 to the minus 43rd seconds, which is, given our understanding of physics, the smallest conceptually useful unit of time, 0.000000000000000000000001 seconds, our universe had, according to the standard model of the Big Bang, a radius of 10 to the minus 33 centimeters, in other words, billions of times smaller than a hydrogen atom. In that instant, its temperature was unimaginably hot, 10 to the 32nd degrees, or 100,000 billion degrees. Its energy was just as precise and immense, 10 to the 19th giga-electron volts, GeV. But the most extraordinary thing is that in that primordial epoch, where neither matter nor any structure or element existed yet, everything was already fantastically ordered and calibrated. Two of them, the strong and weak forces, act on the extremely small at the scale of elementary particles. The other two, the electromagnetic and gravitational forces, produce significant large-scale forces, like those between bodies as great as stars. These four forces sustain all life's processes at the most profound level. The strong force, for example, keeps the atoms of your body from scattering into a cloud of elementary particles. At the other extreme, the electromagnetic force is constantly at work in the depths of your brain, producing your thoughts and transmitting them from one neuron to another. The same phenomenon takes place in your muscles, in your heart, for example, whose pace is regulated by electric pulses. In sum, you can think and walk thanks to a force that came into being at the instant of the Big Bang 13.8 billion years ago. Now here is where things get interesting. These four forces that underpin everything you see around you, and also the entirety of the universe, are themselves based on numbers. More precisely, these are pure and dimensionless numbers. Physicists call them coupling constants. These numbers are called pure because, as the relative ratio of the four different interactions, they hold true independently of any unit of measure, and their value can only be discovered through measuring devices. What exactly are our four fundamental forces and the numbers attached to them? Where do their respective values come from? It's a mystery. Their incredible fine-tuning still seems to be the result of a miracle. If the strong force has a value of 1, the electromagnetic force is 137 times weaker. Then comes the weak force, 0.000001, a million times weaker than its cousin, the strong force. Finally, gravity plunges into an abyss, 1,000 billion times weaker than the strong nuclear force. How can we explain this incredible but highly precise fall of exactly 39 orders of magnitude rather than 43 or 35? Why have these constants maintained these same values since the birth of the universe rather than some other value? Where do they come from? No matter how hard we look, it is impossible to find answers, so much so that in the final analysis, as the Nobel laureate Richard Feynman remarked regarding the value of the pure number that is the basis for the electromagnetic force, "It is one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil." At any rate, the extent and precision of this calibration is dizzying. The same holds for the other three pure numbers that correspond to the other three great forces of the universe. Seized by the same emotion, the great theoretical physicist Dirac went beyond his militant atheism when he said in a 1963 issue of Scientific American, something that soon became well known internationally. One could perhaps describe the situation by saying that God is a mathematician of a very high order, and he used very advanced mathematics in constructing the universe. His observation is essentially very simple. If these four pure numbers that regulate the destiny of the four elemental forces of the universe did not fall within a very narrow range, nothing we know would exist. Not the book you hold in your hands, nor the flowers in your garden, nor your dog or cat, not even our world. And the universe as a whole would have generated only the lightest elements like helium and hydrogen. None of the heavy elements capable of supporting life or complex chemistry could ever have been formed. To conclude, notice that all the constants, all the cosmological parameters mentioned above, are said to flow from the breaking of the primordial unity between the four forces at the instant of the Big Bang. 2. In the first instant after the Big Bang, the ratio between the amount of energy in the universe and its rate of expansion had to be fixed with phenomenal precision. At the instant of the Big Bang, the universe already had a fixed quantity of energy and a precise, unchanging rate of expansion. Now, the ratio between the two is extremely important because if the universe's expansion had been even slightly weaker at that moment, the newborn cosmos would have collapsed in upon itself under the force of gravitation well before it could reach its current size. Inversely, if the initial expansion had been even a bit more rapid, the stars would not have had time to form, and the universe would now be composed entirely of gases. Bob Dickey told us that if you thought about the universe at 1 second after the beginning, the expansion rate really had to be just right to 15 decimal places, or else the universe would either fly apart too fast for any structure to form, or recollapse too fast for any structure to form, explains the famous cosmologist Alan Guth, professor of physics at MIT and one of the fathers of inflation theory. In addition, in order for the universe to permit the generation of atoms, the stars, and complex life, first, according to the classical model, the initial density of the universe had to be set within a very narrow range, tuned with a remarkable precision that we are now able to calculate. 1 nanosecond, a billionth of a second, after the Big Bang, this relationship between the average density and the critical density of the universe must have only differed from 1 to the 24th decimal place, that is, 1.0000000000000000000001, as reported by Geraint Lewis and Luke Barnes. In the Planck era, 10 to the minus 43rd seconds after the Big Bang, this value must have been even closer to 1 and is written as 1.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 This negligible deviation from 1 only appears at the 60th decimal. Shocked by such an incredible result, George Smoot could not refrain from bringing this to the attention of his most skeptical colleagues. That is so close to one that reasonable people think it is not simply a matter of chance. Something requires that omega is 1 to all those decimal places. The Buddhist cosmologist Jin Sun Tuan also demonstrated that in order to explain the flatness or absence of curvature of the universe, the mass density had to be fixed with a precision of the order of 1 over 10 to the 60th. We might compare the improbability of this to the accuracy that would be required for an archer to be able to hit a 1 square centimeter target 15 billion light years away. In other words, the probability is near zero. Alan Guth conceived of the moment of cosmic inflation, see point 6 in Chapter 6, as a solution to this enigma of the calibration of the flatness of the universe, as well as other important questions faced by physicists: the absence of magnetic monopoles, the homogeneity of the universe affirmed after 380,000 years, the order of greatness of distances between the star clusters of galaxies. Today, this solution is favored by the majority of cosmologists, though it has not yet been confirmed through experimental research. If confirmed, it would still require the extremely precise calibration of the sequence of events that from these first moments allowed for the emergence of a universe favorable to life. Let's be clear. This fact alone would justify calling the emergence of the universe a miracle rather than mere chance. But there is more. 3. The fine-tuning of the weak force allows antimatter to disappear. At the very beginning of the universe, matter and antimatter were created in equal parts. What differentiates matter from antimatter is their respective charge. An electron has a charge of negative E, an antielectron a charge of positive E. These entities canceled each other out and produced energy in the form of radiation. If the initial ratio of matter and antimatter had been conserved, there would have been total destruction, colossal explosions of energy leaving nothing in the universe but radiation. The universe would have been sterile and devoid of matter. Why isn't this what happened? This question went unanswered for a long time, since matter and antimatter seemed to behave symmetrically during interactions. However, an initial clue appeared one day in 1964 amidst research on the disintegrations of particles called kaons, the discovery of a violation of this symmetry called CP violation. But this effect was too small to explain by itself the quasi-disappearance of antimatter. Recently, a new avenue of research has opened up, resulting in an article published in Nature, May 15, 2020, devoted to this question. The article focuses on the oscillations of neutrinos. Neutrinos or antineutrinos are emitted during the weak interaction, as is the case for the radioactive beta. It had long been believed that these particles had no mass, but then it was observed that they didn't have zero mass, but rather a minute mass that allowed for a phenomenon called oscillation. This discovery earned the Nobel Prize 2015 for Takaaki Kajita and Arthur B. MacDonald. This phenomenon provided the conditions for the asymmetry between matter and antimatter. Admittedly, these very recent experiments still have yet to be refined and confirmed. However, we note that these avenues of research have to do with extremely fine phenomena: CP violation of quarks, the minuscule mass of neutrinos, the oscillations of flavor. In theory, all of particle physics would be able to function without them, yet they appear to contribute to the asymmetry of matter and antimatter. There could, however, be another explanation. If true, this explanation would entail phenomena so infinitesimal that they have not yet been discovered, even though particle physics has been capable of detecting incredibly precise phenomena to the order of 10 to the minus 11th for 60 years. It is stupefying that such an essential phenomenon to our existence as the disappearance of antimatter would find its source in causes so obscure that they have evaded the grasp of particle physicists for 60 years. This is another example of hyper-fine tuning, one which turns out to be absolutely essential. 4. The masses of the fundamental structures of the universe, electrons, protons, neutrons, are also adjusted to perfection. From 10 to the minus 6th to 10 to the minus 4th seconds, Quarks, which had just formed a few moments earlier along with neutrinos and electrons, combined to form protons and neutrons. What caused these structures to appear? In short, the laws of the universe caused their emergence, but those laws had to be minutely adjusted to do so. In fact, in 2015, a dizzying discovery showed that the mass of a proton, 938.27 MeV, is nearly identical to the mass of a neutron, 939.57 MeV, a mere 0.14% lighter. If this minuscule gap had been even slightly different, no life or even complex chemistry would exist, and therefore we would not be here. Fortunately, the neutron is slightly more massive than the proton, and this allows a free neutron to decay rapidly into a proton while the proton itself remains stable. If the reverse were true, protons would decay into stable neutrons, fusion reactions would be based on neutrons, and the only matter in the universe would be neutronium. The chemical elements would never form, and no life would be possible. These and numerous other instances of fine-tuning prompted the famous English materialist Stephen Hawking to observe, "The laws of science as we know them at present contain many fundamental numbers, like the size of the electric charge of the electron and the ratio of the masses of the proton and the electron. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life." Already, at this early stage of the universe's development, we are surrounded by remarkable fine-tunings. Each one is stupefying enough in itself. But that's not all. 5. Keeping the highly unstable neutron going, another essential fine-tuning. Between 10 to the -6th and 10 to the -4th seconds, quarks combine to form protons and neutrons. Here again we encounter numbers that defy comprehension. A proton's lifespan could be 10 to the 34th years, 10 million billion 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 years, while a free neutron sitting right beside it dies after only a brief 15 minutes. Therefore, after the Big Bang, the neutron had only 15 minutes, exactly 878 seconds, to group together with the proton in the first atomic nuclei during the very brief period of first nucleosynthesis. At the end of this short hadron epoch, further creation of protons and neutrons became impossible. So what keeps these unstable neutrons in existence? Again, the answer is the velocity of the expansion of the universe. Since the proton-neutron structure cannot survive above a certain temperature, the universe has to expand at a rate rapid enough to diminish its average energy density, thereby quickly lowering the temperature. Otherwise, all neutrons would disappear. Scientists estimate that the fine-tuning allowed hydrogen to predominate. With this regulation of the expansion, only 1 neutron in 7 is preserved, allowing the universe to be open to life. If the expansion were a little slower, all neutrons would have disappeared, preventing the formation of heavier atoms, and if it had been a little faster, all protons would have bonded with neutrons, which would have been produced in equal numbers, to create helium nuclei, and there would have been no hydrogen needed for the stars to exist. In sum, without this unbelievably well-calibrated adjustment, we would not be here speaking about it. 6. The cosmological constant, one of the finest of fine-tunings. The cosmological constant that Einstein added to his relativity equations in order to maintain the stability of the universe, but later recognized as the greatest mistake of his life after observing the expansion of the universe, see Chapter 5, seems to exist after all, but it is very tiny. And this is where things get truly amazing. In calculating the value of this notorious constant, the positive contributions estimated from the Standard Model of particle physics and the negative contribution of the so-called naked cosmological constant cancel each other out to the 122nd decimal place, matching the value that it's possible to physically measure. In other words, after the decimal point come 122 zeros, and the first non-zero appears in the 123rd place. In a 2012 TED Talk, Brian Greene projected an image of the number included in the bonus PDF. He commented, This number is small. Expressed in the relevant units, it is spectacularly small. And the mystery is to explain this peculiar number. We want this number to emerge from the laws of physics, but so far no one has found a way to do that. To put it another way, the constant contributing to our universe's expansion had an extraordinarily slim chance, 1 in a billion 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 of achieving precisely the right value. So we are faced once again with an extremely measured and precise calibration. Ultra-low in value, the cosmological constant corresponds to a very small vacuum energy that acts as a repulsive force against gravity and produces the acceleration of the expansion of the universe observed today. If the value had been slightly larger, the universe would have expanded too rapidly for stars and galaxies to form, making the emergence of any form of life impossible. Conversely, if the value had been slightly smaller, the cosmos would have collapsed in on itself long ago. Leonard Susskind, professor of physics at Stanford and highly reputed materialist cosmologist, expresses his astonishment. Most fine-tunings are 1% sorts of things. In other words, if the thing is 1% different, everything is bad, and the physicist could say, maybe those are just luck. On the other hand, this cosmological constant is tuned to 1 part in 10 to the 120th power, 1 over 10 to the 120th. Nobody thinks that's accidental. That's the most extreme example of fine-tuning. Confronted with such precise and delicate tuning, even prominent atheist cosmologists have started to refer to it as a miracle. Atheist Stephen Hawking used the word explicitly. The most impressive fine-tuning coincidence involves the so-called cosmological constant. Physicists have created arguments explaining how it might arise due to quantum mechanical effects, but the value they calculate is about 120 orders of magnitude, a 1 followed by 120 zeros, stronger than the actual value obtained through the supernova observations. That means that either the reasoning employed in the calculation was wrong, or else some other effect exists that miraculously cancels all but an unimaginably tiny fraction of the number calculated. Larry Abbott, professor at Brandeis and another atheist cosmologist, declared, "There must in fact be a miraculous conspiracy occurring among both the known and the unknown parameters governing particle physics. The small value of the cosmological constant is telling us that a remarkably precise and totally unexpected relationship exists among all the parameters of the Standard Model, the bare cosmological constant, and unknown physics." Robert Laughlin, professor of physics at Stanford, 1998 Nobel laureate and an atheist, claimed, "The fact that it is so small tells us that gravity and the relativistic matter pervading the universe are fundamentally related in some mysterious way that is not yet understood, since the alternative would require a stupendous miracle." Alexander Vilenkin, the openly materialist director of the Tufts Institute of Cosmology, is equally fascinated. The cosmological constant problem is one of the most intriguing mysteries that we are now facing in theoretical physics. The precision of the tuning behind the cosmological constant is jaw-dropping. But there is still more. 7. The tuning of the strong and weak nuclear forces is equally astonishing and indispensable. Between 1 second and 15 minutes after the Big Bang, the nuclear synthesis of all the light elements took place once and for all. Hydrogen, 92% of the matter in today's universe, helium, 8%, and deuterium, which could only be created in the extreme conditions present during the first minutes of the Big Bang, and a small quantity of lithium, beryllium, and boron. The synthesis of the first atomic nuclei was possible thanks to the strong nuclear force, a short-range interaction 1,000 billion 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 times greater than the force of gravity. The weak force also had to be precisely set to allow life. Stephen Hawking explains, "For example, if the other nuclear force, the weak force, were much weaker, in the early universe all the hydrogen in the cosmos would have turned to helium, and hence there would be no normal stars. If it were much stronger, exploding supernovas would not eject their outer envelopes, and hence would fail to seed interstellar space with the heavy elements planets require to foster life. Incredible, isn't it? If you thought that there couldn't be any more surprises in store, you'd be wrong. There is yet another reason to be amazed at the universe's mysterious tuning at the moment of its emergence, a tuning some scientists don't hesitate to call supernatural. 8. The tremendous conservation of beryllium, which enables the generation of the carbon essential for life. The conditions behind the generation of carbon at the heart of stars are even more impressive. To understand these conditions, let's look at the conclusion drawn by Nobel Prize-winning physicist Steven Weinberg, an avowed agnostic, in his 1992 bestseller, Dreams of a Final Theory. His book came like an electric shock, igniting a furious debate among the scientific community. One of the phenomena he presented was simply beyond our power of comprehension. All the fuss was over the strange behavior of beryllium-8. The most common isotope of carbon, carbon-12, forms within stars in a two-step process. First, two helium nuclei collide and combine to form the highly unstable isotope beryllium-8, which has a half-life of 0.000000000000001 seconds. If beryllium-8 does not absorb another helium nucleus within this incredibly short time frame, it decays and becomes unavailable for carbon formation. Fred Hoyle was the first to understand this, but by the 1950s he had also seen that this interaction is only possible in the context of an excited state of carbon at a very precise energy level, 7.65 MeV, at that time unknown. So Hoyle, in 1954, predicted that this excited state of carbon must exist, since without it life would not exist. Later, he managed to convince an initially skeptical Willie Fowler, nuclear physicist at Caltech, to carry out the necessary testing, which confirmed that the excited state of carbon with the precise and highly improbable energy level and resonance predicted did in fact exist. Militant atheist Hoyle was so impressed by this that he ended his life a deist. As early as 1957, he spoke out about his discovery of this providential phenomenon at the risk of falling out with his colleagues at the very progressive University of Cambridge. I do not believe that any scientist who examined the evidence would fail to draw the inference that the laws of nuclear physics have been deliberately designed with regard to the consequences they produce inside the stars. An affirmation that, once again, leaves no place for chance. As Steven Weinberg points out along the same lines, if the energy of this state of the carbon nucleus were too large or too small, then little carbon or heavier elements would be formed in stars, and with only hydrogen and helium there would be no way that life could arise. And without it, the heaviest elements in the periodic table, that is, elements which formed between 3 and 5 billion years later in the explosion of the first-generation stars that became supernovas, would not exist either. 9. The magical adjustment of the electromagnetic force has also astounded the greatest scholars. During the first 380,000 years that followed the initial 15 minutes of its existence, the universe continued its rapid expansion, dominated by the agitation of highly energized photons coupled to ionized matter. These photons were like prisoners, incapable of striking out on their own because of the high temperature. But at the end of this period, electrons began to associate with existing nuclei. As a result, matter became electrically neutral and radiation decoupled from matter, allowing the emission and propagation of the first light over long distances and the emergence of the visible universe. This association of electrons to atomic nuclei was made possible by the electromagnetic force, which is 137 times smaller than the strong force. The electromagnetic force is determined and governed by the fine structure constant introduced in 1916 by the German physicist Arnold Sommerfeld, close friend of Einstein and the academic mentor to Nobel laureates Wolfgang Pauli and Werner Heisenberg. Why does the fine structure constant have the exact value of 0.00729735253776? Nobody knows. What we do know is that if the constant changed by a few percent, life could not exist in the universe. As already mentioned, this phenomenon haunted the German physicist Max Born, the 1954 Nobel laureate in physics and quantum mechanics superstar. If alpha, the fine structure constant, were bigger than it really is, we should not be able to distinguish matter from ether, the vacuum, nothingness, and our task to disentangle the natural laws would be hopelessly difficult. The fact, however, that alpha has just its value, 1 over 137, is certainly no chance but itself a law of nature. It is clear that the explanation of this number must be the central problem of natural philosophy. We saw earlier how the Nobel laureate Richard Feynman was fascinated by this mysterious constant that seems to arise from nowhere. The constant has been a mystery ever since it was discovered more than 50 years ago, and all good theoretical physicists put this number up on their wall and worry about it. 10. Cosmic microwave background anisotropy is also fine-tuned. 380,000 years after the Big Bang, the liberation of the first visible light produced what we now call cosmic microwave background radiation, CMBR, in near-perfect thermal equilibrium at 3,000 Kelvin. That's about the temperature of the surface of our Sun. But CMBR is not completely uniform. In 1992, tiny variations called anisotropy were detected in it by George Smoot and John Mather. The term anisotropy refers to the fact that the echo of this primordial radiation of the universe is not perfectly homogeneous. Although the magnitude may seem insignificant, only some 10,000ths of a degree, these irregularities were indispensable for the future evolution of the universe into stars and galaxies. Computer simulations show that if the temperature variation 380,000 years after the Big Bang had been slightly greater, our universe could have transformed into a giant field of black holes. On the other hand, if the anisotropy had been slightly less, then instead of shaping the Earth, planets, and stars, the universe would have become a formless cloud of gas. When the astronomical satellite WMAP was launched in 2001 to succeed the device sent up by Smoot and Mather, David Wilkinson, Dickey's former collaborator at Princeton, confidently exclaimed, "I am confident that our probe will soon confirm that nothing in the universe has been left to chance." Brilliant mathematician Steve Carlip from the University of California has arrived at the same conviction and expresses his views very openly. After analyzing the temperature differences between the hot points, in red in the baby picture of the universe taken by satellites, and the cold regions in blue, the mathematician drew this strong conclusion. When the universe was very young and very hot, the ordinary matter was almost entirely a plasma of ionized hydrogen. The small perturbations in the density of this plasma propagated as what were essentially sound waves, with speeds that can be predicted accurately from ordinary laboratory physics. This resulted in correlations of the density at predictable distances. Professor Carlip continues with enthusiasm. In particular, the angular correlation power spectrum, the measure of the relationship between the temperature fluctuations at different angles, is a rather complicated curve which nevertheless agrees exquisitely with theory. The plasma was denser at crests of sound waves and less dense at troughs, and these show up in the measured CMB temperature. Even more striking, Roger Penrose, winner of the 2020 Nobel Prize in Physics, has found that the observed entropy of the universe is extremely improbable compared to all the values it could have had. He found 10 to the 10th power of 101 mass-energy configurations that correspond to an ordered universe like ours. But he also showed that there are even more configurations, 10 to the 10th power of 123, which generate universes dominated by black holes. Since 10 to the 10th power of 101 is only a tiny fraction of 10 to the 10th power of 123, Penrose concluded that the conditions which could give rise to a universe favorable to life are extremely rare in comparison with the total number of possible configurations that might have existed at the beginning of the universe. Dividing 10 to the 10th power of 101 by 10 to the 10th power of 123 always yields 10 to the 10th power of 123. And so the hyper-exponential number calculated by Penrose, 1 out of 10 to the 10th power of 123, provides a quantitative measure of the fine-tuning of the initial conditions of the universe. As Paul Davies observed, The really amazing thing is not that life on Earth is balanced on a knife edge, but that the entire universe is balanced on a knife edge and would be total chaos if any of the natural constants were off even slightly. What an understatement. After receiving the 2006 Nobel Prize for his striking pictures of the first light in the universe, George Smoot devoted his entire lecture to the theme, saying, "If you're religious, it's like looking at God. The order is so beautiful and the symmetry so beautiful that you think there is some design behind it. I saw the universe at its very beginning. I saw this anisotropy which allowed the universe to exist." Smoot and his team are reported as saying that they had pinpointed the oldest and largest cosmic structures yet known, the first anomalies in a seamless universal soup that signaled the beginning of galaxies. Smoot went on to explain that the Big Bang was not a disordered cataclysmic event at all, as we have mentioned, but rather a very carefully organized process consisting of a particular number of sequential events that unfold over the course of time. The evolution of the universe was written in its beginnings, in its cosmic DNA, if you will. But there's more. 11. The Planck constant, which universally regulates the energy levels of all atoms, deserves the nickname theological constant because, without it, all chemistry would be impossible. 380,000 years after the Big Bang, conditions became suitable for the formation of atoms. Miraculously, they arose with predetermined energy levels, exactly identical always and everywhere. Werner Heisenberg, one of the founders of quantum mechanics, was astonished as early as the 1920s by the stability of properties of bodies unexplainable through Newtonian mechanics. Only quite different natural laws can help us to explain why atoms should invariably rearrange themselves and move in such a way as to produce the same substances with the same stable properties. Had this not been the case, as many atoms would have arisen as there were initial states, depending on particular local conditions. In such a world, chemical reactions simply would not be able to take place. For a reaction to occur, elements have to be homogeneous and energetically compatible. Now, thanks to the Planck constant, all the atoms of each element have exactly the same energy level. This is the basis of quantum mechanics. If the laws of the universe had not been programmed this way, the world around us would not exist. Seeing that the Planck constant yields a universe whose structure permits chemistry, some have called it the theological constant, since it seems to be such an integral part of an intelligently designed plan engineered by God. Conclusion. These are only a handful of the most incredible fine-tunings that serve to illustrate the anthropic principle. The sum total of all these physical improbabilities is mathematical confirmation that the universe is not the result of chance. That a Creator God exists is the only obvious conclusion. This proof is, in our opinion, as strong as the evidence predicting the heat death of the universe and of cosmology as we know it. Let us not forget that these different proofs are perfectly independent of each other. All this strong evidence accords with the findings of many other researchers and scientists. It is directly based on the most cutting-edge discoveries in physics and leads to very clear and simple conclusions. But we can go just a little bit further with the help of American astronomer Robert Wilson, who won the 1978 Nobel Prize for his 1964 discovery of the first light in the universe. Certainly, if you are religious, I can't think of a better theory of the origin of the universe to match with Genesis. 10. The Multiverse, Theory or Loophole. The anthropic principle puts us up against a wall. We cannot escape the metaphysical questions raised by these extraordinarily precise fine-tunings. But where do they come from? Could someone be behind it all? There are really only two possible explanations: a creator God or pure chance. The probability that our universe arose as a result of chance alone has been estimated at least at 1 in 10 to the 60th. For such an unlikely event to occur, one would have to assume the existence of approximately 10 to the 60th independent universes, each governed by different physical laws. We can get some idea how big that number is by contemplating the fact that there are only 10 to the 23rd grains of sand in the Sahara. If we follow the calculations of string theory, we get an even greater figure, 10 to the 500th additional universes. This implies an extraordinary multitude of universes existing elsewhere, along with a universe-creating mechanism that we know nothing about, one with the inherent ability to vary the fundamental constants of these universes, selecting them from an appropriate range. As foolish and unverifiable as this hypothesis may seem, it has been surprisingly well studied. Once we exclude the possibility of a creator God, there remains no other rational response to the problem posed by the anthropic principle. Nevertheless, a number of alternative theories have appeared, whose main lines we will trace in this chapter. Hugh Everett and the many worlds interpretation. In 1954, Hugh Everett was discussing the paradoxes of quantum physics with a classmate at Princeton. In the course of the conversation, he threw out the hypothesis of multiple universes as a kind of joke, quipping that perhaps every time the wave function collapsed, a new world was born. He did serious work on this original solution to the problem of the superposition of quantum states, which became the subject of his thesis. In 1957, he published an article explaining the universe like a many-branched tree that creates new universes constantly, like a branch gives off new shoots. Although this unorthodox theory became a major source of inspiration for science fiction writers, it had no real impact on the scientific community. Eventually, Everett left academia and was recruited by the Pentagon to do military research. Alan Guth and the cosmic inflation theory. Alan Guth laid out his inflation theory in 1979 to explain why the universe is so flat and homogeneous. He postulated that the universe grew very rapidly at first, by a factor of 10 to the 26th or more in the tiny span of 10 to the minus 35th seconds, a rate that permitted it to smooth out naturally as it stretched, ensuring the extraordinary homogeneity observable today. This part of the theory was well received by the scientific community, but its further developments were much more speculative. Like the Russian researcher Andrei Linda, Alan Guth found it difficult to imagine that inflation was limited to the first moments of the life of the universe, and that we can plausibly suppose that an infinity of universes are continuously generated in a fractal pattern. The result has been dubbed a bubble universe, chaotic inflation theory. Guth imagined our universe as one among innumerable universes, each following its own set of physical laws, universes that never stop emerging, like champagne bubbles out of quantum fluctuations. According to Guth and Linda's multiverse theory, the fact that our particular universe has conditions favorable to the emergence of life is only a matter of chance. From the 2000s, we moved from the theory of inflation to an inflation of theories relating to the multiverse. More than 50 theories have been elaborated on the basis of Guth's hypothesis alone, not counting other versions. Some are entirely far-fetched, but many others continue to be studied today, like the highly speculative loop quantum gravity theory, or string theory, despite its increasing complexity and the growing doubts it raises among physicists. These theories fall into two types: those that conceive of multiverses in parallel dimensions that are entirely and forever inaccessible to us. Within this type we find theories that conceive of the universe as evolving in dimensions parallel to our space-time, theories that suppose that these parallel universes exist entirely beyond our space-time and have no connection to it. Those that imagine successive multiverses on the same timeline as our universe, difficult to access, but that we may one day be able to consider scientifically. Here, too, there are two subcategories: theories that conceive of bubble universes continuously emerging in an expanding space. They imagine our observable universe as just one bubble among a multitude of others, inaccessible to us and out of the reach of our universe, as they move away from us much faster than the speed of light. Theories postulating cyclic models that exist within our universe. No matter how many universes we imagine, an initial singularity, the Big Bang, remains necessary in all cases. In the late 20th century, Hawking and Penrose developed several singularity theorems. These prove that universes that meet certain minimum energy conditions must start from an initial spatial singularity, that is, a point where the volume of the universe approaches zero. Early mathematical models based on simplified scenarios, such as a universe with a uniform density throughout, suggested such a beginning, but many cosmologists expected that more factually accurate models would lead to different conclusions, allowing for a past and eternal universe to exist. As it turned out, Hawking and Penrose demonstrated that the standard cosmological model, even with its more realistic parameters, indicates that the universe began with a spatial singularity. However, Hawking and Penrose did not study inflationary models that generate bubble universes. Could these get us away from the necessity of a beginning? It turns out that the answer is no. In 2003, Alan Guth, Arvind Borde, and Alexander Vilenkin proved the absolute necessity of an initial singularity in time, a beginning of the universe, for all realistic cosmological models, including the inflationary model. Vilenkin said, "It is said that an argument is what convinces reasonable men, and a proof is what it takes to convince even an unreasonable man. With the proof now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. There is no escape. They have to face the problem of a cosmic beginning." In other words, multiverse theories do not solve the problem of how our universe began in the first place. No matter how many universes these theories put forward, the absolute beginning of the multiverse still demands an explanation. In other words, the multiverse theory might offer an explanation for the fine-tuning found in our world, but even the dizzying proliferation of universes does not resolve the problem of how our universe began in the first place. The multiverse as an escape mechanism. As with the previous chapter, this list of highly original explanations is impressive not only for its length, but also for how much work it takes to create and maintain these theories. The fine-tuning and the origin of the universe present significant challenges for materialist intellectuals. If they could discover reasonable scientific solutions to these issues, they would likely abandon these speculative theories, many of which are inherently unverifiable and sometimes resemble science fiction more than actual science. The remaining theories continuously seek hypothetical experimental evidence to support them. In the end, the various multiverse theories function as escape mechanisms that distract us from the real metaphysical questions at stake. Theories of everything in general and string theory in particular puzzled me more and more because they are tamper-proof. No experience can prove them wrong. I realized that people accept string theory for ideological reasons. It was a terrible shock to me because I thought that scientists refused any form of ideology. That's far from the case, explains Robert Laughlin, professor of physics at Stanford and 1998 Nobel laureate. 11. Preliminary conclusions. One small chapter for our book, one giant leap for our argument. The time has come to put to work the scientific method we explained in Chapter 2, What is Evidence? To prove a thesis, the scientific method begins with a hypothesis, the implications of which are then confirmed or disproved by what we observe in the real world. The thesis, there is no creator God, the world is purely material, generates the three logical consequences listed below. See Chapter 3. If the universe is exclusively material, then 1. The universe cannot have a beginning. 2. The universe cannot have an end like thermal death because such an end implies a beginning. 3. Deterministic laws are purely the result of chance, and therefore it is extremely unlikely that they would be favorable to life. People have known about these implications for as long as the thesis has been around, but they held little scientific interest for thinkers and researchers since it seemed like they would always remain far beyond human understanding. No one could ever have imagined that one day we might be able to test them. Against all expectations, these three implications have now come within the reach of science. Starting at the end of the 20th century, progress in physics, mathematics, technology, and more recently computing began to allow cosmologists to draw conclusions about these subjects. Today we know that the three propositions listed above are very difficult to sustain. This means that the thesis they flow from, there is no creator God, the universe is exclusively material, is equally problematic. A reasonable person must, therefore, adopt the opposite thesis: a creator God exists. A single valid proof is enough to disprove the hypothesis of a purely material universe. But cosmology allows us to establish two separate proofs. The universe had a beginning. This we know most notably from thermodynamics and the Borda-Guth-Vilenkin theorem, which is based on Hawking and Penrose's work on initial singularity. The laws of the universe are very favorable to human life, and the complex, minute fine-tuning of these physical laws is extremely improbable, as demonstrated by the anthropic principle. These undeniable truths contradict the implications that follow from the theory of a purely material universe. According to the rules of logic, a single one of these two proofs is enough to invalidate the theory. The two proofs are even stronger because they are totally independent of one another. Firstly and fundamentally, the fact that the universe had a beginning and that its structure and laws are improbable are two distinct facts with no relation between them. Furthermore, their results are not correlated because they were determined by independent methods. This double independence reinforces their value as proof because the falsity of one has no impact on the truth or falsity of the other. This significantly lowers the probability that the two are simultaneously false. The Big Bang greatly reinforces these two proofs. The discovery of the Big Bang is perfectly coherent with the reality that the universe had a beginning. It is the final, long-awaited missing puzzle piece in the theory. It fits perfectly, exactly where we'd expect it. Short on arguments, some detractors question it on grounds that are not even scientific. They say it is too similar to the Bible's creation account. Some major figures in science have pointed out this unfair move. British physicist George Thomson, who shared the 1937 Nobel Prize, probably every physicist would believe in a creation if the Bible had not unfortunately said something about it many years ago and made it seem old-fashioned. American physicist Robert Wilson, 1978 Nobel co-laureate in physics, as already mentioned in a preceding chapter, certainly if you are religious, I can't think of a better theory of the origin of the universe to match with Genesis. Arno Penzias, 1978 co-laureate in physics, the best data we have are exactly what I would have predicted had I nothing to go on but the 5 books of Moses, the Psalms, the Bible as a whole. Proof through slander and harassment. As we have seen, the attacks and harassment suffered by the supporters of a beginning to the universe and of its fine-tuning, two proofs that disprove the theory of an exclusively material universe, paradoxically give them even more legitimacy. If the two proofs were false, uncertain, or debatable, or if their consequences were not evident, then Gamow, Bronstein, Landau, Frederiks, Kozyrev, and many others would not have been attacked and persecuted, exiled, thrown into the gulag, or executed. Materialists would not have advocated for every conceivable alternative theory or invested excessive time in theories they label as speculative, which some of us, with less regard for their sentiments, refer to as science fiction. Remember, if Galileo was put under house arrest, it was because he was right. Violence begins when people run out of arguments. This violence against scientists serves as indirect evidence, particularly because it was perpetrated by intellectuals, politicians, and fellow scientists who were well equipped to evaluate both the validity of these new discoveries and the genuine threat they represented to their interests. These cosmological proofs are so recent that they aren't yet common knowledge. Keep in mind that this revolution in cosmology and its metaphysical implications is extremely recent. These proofs are not yet part of everyone's mental landscape, though they are slowly making headway. The confirmation of thermodynamics dates to the early 20th century. The Big Bang was confirmed in 1964. The anthropic principle was first formulated in 1973, and the confirmations are still rolling in. The Big Crunch was only disproved in 1998. In 2003, the Borda-Guth-Vilenkin theorem showed that the universe can't have an infinite past. There must have been an initial singularity. The thesis of a creator God on the edge of Occam's razor. In the 14th century, the erudite monk William of Ockham laid down the principle that when we're faced with two explanations, the simpler one is more likely to be true. This principle has become known as Occam's razor, and it is an important tool for scientists today. For many centuries, it has been used to argue that, because the hypothesis of God is not necessary, it should not be believed. But today, the same principle can be turned against materialists. The multiverse, the materialist's final trump card. Materialist thinkers today cling to the multiverse as their last hope. This theoretical construct certainly stretches the imagination, but it does not offer a solution to the problem of improbability posed by the fine-tuning of the universe. All the multiverse theories, in fact, require processes of universe creation which must themselves be extremely fine-tuned in order to generate multiple universes, some of which would be favorable to life. In other words, the challenge posed by improbability is simply transferred to the mechanisms that generate new universes without providing any ultimate explanation of their fine-tuning. Nor do these models provide any solution to the question of the beginning of the universe. The problem is simply shifted back to a mother universe about which we know nothing at all. But it is impossible to go back infinitely in time in this way, and so there must be an absolute beginning to all this, as the previously cited Borda-Guth-Vilenkin theorem also demonstrates. In short, the materialist multiverse hypothesis turns out to be purely speculative and completely powerless to counter the thesis of a creator God. Quotations on the subject. In his book The Secret Melody, Jin Soon Tuan remarks how, "For myself, I am prepared to bet on the existence of a supreme being. The hypothesis of a multiplicity of imaginary, unverifiable universes violates my sense of simplicity and economy." The multiverse hypothesis is alleged to be the last resort for the desperate atheist. Neil Manson, professor of philosophy at King's College, Cambridge. This multiverse view represents the failure of our grand agenda and seems to me contrary to the prescribed simplicity of Occam's razor, solving our lack of understanding by multiplying unseen entities into infinity. Gregory Benford, professor of physics and astronomy at the University of California, Irvine, specialist in space exploration. Even if the probability of finding a universe with a weak cosmological constant is very low, if we have an infinity of universes, it will happen somewhere. But is this a solution or a desperate explanation? George Efstathiou, professor of cosmology, director of the Cambridge Institute of Astronomy. Here is the cosmological proof of the existence of God, the design argument of Paley, updated and refurbished. The fine-tuning of the universe provides prima facie evidence of deistic design. Take your choice: blind chance that requires multitudes of universes, or design that requires only one. Many scientists, when they admit their views, incline toward the teleological or design argument. Edward Harrison, professor of astrophysics at the University of Amherst. A creator God is a much more simple and well-founded solution than the thesis of multiverses. A rational mind should favor it. It is simpler because if we have to choose between one creative being and a dizzying inflation of universes, the more rational choice is the one that limits unnecessary hypotheses. Let's remember that the multiverses belong only to the final group in our classification of evidence, Group 6, theories with no known or observable implications. On the other hand, the thesis of a creator God and its opposite are part of Group 5 and generate clear, logical, and numerous implications that we can compare with the real world. Is that the last word? We have now reached the end of the first part of our survey. Cosmology alone has provided us with sufficient evidence for the existence of a creator God. We could stop writing, and you could stop reading here. But it would be a shame to limit ourselves to a single angle of analysis. 12. Biology: the incredible leap from inert to living matter. Cosmological discoveries have allowed us to discredit the thesis of an entirely material universe, and recent advances in several other fields further confirm this conclusion. One such discovery, this time in the field of biology, is the incredible leap from inert to living matter. 1. A gap that ultimately turned out to be an abyss. Less than a century ago, what was thought to be a mere gap between inert and living matter was revealed to be a deep abyss. Modern biology has shed light on the incredible complexity of even the smallest living cell, which in fact bears a resemblance to an ultra-sophisticated factory. We now know that the transition to life was an extremely unlikely and complex event that took place over a relatively short span of time. Consequently, the thesis that life emerged by pure chance in a universe that was not specifically designed to be hospitable to it is no longer tenable. A biological fine-tuning is added to the cosmological fine-tuning. The only possible rational explanation for the natural appearance of life on our planet is that life resulted from laws of the universe that remain unknown to us, or at least from as yet unrecognized effects of finely tuned laws that prevailed at the time this leap occurred. That is to say, in addition to the cosmological fine-tuning of the universe, there is a second anthropic principle that applies to the emergence of life. Some established facts. Though no one knows exactly how life appeared on our planet, there are 3 facts about which we are absolutely certain. 1. The transition from inert matter to life as we know it must have happened because we are here now. 2. This occurred at least 3.8 billion years ago, less than 700 million years after the formation of the Earth. 3. This enormous leap required the coordination of a great number of extremely improbable factors. The likelihood of this has been calculated by scientists, and we will see later that the improbability is dizzying. Chance alone cannot explain the appearance of life. The goal of this chapter is to show that only the invisible hand of precisely regulated laws, or effects of the laws of nature that we still do not understand, could have guided this astonishing process. First, matter organized itself in an ever more elaborate way into quarks, atoms, molecules, and polymers, leading to the complex languages of RNA, DNA, and proteins which would allow the replicative, reproductive, and metabolic functions necessary for the emergence of life. All these functions came together to form the first unicellular living organisms. These, in the course of evolution, led to the earliest common ancestor of all terrestrial living beings, which scientists call LUCA, Last Universal Common Ancestor, a cellular system that was itself remarkably complex, characterized by a universal genetic code linking DNA-RNA to proteins, with a ribosome playing the role of translator. The fact that the laws of matter and energy are fine-tuned for life poses a major obstacle for the materialist, as the claims of materialism mean denying both that the universe was particularly favorable to the appearance of life and that this constitutes another strong argument for the existence of a creator God. How has our thinking about the appearance of life evolved over time? Since people in past centuries had little understanding of the complexity of living organisms, philosophers and scientists did not devote much study to the transition from inert matter to life. Plato took it for granted that the universe and every living being were composed of the 4 elements: fire, air, water, and earth. Aristotle opted for continuity, thinking, for example, that eels came from river silt. He also wrote, "Nature passes so gradually from inanimate to animate things that from their continuity their boundary and the mean between them is indistinct. The race of plants succeeds immediately that of inanimate objects." Lucretius described the emergence of life as a simple operation. Thus then the new earth first of all put forth grasses and shrubs, and afterward begat the mortal generations, there upsprung in modes innumerable after diverging fashions. In the 18th century, Diderot and other thinkers supposed that matter itself was alive. Every animal is more or less a human, every mineral more or less a plant, every plant more or less an animal. Leibniz thought the same. In the smallest particle of matter there is a world of creatures, living beings, animals, entelechies, souls. Each portion of matter may be conceived as like a garden full of plants and like a pond full of fishes. Thus there is nothing fallow, nothing sterile, nothing dead in the universe. No chaos, no confusion save in appearance. From antiquity onwards, people spoke of the spontaneous generation of life from inert matter. In the mid-19th century, biologist Félix Archimède Pouchet imagined, "It must be specified that by spontaneous generation we are only claiming that, under the influence of still unexplained forces, there occurs, either in animals themselves or elsewhere, a synthetic event that tends to group molecules, to impose on them a special mode of vitality that eventually gives rise to a new being that is related to the event, from which its elements were originally drawn." In 1861, Louis Pasteur's discovery of microorganisms put an end to belief in spontaneous generation. But the transition from inert to living matter was still viewed as something that could one day be explained or even replicated. When Darwin approached the question in 1871, in a letter to his colleague Joseph Hooker, he wrote, "But if, and oh what a big if, we could conceive in some warm little pond with all sorts of ammonia and phosphoric salts, light, heat, electricity, etc. present, that a protein compound was chemically formed, ready to undergo still more complex changes, at the present day such matter would be instantly devoured or absorbed, which would not have been the case before living creatures were formed." Between 1950 and 1970, scientists attempted to replicate the original conditions for the emergence of life on Earth. They tried to recreate the soup of chemicals spoken of by Darwin and others to see what might arise when this primordial soup was heated, dried, ground up, and subjected to electric currents. As we will see later, these attempts did succeed in creating some of the building blocks of life. Despite this, these preliminary results represent only a very small step towards understanding the genesis of life. In fact, since those pioneering days, a growing number of scientists from a wide range of fields, including physics, chemistry, biochemistry, biology, geology, and earth sciences, are now working in astrobiology, a field that aims to understand the history of life in the universe. However, despite the amazing progress made over the last 50 years, the gap between inert and living matter seems to be widening endlessly beyond anything we could have imagined. A preliminary analogy: a car and a spare part. In order to appreciate the enormity of this leap, the following analogy will help us visualize the difference between the most complex inert matter of the theoretical primordial soup, some building blocks of proteins, and the simplest known life form, a single-celled organism such as a bacterial cell. The relation between the two will give us some idea of the distance separating the two banks of the gap, and thus of the magnitude of the leap required to cross it. If we take this artificially constructed, complex inert matter, a protein about 3 × 10⁻⁹ meters, 10 × 10⁻⁹ feet, in diameter, and scale it up 10 million times, we end up with a small mechanical part measuring 3 centimeters, a little over 1 inch, in every direction, with a volume of 3 × 3 × 3 equals 27 cubic centimeters, about 1.5 cubic inches. If we then enlarge the simplest unit of living matter, say a single-celled bacterium measuring 2 × 10⁻⁷ meters, on the same scale as the protein, it would measure 2 meters, 6½ feet, in every direction. In other words, it would be the size of a car with a volume of 8 cubic meters, or 10 cubic yards, which is 300,000 times bigger than the 27 cubic centimeters, 1.5 cubic inch, spare part. The leap in size is equivalent to going from a mechanical part of 27 cubic centimeters to a mechanism of 8 million cubic centimeters. In other words, the largest inert matter produced to date represents 1/300,000th of what we'd have to synthesize to get the smallest possible single-celled organism. That is, the equivalent of one word out of all the words in 2 books like the one you are holding in your hands. To continue to assess the immense gap to be bridged, we have to look more closely at the most complex piece of inert matter that has been obtained by experimental means and compare it with the smallest conceivable living being. 2. The most complex inert matter obtained by experimental means. Between 1950 and 1970, experiments were run on prebiotic soups that mimic the conditions of the emergence of life on Earth. The result? A few building blocks of proteins. The imaginative non-specialist reader might picture scientists busy around bubbling cauldrons, stirring the scum of a strange liquid, the prebiotic soup from which bits of living matter are supposed to emerge. The actual experiments undertaken by leading chemists, biochemists, and biologists were much less picturesque, but still quite exciting. The best known of these experiments was conducted by Stanley Miller in 1953. It approximated what was thought at the time to be the atmosphere of the early Earth, bringing methane, ammonia, and hydrogen to a boil in water and subjecting the mixture to a high-voltage electrical current imitating lightning. This atmosphere must, moreover, necessarily be deprived of any oxygen, which would destroy the amino acids. The experiment yielded 13 of the 22 stable amino acids that are the building blocks of living things. Amino acids are molecules made up of 15 to 40 chemical elements, mainly carbon, hydrogen, oxygen, and nitrogen, that when linked together in long chains of several hundred to several thousand elements, constitute the complex macromolecules that are proteins essential to all living organisms. In 1958, at Florida State University, Sidney W. Fox and his student Karu Harada succeeded in creating amino acid polymers through the thermal condensation of glutamate and aspartate, 2 amino acids previously identified in Miller's experiment. Although resembling proteins, these polymers, called proteinoids, were not, however, made up like normal proteins. Dissolved in water, the proteinoids spontaneously formed microdroplets that suggested possible ancestral forms of protocells, but, not surprisingly, these microstructures were non-functional. Next, in 1960, Dr. Jean Aurot of the University of Houston mixed cyanhydric acid and ammonia in water. By heating the solution for 24 hours at 90 degrees Celsius, he was able to synthesize adenine, A, another building block of life, which is one of the 4 nucleotide bases that combine to form RNA and DNA. In 1961, Melvin Calvin, a professor at the University of California at Berkeley, used a cyclotron to run a stream of accelerated electrons at high speed through a mixture of primitive gases. He managed to synthesize amino acids along with sugar, urea, and fatty acids. In 1963, Dr. Cyril Panamparuma used Berkeley's cyclotron to irradiate a mixture of ammonia, methane, and water, simulating what was thought at that time to be the conditions of the early atmosphere. He obtained a relatively good yield of the adenine nucleobase A. In collaboration with Carl Sagan of Stanford University, he synthesized adenosine through ultraviolet irradiation of a mixture of ribose and adenine, and then the corresponding nucleobase triphosphate in the presence of phosphoric acid and polyphosphate ester under similar conditions. Sidney W. Fox, already cited for his work on proteinoids in 1958, was later able to synthesize amino acids by bringing a mixture of methane, ammonia, and water vapor to a temperature of 1,000 degrees Celsius. These experiments initiated a conceptual revolution by showing that the primordial soup by itself is not sufficient to produce life. Since then, and especially over the last 20 years, further progress has been made. For example, organic molecules involved in the composition of living matter have been identified in meteorites, comets, and interstellar clouds. These important discoveries showed that the chemistry that flows from the laws of the universe is conducive to the emergence of the basic molecules of life. In other words, the building blocks of life appear to be an inevitable result of the universe. However, it is more difficult to understand how these molecules were selected and built up on Earth. Other environmental factors must have been essential to promoting the chemical selection of the molecules that characterize life, and scientists imagine that this could have happened not only in small pools, but also perhaps in space, in the Earth's atmosphere, on mineral surfaces, or in hydrothermal vents. We have not proposed a single scenario for the origin of life, but we can suggest that none of these hypotheses excludes the others. The very complex chemistry leading to life was probably built from numerous and very different laws of the universe. These laws lead to the appearance of the first building blocks of life, which are energy wells, that is to say, naturally occurring stable combinations. Under certain conditions, as we have seen, these bricks form spontaneously and then remain stable and solid. Nevertheless, if prebiotic chemical processes can plausibly lead to small informational peptides and RNAs, it is also clear that none of these molecules are generated by the simple brewing of a primordial soup. There is still a long way to go to understand the history of life in the universe. Hubert P. Yockey, professor of theoretical physics at the University of California, Berkeley, and specialist in information theory as it applies to biology and the origin of life, came to this conclusion. Virtually all biochemists agree that life on Earth arose spontaneously from non-living matter. This belief is simply a matter of faith in strict reductionism and is based entirely on ideology. Philippe Labro of the Centre de Biophysique Moléculaire, Molecular Biology Center, at the CNRS of Orléans, made the same observation. The construction of one living cell from extremely simple molecules, such as those synthesized by Stanley Miller, is a feat of incredible complexity. The advances made by chemists since the historic experiments of Stanley Miller in 1953 seem risibly inadequate to the task. 3. The simplest life form. The development of the electron microscope has allowed us to explore reality on a very small scale. Scientists have confirmed that all living beings are composed of at least one cell, and that even the smallest of these single-celled organisms, 0.2 microns for the smallest imaginable bacteria, compared to the 20 microns or 0.02 of a millimeter of a human cell, demonstrates organization at a remarkable level of complexity. The single-celled organism is the smallest form of life, but even its structure is highly complex. The smallest living thing that we can currently imagine, even a little smaller than the smallest living thing known to date, would have a minimum size of 0.2 micrometers, 2 × 10⁻⁷ meters. This organism could only live, develop, and reproduce thanks to a very dense and organized internal structure. Inside its already complex cellular membrane, it would need, at minimum, a DNA genome of at least 250 genes, around 150,000 pairs of nucleotide bases assembled in a very precise order. It would also need an RNA system and a ribosome to interpret the RNA. Finally, this complex system would have to be able to produce at least 180 types of proteins, dozens of enzymes, and locomotory organelles. All of this equipment just for a single cell, the tiniest one possible. After 20 years of research, John Craig Venter, an expert in microbiology, genetics, and synthetic biology, made the following remark about this incredible complexity. We're showing how complex life is, even in the simplest of organisms. To date, no definite intermediate steps have been identified between the most complex inert matter and the least complicated life forms currently known. Viruses are even smaller than the smallest single-celled organisms, but they are not, strictly speaking, living beings. They are parasites that can't live or replicate unless they are attached to a living being. Nevertheless, it remains a possibility that at some intermediate stage there existed other beings capable of self-replication that disappeared after the first life forms arose. Just because they are nowhere to be found does not mean they never existed. Meanwhile, the smallest quasi-living being known by science to date is the bacterium Nasuia deltacephalonicula, discovered in 2013, which has 225 genes for a genome of 112,000 pairs of nucleotides. In reality, it is not complex enough an organism to survive on its own. It has to acquire certain nutrients from a living host. So it is a parasite, but one that possesses all the machinery of a living being capable of reproducing itself, DNA, RNA, and a ribosome to build its own proteins. But DNA, RNA, and ribosomes cannot exist independently in nature. Lacking the protective and reproductive mechanisms proper to a living being, they rapidly decay outside the protective membrane of the cell. This means that these three fundamental structures of life can only exist within a cell and can only be produced when the cell duplicates itself. The cell cannot exist without DNA, RNA, which themselves cannot exist independently outside the cell. Science does not yet have a clear explanation for this. So we return to the original question: what natural mechanism could have led to the emergence of the first cell? In order to visualize this tiny single-celled organism, let's go back to our car analogy. Let's take the smallest conceivable life form, our bacterium of 0.2 microns, 100 times smaller than a human cell. If we enlarge it 10 million times, it will be the size of a 2-meter car. On the same relative scale, the hundreds of thousands of proteins that make it up will each be the size of 1 to 10 centimeter car parts. What would we see then? Hundreds of openings not unlike a boat's portholes appear on the cell's surface, opening and closing to permit a continual circulation of materials into and out of the cell. As we enter the structure through one of these orifices, a world of immense complexity comes into view. A network of corridors and pipes branches out in every direction from the cell's perimeter, leading to information processing units and assembly lines. Cells lacking a nucleus, prokaryotes, are much larger and more complex than those with a nucleus, eukaryotes, which have the equivalent of a central memory bank. The memory bank is comparable to a spherical chamber, like a geodesic dome, storing dozens of meters of twisted chains of very fine DNA molecules well stacked in orderly rows. We marvel at the highly controlled movement of so many objects passing down so many corridors. Machines zoom about like robots in every direction. We notice that even the simplest functional parts of the cell, the protein molecules, are astonishingly complex pieces of molecular machinery, each composed of thousands of atoms in a highly organized configuration. The life of the cell depends on the coordinated activity of numerous RNA molecules and at least 180 different proteins. We notice that the cell's workings share many features with our own advanced machines: an artificial language and a decoding system, a databank for storing and extracting information, control systems that direct the automated assembly of parts and components, automatic quality control devices, assembly procedures based on prefabrication and modular construction. We're watching a whirring machine working at full steam. It is infinitely more complex than a car. It is a completely automated factory in perpetual movement, with the extraordinary capacity to duplicate itself entirely within a matter of minutes or hours. What the industrial executive can only dream of is achieved by the tiniest of our cells. We are still far from understanding the natural mechanisms that led to the synthesis of this smallest conceivable form of life, whose untold complexity continues to astonish scientists. According to microbiologist Werner Arber, 1978 Nobel Prize laureate, the most primitive cells may require at least several hundred different specific biological macromolecules. How such already quite complex structures may have come together remains a mystery to me. But if the cell as a whole is one of the greatest scientific enigmas, its principal components, DNA, RNA, proteins, ribosomes, and enzymes, have their own share of mystery. 1. DNA. Double helix, double mystery. The discovery of the double helix structure of DNA in 1953, attributed to James Watson and Francis Crick, marked a turning point in research. It revealed the existence of a single encoding language common to all life forms. DNA, or deoxyribonucleic acid, is a long chain composed of 4 molecules formed from nucleobases: adenine A, thymine T, cytosine C, and guanine G. Its beautiful double helix structure opens up to allow the genetic information to be copied. From bacteria all the way up the hierarchy of life, from plants to animals to humans, every form of life on Earth makes use of this unique language of life. The genetic message carried by DNA is coded information that, along with epigenetic sources of biological information, programs every stage of your development and physical traits, from basic cell function to the color of your eyes. Scientists call it a genetic message because it really does carry a message, an intelligible, carefully composed text that gives sequences of instructions called genes. DNA represents the most sophisticated body of information that we know of in the universe. The way DNA stores information is a true technological marvel. If we wrote out all the information stored in the DNA of a single nucleus measuring 6 millionths of a millimeter, it would take us 1 million pages, or more than 30 times the length of the Encyclopedia Britannica. If all the books ever written by humans, roughly 30 million times the Encyclopedia Britannica, were stored using this format, they would fit in a teaspoon. We are nowhere close to inventing such an efficient data storage device today, as the density of information in DNA is 40,000 billion times greater than humans' best efforts now in the 21st century. Hubert P. Yockey of Berkeley writes on this topic, "It is highly relevant to the origin of life that the genetic code is constructed to confront and solve the problems of communication and recording by the same principles found both in the genetic information system and in modern computer and communication codes. There is nothing in the physico-chemical world that remotely resembles reactions being determined by a sequence and codes between sequences." Pierre Sonigaud, expert on molecular genetics and research director at INSERM, the French equivalent of the USA's NIH, adds, "DNA seems like a historical cause, the beginning of the story, but no one knows where it comes from or how it produces life." Coming from an atheist scientist, this confession of ignorance should make us think. In 2003, the revelation of the human genome confirmed the astonishing complexity of this genetic message. Daniel Cohen, former professor of genetics at the Université de Vrije and founder and scientific director of the GenSet Corporation, Genetic Engineering, was one of the very first to map the human genome. He admitted to the French weekly Le Point, "The genome is a program written in a very sophisticated language. Could such a complex language arise by accident? We are free to suppose that, but we can't demonstrate it." Personally, I went from being an atheist to agnostic in the space of 1 year, because if this language is not the result of chance, then I suspect that one day we will be able to demonstrate it. Can you imagine what a sea change that would be? Christian de Duve, 1974 Nobel laureate in physiology, a biochemist who specializes in cellular biology, claims that the likelihood DNA arose from pure chance is one of those improbabilities so incommensurably high that they can only be called miracles, phenomena that fall outside the scope of scientific inquiry. Further, Sir Francis Crick, a molecular biologist who won the 1962 Nobel Prize in Chemistry for discovering DNA, and is not a believer, admitted that DNA was a mystery. A structure like DNA could not have appeared by chance. Scientists are unanimous on this point. The origin and development of this genetic code constitute a significant double enigma. 2. Proteins, or the 3D letters of the alphabet of life. Proteins are highly complex macromolecules built out of 22 amino acids, which are like the letters used to compose genetic phrases. A cell cannot exist without proteins because, to take but one example, the proteins at the heart of the cell, along with RNA, execute many essential tasks. These proteins are composed of hundreds or even millions of smaller chemical entities called amino acids, which are particularly special because they are lateralized. Of the 2,000 amino acids found in nature, about half are oriented to the right and half to the left, but only 22 of them, all left-oriented, are useful for life. These combine to form long protein chains. Biologists have compared them to the 26 letters of the alphabet because these letters can form a huge number of sequential combinations that function like words and phrases in the genetic code. If the letters are arranged correctly, they are a comprehensible and useful text. Otherwise, it is gibberish. There are more than 80,000 distinct proteins, and each one rests on a different specific combination of the 22 amino acids. The proteins must also be arranged in a particular three-dimensional, 3D, configuration. Proteins are effective in performing cellular tasks like recognizing other molecules and catalyzing a wide range of chemical reactions, in part due to their complex and irregular three-dimensional structure. It is the specific arrangement of amino acids within a protein sequence that specifies a particular 3D configuration. In theory, a long chain of amino acids should be able to take on an infinite number of 3D configurations, but it has recently been shown that the laws of nature exert physico-chemical constraints that reduce 3D layouts to less than 1,000 possible shapes. 3. The ribosome, a mysterious translator. The ribosome is the incredibly complex piece of machinery responsible for the synthesis of proteins encoded from messenger RNAs, which are temporary copies of DNA genes. While scientists are working to understand how this mechanism functions, its origin continues to elude all understanding. Atheist George Church, professor of genetics at Harvard and director of the Center for Computational Genetics at MIT, expresses his astonishment on the subject of this translator composed essentially of RNA and proteins. The ribosome, both looking at the past and at the future, is a very significant structure. It's the most complicated thing that is present in all organisms. If I were to be an intelligent design defender, that's what I would focus on. How did the ribosome come to be? If we take all the life forms we have so far, isn't the minimum for the ribosome about 53 proteins and 3 polynucleotides? And hasn't that kind of already reached a plateau where adding more genomes doesn't reduce that number of proteins? That's really marvelous. We need to understand that better. Nobody has constructed a ribosome that works well without proteins. These proteins themselves are synthesized thanks to a ribosome made up of about 2/3 RNA. 4. Enzymes, incredible time savers. Enzymes are a crucial kind of protein. Without them, the many chemical reactions that take place in cells every second would take a prohibitively long time. Richard Wolfenden, professor of biochemistry at the University of North Carolina, expert in enzymes and biochemical kinetics and member of the American Academy of Sciences, notes that without the proper enzyme at work in the decarboxylation of orotidine 5' monophosphate decarboxylase, OMPDC, a reaction that is absolutely essential for the synthesis of DNA and RNA, it would take 78 million years to process just half the substrate. Enzymes get the job done in 18 milliseconds, 10 to the 17th times faster. And like most enzymes, OPMDC is a protein whose synthesis depends on DNA and RNA. In the same way, it would normally take 2.3 billion years to process half the substrate needed for another reaction crucial for the synthesis of chlorophyll and hemoglobin. But thanks to their shape recognition abilities, enzymes make the reaction take place in a few milliseconds. How can we explain the existence of enzymes and their presence at the right place at the right time? No one yet knows. 5. 2 languages and a translator. Since the year 2000, we have known that DNA, proteins, and ribosomes form part of a unique, sophisticated, and coordinated coding system. The 2009 Nobel Prize in Chemistry was awarded to 3 researchers, Venki Ramakrishnan, Cambridge, Thomas A. Seitz, Yale, and Ada E. Yonat, Israel, who worked on this specific subject. How does the translator function between the 2 languages, that of DNA, 4 letters, and that of proteins 22 letters. A 2009 press release notes that the prize was awarded in recognition of research into one of life's core processes, the ribosome's translation of DNA information into life. The press release continues, ribosomes produce proteins, which in turn control the chemistry in all living organisms. But the DNA molecule is passive. If there was nothing else, there would be no life. In fact, all life requires these two languages, DNA and proteins, to be in place, each with its own alphabet, 4 bases for DNA, 22 amino acids for proteins, vocabulary, and grammar. The ribosome's translation system is the crucial intermediary between these two languages. The analogy of language is well suited to explaining how DNA works. The 4 bases group together in threes to form codons with 4 times 4 times 4 equals 64 possible combinations of words, but we notice that only 61 are used to give, through genes, instructions that program our development. What about the 3 unused codons? They function as punctuation, codon stops, to signify the beginning and end of phrases. The rules of language are nothing new. This extremely complex system of 2 languages and their translator must have existed with Luca, last universal common ancestor, the common ancestor of all living beings, and has changed very little over the past 3.8 billion years. Jacques Monod, a militant atheist, wrote, "The big problem is the origin of the genetic code and the mechanism of translation. Actually, it is more of an enigma than a problem. The code has no meaning unless it is translated. The translation machine of the modern cell possesses at least 50 macromolecular parts that are also coded in DNA. That means the code can only be translated by products that are the result of a translation. It's the modern version of the chicken and the egg paradox. When and how did the loop close? That is an exceedingly difficult question to think about." Hubert P. Yockey observed, "The genetic information system is segregated, linear, and digital. It is astonishing that the technology of information theory and coding theory has been in place in biology for at least 3.85 billion years." How could nature alone have put in place more than 3.85 billion years ago the entire ultra-complex system that characterizes life on Earth? How could this code, the only key to life on Earth as we know it, have created itself and become operational all at once without any subsequent evolution? All these questions remain unanswered. 6. Metabolism, the whirlpool of life. A living being cannot be reduced to the sum of its parts, each more improbable than the next. The movement underlying the kinetic and stable chemical system that we call life itself has to be set in motion. Metabolism is a series of coordinated movements and highly complex biochemical operations that have to take place without ceasing for an organism to stay alive. If we gather together all the cell's parts at the same place and time and in the right order, we still have only a dead cell, the equivalent of a factory filled with machines that aren't switched on. A living structure must be capable of autonomous movement and precise activities, constantly assimilating, eliminating, and renewing the material elements that compose it, while also performing a wide range of complex operations to adapt, regenerate if necessary, reproduce, and evolve. Metabolism involves setting in action a number of catalytic nanomachines crucial to carrying out numerous interactions and coordinated chemical processes every second, and this coordination, so essential to life, is still very difficult to explain. In the last 50 years, we have discovered that the complexity of life surpasses anything we could have imagined. Today's leading figures in science have been humbled by this fact. Sir Francis Crick, a militant atheist and winner of the 1962 Nobel Prize in Chemistry for the discovery of DNA, explains the situation. An honest man, armed with all the knowledge available to us now, could only state that in some sense the origin of life appears at the moment to be almost a miracle, so many are the conditions which would have had to have been satisfied to get it going. Harold Urey, 1934 Nobel Prize winner in chemistry and atheist, admits, All of us who study the origin of life find that the more we look into it, the more we feel it is too complex to have evolved anywhere. We all believe, as an article of faith, that life evolved from dead matter on this planet. It is just that its complexity is so great, it is hard for us to imagine that it did. Franklin Herold, professor of microbiology at the University of Washington, ended his work, The Way of the Cell, Molecules, Organisms, and the Order of Life, with these words: "The origin of life appears to me as incomprehensible as ever, a matter for wonder but not for explication." Lynn Margulis, microbiologist at the University of Massachusetts, member of the American Academy of Sciences and a convinced atheist, underlines the importance of the qualitative leap from inert to living matter. To go from a bacterium to people is less of a step than to go from a mixture of amino acids to that bacterium. Michael Denton, former director of the Genetics Center in Sydney, professor of biochemistry at the University of Otago and expert on evolution, writes, "Is it really credible that random processes could have constructed a reality, the smallest element of which, a functional protein or gene, is complex beyond our own creative capacities, a reality which is the very antithesis of chance, which excels in every sense anything produced by the intelligence of man?" To get some idea about what nature supposedly accomplished all by itself, let's calculate the probability of a protein emerging by pure chance. There are 3 reasons why we should calculate this probability. It is mathematically approximable. Many specialists have already done so, and we present the probabilities they've calculated. Proteins belong to the realm of inert matter, so the probability of a protein emerging is not affected by the laws of evolution. The calculation of the probability of their appearance is not affected by natural selection. Protein chains consist of between 150 and several million amino acids. What is the minimum probability that a chain composed of 1,000 of the 22 types of amino acids could come together in the right order? Our calculation won't take into account the question of proper 3D arrangement, extremely improbable, or the success rate of the connection of amino acids through peptide bonds, which only happens successfully half the time, and will also ignore the fact that to be used in a living system, an amino acid must have a left enantiomer conformation, not the equally likely right conformation. Even when we make the task this much simpler, the probability comes out to be 1 chance in 22 to the 1,000th. In other words, about 1 chance in 10 to the 1,500th. The number is so large it is impossible to comprehend. To put it in perspective, the likelihood is less than winning the lottery by drawing the right 6 numbers between 1 and 49 in order, at 1 chance in 10 billion, every week in a row for 150 weeks, more than 2 years. It is radically impossible for this to happen by chance. Practically speaking, it would take longer than the lifespan of the universe for a single protein to form by accident out of available amino acids. And since the simplest life form has at least 200 proteins, we are dealing with improbabilities of staggering proportions, especially since a living cell needs not only 200 proteins but also DNA, RNA, genes, enzymes, and a good deal of other factors like metabolism. Professor Frank Salisbury, former director of plant science at Utah State University and member of the American Association for the Advancement of Science, AAAS, has estimated the probability of the formation of a molecule of DNA through natural chemical reactions on 10 to the 20th hospitable planets over the course of 4 billion years at 1 chance in 10 to the 415th. Simply put, in practical reality, there is no chance at all. As we shall see later, there are others who have calculated the probability that the 2,000 enzymes useful for life could self-assemble by chance at 1 in 10 to the 40,000th, a number that makes virtually no sense in the real world. The possibility that 100 proteins could self-assemble in parallel by chance has been calculated at the ridiculously low chance of 1 in 10 to the 2,000th. Finally, other scientists estimate at 1 chance in 10 to the 340,000th the probability that the simplest living cell could arise by chance. The number is dizzying. The discovery of this near absolute impossibility is reflected in the facts. There has been no large-scale international effort to recreate the conditions that might have led to the emergence of life. Since the 1970s, scientists have ceased their attempts to obtain life from inert matter. Their resignation provokes a realization. Yes, we are today faced with an enigma that surpasses our understanding. With the help of state governments, scientists often manage to find the time and money to undertake important research that advances our understanding in matters of crucial scientific importance. The Apollo program, launched in the 1960s to get a man on the moon, required 400,000 people working for 10 years with a total budget of $25 billion, $169 billion in today's money. As is well known, this effort was successful. To decrypt the human genome, 25,000 researchers worked for 12 years with a total budget of €3 billion. They also succeeded. ITER, an international nuclear fusion research and engineering project whose goal is to use nuclear fusion to produce unlimited free energy for the world, has an operating budget of more than €10 billion. The project is still in progress. However, no international program is trying to recreate and experiment with the conditions that would allow us to observe a natural start of life. Why is this? Probably because so far no one has proposed a single credible scenario for how to cross the chasm that separates living and inert matter. Discovering the origins of life would be a huge leap for human knowledge, but, in the absence of even a minimal roadmap, not even the most princely budget can work miracles. Eugene Koonin, director of an evolutionary genetics library at the National Center for Biotechnology Information, assesses the current state of scientific thought on the origins of life. The origin of life field is a failure. We still do not have even a plausible, coherent model, let alone a validated scenario, for the emergence of life on Earth. Certainly, this is due not to a lack of experimental and theoretical effort, but to the extraordinary intrinsic difficulty and complexity of the problem. A succession of exceedingly unlikely steps is essential for the origin of life, from the synthesis and accumulation of nucleotides to the origin of translation. Through the multiplication of probabilities, these make the final outcome seem almost like a miracle. However, some programs actively work on synthetic biology. There is a sharp distinction between the stalled state of research into the spontaneous emergence of life and the flourishing science of synthetic biology. Synthetic biology is a robust scientific field that aims to recreate the various components necessary for life out of inert matter. This is a question of copying existing life using the chemical elements present in nature and knowing in advance the desired result, using all our intelligence, all our knowledge, and the extraordinary tools of modern technology. Although it does not concern itself with the spontaneous emergence of life that takes place in nature, without the intervention of human understanding or modern technological intervention, synthetic biology is nevertheless a fascinating and rapidly developing discipline. In September 2017, researchers at 17 labs in the Netherlands formed the group Building a Synthetic Cell, BASIC, with a goal of constructing a synthetic cell that can grow and divide within a 10-year projected time frame. The project is funded by a government grant of €18.8 million. In September 2018, the U.S. National Science Foundation, NSF, announced the launch of its first synthetic cell program, financed to the tune of $10 million. Several European researchers have also proposed to construct a synthetic cell within the framework of the European Commission's flagship programs in future and emerging technologies with a €1 billion budget. Even if we can hope to succeed one day in synthesizing a living organism, understanding the conditions under which life emerged naturally remains entirely speculative and outside our comprehension. According to leading scientists, it's no fluke. Anthony Flew, one of the greatest philosophers of the 20th century, became an atheist when he was 15 years old and spent almost his whole life fighting for the atheist cause, most famously writing Theology and Falsification. After 54 years of militant atheism, he made a profound reversal at 81 years old. He explains, I think the DNA material has shown, by the almost unbelievable complexity of the arrangements which are needed to produce life, that intelligence must have been involved in getting these extraordinarily diverse elements to work together. Chandra Vikramasinghe, professor of applied mathematics and astronomy at University College Cardiff and former collaborator with Fred Hoyle, concludes, "The likelihood of the formation of life from inanimate matter is 1 to a number with 40,000 noughts after it, 10 to the 40,000th. It is big enough to bury Darwin and the whole theory of evolution. There was no primeval soup, neither on this planet nor any other, and if the beginnings of life were not random, they must therefore have been the product of purposeful intelligence." Christian de Duve thinks that chance has to be excluded as a hypothesis. "I have opted for a universe that is meaningful and not empty of meaning, not because I want it to be so, but because this is how I interpret the scientific data we have." Hubert P. Yockey is also struck by the improbability of coding the emergence of DNA, pointing out that natural selection would have to explore 1.40 times 10 to the 70th different genetic codes to discover the universal genetic code found in nature. Biologists have calculated the probability that the 1,000 enzymes necessary for life could come together in an ordered manner to form a living cell over the course of an evolution of several billion years at less than 1 chance in 10 to the 1,000th. The famous Fred Hoyle, MIT, went even further, declaring, "Life cannot have had a random beginning. The trouble is that there are about 2,000 enzymes, and the chance of obtaining them all in a random trial is only 1 part in 10 to the 40,000th, an outrageously small probability that could not be faced even if the whole universe consisted of organic soup." Biochemist Michael Denton also tried his hands at calculating the probabilities. To get a cell by chance would require at least 100 functional proteins to appear simultaneously in one place. That is, 100 simultaneous events, each of an independent probability which could hardly be more than 10 to the minus 20th, giving a maximum combined probability of 10 to the minus 2,000th. The molecule of cytochrome C, present among almost all living things and essential for cellular respiration, is composed of 100 amino acids. Hubert P. Yockey has calculated that the probability of this molecule coming into existence through the random linking up of amino acids is 1 in 10 to the 65th. Even if there were enough amino acids to fill all the world's oceans, around 10 to the 42nd molecules, while taking account of the constraints due to chirality, the exclusion of right-handed amino acids, the probability plummets to chance in 10 to the 94th, as he explained at the Tacoma Conference, New York, June 1988. Robert Shapiro, professor of biochemistry at New York University, focuses his research on bacteria. He has estimated at 1 chance in 10 to the 40,000th the probability that the 2,000 types of proteins present in a simple bacterium could form as a result of chance alone. Finally, biophysicist Harold Morowitz of Yale University, an expert in the applications of computer science and thermodynamics in biology, calculated the probability that the simplest living cell arose as a result of chance alone at 1 chance in 10 to the 340,000th, which for all practical purposes is evidently equal to 0. The numbers don't lie, and they all point one way. Pure chance is not a reasonable hypothesis for explaining the transition from inert matter to the first living being. Consequently, the various laws and physico-chemical constraints that govern the appearance of life point necessarily to the existence of an intelligent designer. The preceding chapters on cosmology have already shown that the fine-tuning of the universe had a 1 in 10 to the 120th chance of turning out as it did, as if this number weren't crazy enough already. But biology has yielded even more outlandishly long odds. The probability that life emerged by chance is mind-blowingly small, 10 to the 340,000th, but nothing in the observable universe can exceed 10 to the 120th. The fine-tuning of the laws of the universe is a genuine proof of the existence of a designer. The argument is convincing beyond all reasonable doubt. Fred Hoyle, himself a convert from atheism to deism, Realize that only a psychological or ideological block can explain why some people refuse to admit the possibility of a creative intelligence. Once we see, however, that the probability of life originating at random is so utterly minuscule as to make it absurd, it becomes sensible to think that the favorable properties of physics on which life depends are in every respect deliberate. It is therefore almost inevitable that our own measure of intelligence must reflect higher intelligences, even to the limit of God. Such a theory is so obvious that one wonders why it is not widely accepted as being self-evident. The reasons are psychological rather than scientific. The fact that we can quantify the incredible leap from the inert to the living is strong evidence for the existence of a creator God. A committed materialist can explain the existence of life in one of two ways: by stubbornly persisting in the assumption that this leap is a result of chance alone, not due to a fine-tuning of the laws of the universe. In that case, he prefers to accept a hypothesis whose probability is so infinitesimal that for all intents and purposes it is impossible, to accepting the existence of a creator God, which, by all accounts, is an enormously more probable hypothesis. One could consider this choice entirely irrational, based more on a categorical rejection of the existence of a creator God than as the result of mature reflection. Or he could view this passage as the outcome of a universe governed by laws that, among countless possible multiverses, happens to be uniquely conducive to the emergence of life. This is the final trump card we referred to earlier, and it is really just another way of refusing to look the scientific facts in the face. It is to opt for science fiction. On the other hand, accepting the hypothesis of a creator God makes it possible to choose from two explanatory models. We can postulate that the leap from inert to living matter took place according to natural laws set in place by a creator God in the very beginning. According to this model, life is the result of precise programming on the part of God, who carefully designed cosmological development to permit life as we know it to develop. Or, if it's impossible to believe that any number of natural laws could have brought about such a giant leap, we must hold that this particular step was the result of a special intervention by the same creator God. One piece of evidence that has surprised many scientists is that the passage from inert to living matter seems to have taken place only once in the history of our Earth, and many believe that all living beings are descended from one common ancestor, the celebrated single-celled organism known as Luca. Nobel laureate Pierre-Gilles Lejeune has expressed his astonishment. What intrigues me is the fact that the genetic code is always the same, while life has adapted itself in many ways. I have a hard time believing that Darwinian selection could result in only one type of code. The conclusions drawn from biology join those we have made from cosmology as additional evidence for the necessity of the existence of a creator God. At this point, the reader might want to know what scientists themselves think about all these discoveries. The next chapter will answer this question. 100 citations from leading figures in science will reveal the difficulties and the questions that cutting-edge advances have raised within the scientific community. To our knowledge, this is the first time that these citations, combined with precise references, have been published together in one place. 13. 100 essential citations from leading scientists. The following 100 quotes from leading scholars in various scientific fields highlight the surprising and thought-provoking nature of these discoveries. They are essential because they uncover the metaphysical significance of the insights these discoveries provide about reality and existence. Furthermore, they illustrate how weak and even discredited the old materialist frameworks of thought are in comparison. Nietzsche's claim that God is dead, held by the scientists of the 19th and 20th centuries, has itself suffered a mortal wound. In the science today, God is more alive than ever. 1. Cosmology, physics, chemistry. An asterisk indicates that the citation has been previously referenced. 1. Alexander Vilenkin, 1949 to the present. professor of theoretical physics at Tufts University and director of the Tufts Institute of Cosmology, on his theorem demonstrating the necessity of an absolute beginning to the universe. It is said that an argument is what convinces reasonable men, and a proof is what it takes to convince even an unreasonable man. With the proof now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. There is no escape. They have to face the problem of a cosmic beginning. 2. Roger Penrose, 1931 to the present. Professor of mathematics at Oxford and winner of the 2020 Nobel Prize in Physics. But in order to start off the universe in a state of low entropy, so that there will indeed be a second law of thermodynamics, the Creator must aim for a much tinier volume of the phase space. Several pages of argumentative calculations follow. This now tells us how precise the Creator's aim must have been, namely to an accuracy of 1 part in 10 to the power of 10 to the 123rd. This is an extraordinary figure. Even if we were to write a 0 on each separate proton and on each separate neutron in the entire universe, and we could throw in all the other particles as well for good measure, we should fall far short of writing down the figure needed. 3. Richard Feynman, 1918 to 1988, physicist, pioneer of quantum mechanics, and 1965 Nobel laureate in physics. There is a most profound and beautiful question associated with the observed coupling constant, E, the amplitude for a real electron to emit or absorb a real photon. It is a simple number that has been experimentally determined to be close to 0.08542455. It has been a mystery ever since it was discovered more than 50 years ago, and all good theoretical physicists put this number up on their wall and worry about it. It's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil. 4. Christian Anfinsen, 1916 to 1995, professor of chemistry at Harvard and winner of the 1972 Nobel Prize in Chemistry. I think only an idiot can be an atheist. We must admit that there exists an incomprehensible power or force with limitless foresight and knowledge that started the whole universe going in the first place. 5. Alfred Kastler, 1902 to 1984, winner of the 1966 Nobel Prize in Physics and the inventor of the laser. The idea that the world, the material universe, created itself seems to me patently absurd. I do not conceive of the world without a creator, which is to say, without a God. For a physicist, a single atom is so complicated, so pregnant with intelligence, that the materialist universe simply makes no sense. Again, there is no chance of explaining the emergence of life and its evolution by the interaction of chance forces. Other forces are at work. 6. Werner Heisenberg, 1901 to 1976, who invented quantum mechanics and won the 1932 Nobel Prize in Physics. Atomic physics has turned science away from the materialistic trend it had during the 19th century. 7. Robert Laughlin, 1950 to the present, professor of physics at Stanford and winner of the 1998 Nobel Prize in Physics. The theories of everything in general and string theory in particular left me more and more perplexed all the time because they are unfalsifiable. No experiential data can prove that they are wrong. I realized that people accept string theory for ideological reasons. It was a terrible shock to me because I thought that scientists shunned any form of ideology. That's far from the case. 8. Robert W. Wilson, 1936 to the present. The radio astronomer who discovered cosmic microwave background radiation and won the 1978 Nobel Prize in Physics. Certainly there was something that set it all off. Certainly, if you are religious, I can't think of a better theory of the origin of the universe to match with Genesis. 9. William D. Phillips, 1948 to the present. specialist in the laser cooling of atoms and 1997 Nobel laureate in physics. Why is the universe so finely tuned for the existence of life? More to the point, why is the universe so finely tuned for the existence of us? Does this constitute legitimate scientific evidence for an intelligent creator? It may, but it is not universally compelling. 10. Robert Millikan, 1868 to 1953. The physicist who calculated the charge of the electron and the Planck constant, winner of the 1923 Nobel Prize in Physics. A lifetime of scientific research has convinced me that there is a divinity who is shaping the destiny of man. 11. George Thomson, 1892 to 1975. British physicist, Nobel co-laureate in 1937. Probably every physicist would believe in a creation of the universe if the Bible had not unfortunately said something about it many years ago and made it seem old-fashioned. 12. Arthur Schawlow, 1921 to 1999, professor at Stanford, co-inventor of the laser, and 1981 Nobel laureate in physics. The world is just so wonderful that I can't imagine it just having come by pure chance. 13. Robert Jastrow, 1925 to 2008, astrophysicist, professor at Columbia, and director of NASA. For the scientist who has lived by his faith in the power of reason, the story ends like a bad dream. He has scaled the mountains of ignorance. He is about to conquer the highest peak. As he pulls himself over the final rock, he is greeted by a band of theologians who have been sitting there for centuries. 14. Paul Davies, 1946 to the present. Cosmologist and astrobiologist, professor of theoretical physics at the University of Adelaide, and formerly at Cambridge. The multiverse theory seems to have become the main explanation for scientists to justify the remarkable ability of our universe to welcome life. But this theory is problematic for me. The death of scientism, of its determinism, of its dream of a transparent science that can access the secret of the universe, was a kind of torture for the Nobel Prize laureates who lived the quantum adventure. 15. Anthony Hewish, 1924 to 2021. Professor of astronomy at Cambridge and winner of the 1974 Nobel Prize in Physics for the discovery of pulsars. I believe in God. It makes no sense to me to assume that the universe and our existence is just a cosmic accident, that life emerged due to random physical processes in an environment which simply happened to have the right properties. God certainly seems to be a rational creator. That the entire terrestrial world is made from electrons, protons, and neutrons, and that a vacuum is filled with virtual particles demands incredible rationality. 16. Arno A. Penzias, 1933 to 2024. Nobel Prize in Physics, 1978. In order to achieve consistency with our observations, we must assume not only creation of matter and energy out of nothing, but creation of space and time as well. The best data we have are exactly what I would have predicted had I nothing to go on but the 5 books of Moses, the Psalms, the Bible as a whole. The Big Bang is a moment of discrete creation from nothing. 17. Richard Smalley, 1943 to 2005. Professor of Chemistry at Rice University and 1996 Nobel laureate in Chemistry. Although I suspect I will never fully understand, I now think the answer is very simple. It's true. God did create the universe about 13.7 billion years ago, and of necessity has involved himself with his creation ever since. The purpose of this universe is something that only God knows for sure, but it is increasingly clear to modern science that the universe was exquisitely fine-tuned to enable human life. 18. Charles Townes, 1915 to 2015. Physicist, professor at Berkeley, winner of the 1964 Nobel Prize in Physics, and former director of NASA. I strongly believe in the existence of God based on intuition, observations, logic, and also scientific knowledge. Again, many cosmologists have a feeling that somehow intelligence must have been involved in the laws of the universe. Also, determinism no longer holds water. Biologists have not yet learned the limits of their knowledge, though it is staring them in the face. 19. Marc Lévy, 1953 to the present. Physicist, pupil of Prigogine. Let's assume, along with Stephen Hawking and Steven Weinberg, that the development of our universe since the Big Bang is the result of pure chance alone. This universe, guided totally by chance, managed to synthesize a self-replicating RNA molecule. The probability that this synthesis took place according to the laws of chance can be calculated. It is thus also possible to calculate the time it would take for a chance-based universe to do it. It turns out that this time is millions of times greater than the age of our present universe. Thus, the chance hypothesis is refuted in its own language, the calculation of probabilities. 20. George Smoot, 1945 to the present. Astrophysicist and cosmologist, professor at Berkeley, Nobel laureate 2006. The most cataclysmic event that we could imagine, the Big Bang, appears when closely examined to be precisely orchestrated. On the detailed images provided by the WMAP satellite, he said, "If you're religious, it's like looking at God. The order is so beautiful and the symmetry so beautiful that you think there is some design behind it." Then, in 2006, when he received the Nobel Prize for his striking images of the first light of the universe, "It is like seeing God. I saw the universe at its very beginning. I saw the anisotropy that allowed the universe to exist." 21. Donald Page, 1948 to the present. Professor of Physics and Cosmology at the University of Alberta. In view of all the evidence, including both the elegance of the laws of physics, the existence of orderly sentient experiences, and the historical evidence, I do believe that God exists and think the world is actually simpler if it contains God than it would have been without God. 22. Jin Soon Tuan, 1948 to the present. Buddhist astronomer, professor of astrophysics at the University of Virginia, and research associate at the Institut d'Astrophysique de Paris. One of the most surprising discoveries of modern cosmology is the realization that the initial conditions and physical constants of the universe had to be adjusted with exquisite precision if they are to allow the emergence of conscious observers. This realization is referred to as the anthropic principle. Change the initial conditions and physical constants ever so slightly, and the universe would be empty and sterile. We would not be around to discuss it. The precision of this fine-tuning is nothing short of stunning. The initial rate of expansion of the universe, to take just one example, had to have been tweaked to a precision comparable to that of an archer trying to land an arrow in a 1 square centimeter target located on the fringes of the universe 15 billion light-years away. Again, I reject the hypothesis of chance because, aside from the meaninglessness and despair it would entail, I cannot conceive that the harmony, symmetry, unity, and beauty we perceive not only in the world, from the delicate pattern of a flower to the majestic architecture of galaxies, but also in the laws of nature, are the mere results of chance. If we accept the hypothesis of a single universe, our own, we must also postulate a primary cause that from the outset tweaked the laws of physics and initial conditions in order for the universe to become conscious of itself. If we accepted the hypothesis of a single universe, our own, we must also postulate a primary cause. 23. Edward Harrison, 1919 to 2007. Professor of Astrophysics at the University of Massachusetts in Amherst. Here is the cosmological proof of the existence of God, the design argument of Paley, updated and refurbished. The fine-tuning of the universe provides prima facie evidence of deistic design. Take your choice: blind chance that requires multitudes of universes, or design that requires only one. Many scientists, when they admit their views, incline toward the teleological or design argument. 24. Robert Dicke, 1916 to 1997, professor of physics at Princeton, discoverer of the fine-tuning of the universe. The puzzle here is the following: how did the initial explosion become started with such precision? the outward radial motion becomes so finely adjusted as to enable the various parts of the universe to fly apart while continuously slowing in the rate of expansion. There seems to be no fundamental theoretical reason for such a fine balance. If the fireball had expanded only 0.1% faster, the present rate of expansion would have been 3 times 10 to the third as great. Had the initial expansion rate been 0.1% less, and the universe would have expanded to only 3 times 10 to the minus sixth of its present radius before collapsing, no stars could have formed in such a universe, for it would not have existed long enough to form stars. 25. Lee Smolin, 1955 to the present, materialist physicist. We must understand how it came to be that the parameters that govern the elementary particles and their interactions are tuned and balanced in such a way that a universe of such variety and complexity arises. We should ask just how probable is it that a universe created by randomly choosing the parameters will contain stars? The answer, in round numbers, comes to about 1 chance in 10 to the 229th. Again, the universe is improbable, and it is improbable in the sense that it has a structure which is much more complex than it would be if its laws and initial conditions were chosen more randomly. 26. Gregory Benford, 1941 to the present, professor of physics and astronomy at the University of California, Irvine. This multiverse view represents the failure of our grand agenda and seems to me contrary to the prescribed simplicity of Occam's razor, solving our lack of understanding by multiplying unseen entities into infinity. 27. Brian Greene, 1963 to the present, professor of physics and mathematics at Columbia, expert in string theory. The laws of physics are the closest thing in the world today that I would align with a theological perspective. I view the world as extraordinarily coherent and harmonious because of the way the fundamental laws of physics are able, with just a few symbols etched on a piece of paper, to describe a wealth of phenomena, from subatomic particles to the edge of the universe. That resonates with me in a similar way as the order, organization, and explanation for the universe that adherents of religion will ascribe to a deity. From my perspective, that order and organization come from fundamental physical laws. For others, that's the role that God plays. 28. Henry F. Schaefer, 1944 to the present, professor of chemistry, director of the Center for Computational Chemistry at the University of Georgia, and one of the most quoted chemists in the world. Against powerful logic, some atheists continue to claim, irrespective of the anthropic constraints, that the universe and human life were created by chance. 29. Werner Gitt, 1937 to the present, professor and director of the Federal Institute of Physics and Technology, Brunswick. All experiences indicate that a thinking being voluntarily exercising his own free will, cognition, and creativity is required. There is no known law of nature, no known process, and no known sequence of events which can cause information to originate by itself in matter. 30. Carlo Rubbia, 1934 to the present, professor of physics at Harvard, director of CERN, expert in particle physics, 1984 Nobel laureate. Speaking of the origin of the world brings us inevitably to think of creation, and, in considering nature, we find that it has an order too precise to have been determined by chance from confrontations between forces that we, physicists, continue to maintain. However, I believe that the existence of a pre-established order of things is more evident among us than elsewhere. We come to God by the path of reason. Others follow the irrational path. 31. Derek Barton, 1918 to 1998, professor of chemistry at Imperial College and at Harvard, 1969 Nobel laureate in chemistry. The observations and experiments of science are so wonderful that the truth that they establish can surely be accepted as another manifestation of God. God shows himself by allowing man to establish truth. 32. Jacques Desmarais, 1943 to 1999, cosmologist specializing in the anthropic principle and professor at the University of Liège. The mere fact that we are present here in the universe tells us something about the value of the fundamental constants, for example, the physical constants such as the Planck constant or the fine structure constant. Though scientists do not know why these constants have the specific values they do, what we are certain about is that if they varied even slightly, then life could never have emerged. 33. John Polkinghorne, 1930 to 2021, Professor of Mathematics and Physics at the University of Cambridge. The precise adjustment of the initial conditions of the universe is an indispensable element of the existence of the world. Through their discoveries, scientists encounter the divine Logos. 34. Isidore Isaac Rabi, 1898 to 1988, winner of the 1944 Nobel Prize in Physics. Physics filled me with awe, put me in touch with a sense of original causes. Physics brought me closer to God. That feeling stayed with me throughout my years in science. 35. Herbert Uhlig, 1907 to 1993, physical chemist and professor of metallurgy at MIT. The origin of the universe can be described scientifically as a miracle. 36. Shoichi Yoshikawa, 1935 to 2010, professor of astrophysics at Princeton. I think that God originated the universe and life. Homo sapiens was created by God using a process which does not violate any of the physical laws of the universe in any significant way. 37. Antonino Zucchichi, 1929 to the present, physicist at CERN, president of the European Physical Society and of the World Federation of Scientists. Without science, we would have no retort for an atheistic culture that wishes we were nothing more than sons of chance. 38. Freeman Dyson, 1923 to 2020, physicist, astrophysicist, futurologist, and professor at Princeton. As we look out into the universe and identify the many accidents of physics and astronomy that have worked together to our benefit, it almost seems as if the universe must in some sense have known that we were coming. 39. Max Born, 1882 to 1970, physicist and professor of theoretical physics at Göttingen, Nobel Prize in Physics, 1954. If alpha, the fine structure constant, were bigger than it really is, we should not be able to distinguish matter from ether, the vacuum, nothingness, and our task to disentangle the natural laws would be hopelessly difficult. The fact, however, that alpha has just its value 1/137th is certainly no chance, but itself a law of nature. It is clear that the explanation of this number must be the central problem of natural philosophy. 40. John Barrow, 1952 to 2020, professor of astronomy at Cambridge, speaking about theories of the universe emerging from nothing. These theories necessarily assume the existence of far more than what we would usually consider nothing. From the beginning, there must be laws of nature, energy, mass, geometry, and, implicitly, the world of mathematics and of logic. There must be a considerable underlying structure based on rationality. One must remain aware of the fact that many studies on cosmology are motivated by the desire to avoid an initial singularity. 41. Arthur Compton, 1892 to 1962, professor of physics at Princeton and winner of the 1927 Nobel Prize in Physics. If religion is to be acceptable to science, it is important to examine the hypothesis of an intelligence working in nature. The discussion of the evidences for an intelligent God is as old as philosophy itself. The argument on the basis of design, though trite, has never been adequately refuted. On the contrary, as we learn more about our world, the probability of its having resulted by chance processes becomes more and more remote, so that few indeed are the scientific men of today who will defend an atheistic attitude. 42. George Efstathiou, 1955 to the present, professor of cosmology, director of the Institute of Astronomy at Cambridge, and member of the scientific team of the European Space Agency's Planck satellite. Even if the probability of developing a universe is very low with a weak cosmological constant, if there were an infinity of universes, it would have appeared somewhere. But is this really an explanation or a desperate answer? 43. Max Planck, 1858 to 1947. One of the founders of quantum mechanics, 1918 Nobel laureate in physics and discoverer of the quantum structure of radiation. Metaphysical reality does not stand spatially behind what is given in experience but lies fully within it. Again, anybody who has been seriously engaged in scientific work of any kind realizes that over the entrance to the gates of the temple of science are written the words, "You must have faith. It is a quality which the scientists cannot dispense with." Also, all matter originates and exists only by virtue of a force. We must assume behind this force the existence of a conscious and intelligent spirit. 44. Tony Rothman, 1953 to the present, cosmologist and professor of physics at Wesleyan University. When confronted with the order and beauty of the universe and the strange coincidences of nature, it is very tempting to take the leap of faith from science into religion. I am sure many physicists want to. I only wish they would admit it. 45. Max Tegmark, 1967 to the present, astronomer at MIT. The multiple parallel universes allow us to ignore the fine-tuning of the cosmos's initial conditions and of the fundamental constants. At the end of the day, we are making our judgment based on nothing more than what we find most exquisitely to our taste. 46. Dr. Alan Sandage, 1926 to 2010. One of the most celebrated astronomers of our day, who recognized his belief in God at the age of 50. The world is too complicated in all parts and interconnections to be due to chance alone. 47. Lothar Schaefer, 1939 to 2020, professor of quantum chemistry at the University of Arkansas. At the root of all ordinary objects, we find entities that possess the rudiments of consciousness. In quantum leaps, quantum systems act spontaneously. A spirit is the only thing we know of that can act that way. One cannot use science as a basis for atheism. It's a lost cause. 48. Fred Hoyle, 1915 to 2001, cosmologist and astronomer. The chance that higher life forms might have emerged in this way is comparable with the chance that a tornado sweeping through a junkyard might assemble a Boeing 747 from the materials therein. Hoyle and Wickramasinghe calculate the probability of the 2,000 enzyme proteins needed to accelerate the chemical reactions needed to cause life at one chance in 10 to the 40,000th, calling this an outrageously small probability that could not be faced even if the whole universe consisted of organic soup. I've always thought it curious that, while most scientists claim to eschew religion, it actually dominates their thoughts more than it does the clergy. Again, I do not believe that any scientist who examined the evidence would fail to draw the inference that the laws of nuclear physics have been deliberately designed with regard to the consequences they produce inside the stars. 49. Robert Caïta, 1952 to the present, professor of physics and astrophysics at Princeton. Science is impossible without accepting that we live in a caused universe that ultimately should encourage one to acknowledge its first cause, or creator. 50. Wernher von Braun, 1912 to 1977, former director at NASA and inventor of the V-2 rocket, the first ballistic missile used during World War II. One cannot be exposed to the law and order of the universe without concluding that there must be design and purpose behind it all. The better we understand the intricacies of the universe and all it harbors, the more reason we have found to marvel at the inherent design upon which it is based. To be forced to believe only one conclusion, that everything in the universe happened by chance, would violate the very objectivity of science itself. Certainly there are those who argue that the universe evolved out of a random process, but what random process could produce the brain of a man or the system of the human eye? 51. Henry Lipson, 1910 to 1991, president of the physics department at the University of Manchester. I think we must admit that the only acceptable explanation is creation. I know that this is anathema to physicists, as indeed it is to me, but we must not reject a theory that we do not like if the experimental evidence supports it. 52. John O'Keefe, 1916 to 2000, NASA astronomer, planetary scientist, and a major leader in developing the American lunar science program during the early Project Apollo era. If the universe had not been made with the most exacting precision, we could never have come into existence. It is my view that these circumstances indicate the universe was created for man to live in. 53. Vincent Fleury, 1963 to the present, biophysicist, researcher at CNRS, and teacher at the École Polytechnique. What is consonant with physics as we currently understand it is either a God who fixed everything at the beginning, or one who intervenes in the reduction of a quantum wave packet. Everything else is physically impossible unless God does not respect the laws of physics. 54. Walter Kahn, 1923 to 2016, physics professor at the University of California and winner of the 1998 Nobel Prize in Chemistry. There continue to be very deep epistemological questions about the significance of sharp scientific laws like the laws of quantum mechanics and the laws that govern the nature of chaos. Both of these fields have irreversibly shaken the 18th and 19th centuries' purely deterministic, mechanistic view of the world. 55. Pierre Perrier, 1935 to the present, mathematician, logician, and physicist. The argument that it was all simply a matter of time and that there was a sufficient amount of it after the Earth had formed flies in the face of numerical reality. The proponents of this or that metaphysics must take into account the combinatorial explosion that results from all possible configurations, while also respecting the chronologies and duration of formation of the real world that surrounds us, which forms the backdrop against which we may launch attempts to falsify the available theories. 56. Bernard d'Espagnat, 1921 to 2015, professor of physics at the University of Paris. Quantum mechanics has delivered us from the lead cloak of deterministic materialism. Again, Bohr has unmade what Copernicus had made. He has put man back at the center of his own representation of the universe. 57. Stephen Hawking, 1942 to 2018, professor of mathematics at Cambridge, who, despite the following words, was an atheist all the same. If the rate of expansion 1 second after the Big Bang had been smaller by even 1 part in 100,000 million, the universe would have recollapsed before it ever reached its present size. Again, the laws of science contain many fundamental numbers. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. Again, what is it that breathes fire into the equations and makes a universe for them to describe? Finally, the odds against a universe like ours emerging out of something like the Big Bang are enormous. I think clearly there are religious implications whenever you start to discuss the origins of the universe, but I think that most scientists prefer to shy away from the religious side of it. 58. Sir James Hopwood Jeans, 1877 to 1946. British physicist, astronomer, and mathematician. The stream of knowledge is heading towards a non-mechanical reality. The universe begins to look more like a great thought than like a great machine. Mind no longer appears as an accidental intruder into the realm of matter. 59. Joe Rosen, 1937 to the present. Professor of physics at Tel Aviv University and the University of Central Arkansas. The anthropic principle is among the most important fundamental principles around, even, let me dare venture, the most basic principle we have. 60. Nicolas Gizon, 1952 to the present. Professor of physics at the University of Geneva and specialist in quantum mechanics. Non-local correlations seem, in some way, to emerge from outside space-time. Who keeps track of who is entangled with whom? That is, where is the information stored? Are there angels manipulating enormously huge Hilbert spaces? Let us emphasize that we take such questions very seriously. 61. David Gross, 1941 to the present, professor of theoretical physics at the University of California, 2004 Nobel laureate. The danger of the anthropic principle is that it is impossible to disprove. 62. Jeffrey Chew, 1924 to 2019, professor of theoretical physics at Berkeley. Appeal to God may be needed to answer the origin of the universe question. 63. Hubert Reeves, 1932 to 2023, popular astronomer and professor of astrophysics at the University of Paris and the University of Montreal. The laws governing physical forces possess remarkable properties. They seem to us to be fine-tuned to promote complexity. Tiny variations of the numerical values that specify them would be enough to render the universe sterile. No life form, no complex structure would ever have arisen from it, not even an atom of carbon. 2. Biology and Life Sciences. 64. Sir Francis Crick, 1916 to 2004, co-discoverer of DNA in 1953, winner of the 1962 Nobel Prize in Medicine. At present, the gap from the primal soup to the first RNA system capable of natural selection looks forbiddingly wide. An honest man, armed with all the knowledge available to us now, could only state that in some sense the origin of life appears at the moment to be almost a miracle, so many are the conditions which would have had to have been satisfied to get it going. Again, we can't help but notice the intrinsic beauty of the DNA double helix. It is the molecule which has style. 65. George Wald, 1906 to 1977, professor of sensory physiology at Harvard, Nobel Prize in Medicine in 1967. And now for my main thesis. If any one of a considerable number of the physical properties of our universe were otherwise, some of them basic, others seemingly trivial, almost accidental, that life, which seems now to be so prevalent, would become impossible here or anywhere. Again, when it comes to the origin of life, there are only two possibilities: creation or spontaneous generation. There is no third way. Spontaneous generation was disproved 100 years ago, but that leads us to only one other conclusion, that of supernatural creation. We cannot accept that on philosophical grounds, therefore we choose to believe the impossible, that life arose spontaneously by chance. 66. Richard C. Lewontin, 1929 to 2021. Harvard evolutionary biologist. We take the side of science in spite of the patent absurdity of some of its constructs, in spite of its failure to fulfill many of its extravagant promises of health and life, in spite of the tolerance of the scientific community for unsubstantiated just-so stories, because we have a prior commitment, a commitment to materialism. Moreover, that materialism is absolute, for we cannot allow a divine foot in the door. 67. Ilya Prigogine, 1917 to 2003, Nobel Prize in Chemistry in 1977, and Isabel Stengers, philosopher, epistemologist, born in 1949. In biology, the opposition between anti-reductionists and reductionists has often taken the form of a rivalry between fraternal enemies, proponents of internal finality versus those advocating for external finality. The idea of an immanent organizing intelligence is thus countered by a model of organization borrowed from the technology of the era, mechanical, thermal, or cybernetic machines, which immediately raises this objection: who assembled the machine? Is this automaton governed by an external purpose? 68. Christian Duduve, 1917 to 2013, biochemist, winner of the 1974 Nobel Prize in Physiology. God plays dice because he is sure to win. I opted for a meaningful universe, not a meaningless one. Not because I wanted it to be that way, but because that's how I interpret the scientific data we have. The universe was pregnant with life and the biosphere with man. 69. John Eccles, 1903 to 1997, neurologist, electrophysiologist, winner of the 1963 Nobel Prize in Medicine. I maintain that the human mystery is incredibly demeaned by scientific reductionism, with its claim in promissory materialism to account eventually for all of the spiritual world in terms of patterns of neuronal activity. This belief must be classed as a superstition. Again, I am constrained to attribute the uniqueness of the self or soul to a supernatural spiritual creation. 70. Werner Arber, 1929 to the present. Microbiologist and winner of the 1978 Nobel Prize in Medicine. Life only starts at the level of a functional cell. The most primitive cells may require at least several hundred different specific biological macromolecules. How such already quite complex structures may have come together remains a mystery to me. The possibility of the existence of a creator, of God, represents to me a satisfactory solution to this problem. 71. Jacques Monod, 1910 to 1976, atheist, biologist and biochemist from the Pasteur Institute in Paris, Nobel Prize in Physiology or Medicine in 1965. The machinery by which the cell, at least the non-primitive cell, which is the only one we know, translates the code consists of at least 50 macromolecular components which are themselves coded in the DNA. Thus the code cannot be translated except by using certain products of its translation. This constitutes a baffling circle, a really vicious circle, it seems, for any attempt to form a model or theory of the genesis of the genetic code. 72. Ernst Chain, 1906 to 1979, professor at the universities of Berlin, Cambridge, and Oxford, pioneer in the development of penicillin, and 1945 Nobel laureate in physiology or medicine. I would rather believe in fairies than in such wild speculation. I have said for years that speculations about the origin of life lead to no useful purpose, as even the simplest living system is far too complex to be understood in terms of the extremely primitive chemistry scientists have used in their attempts to explain the unexplainable that happened billions of years ago. God cannot be explained away by such naive thoughts. 73. Simon Conway Morris, 1951 to the present, professor of paleontology at Cambridge. The evolutionary routes are many, but the destinations are limited. In essence, this approach posits the existence of something analogous to attractors by which evolutionary trajectories are channeled towards stable nodes of functionality. The nodes of occupation are effectively predetermined from the Big Bang. If the universe is actually the product of a rational mind and evolution is simply the search engine that in leading to sentience and consciousness allows us to discover the fundamental architecture of the universe, then things not only start to make much better sense, but they are also much more interesting. Farewell, bleak nihilism, the cold assurances that all is meaningless. We are indeed dealing with unfinished business. God's funeral? I don't think so. 74. Sarah Woodson, 1967 to the present, professor of biophysics at Johns Hopkins University, speaking about the nanomachines, such as the flagellar motor, in various types of cells. The cell's macromolecular machines contain dozens or even hundreds of components, but unlike man-made machines, which are built on assembly lines, these cellular machines assemble spontaneously from their protein and nucleic acid components. It is as though cars could be manufactured by merely tumbling their parts onto the factory floor. 75. George Church, 1954 to the present, atheist, professor of genetics at Harvard and MIT, and director of the Center for Computational Genetics. The ribosome is the most complicated thing that is present in all organisms. If I were to be an intelligent design defender, that's what I would focus on. How did the ribosome come to be? But isn't it the case that, if we take all the life forms we have so far, isn't the minimum for the ribosome about 53 proteins and 3 polynucleotides? That's really marvelous. Nobody has constructed a ribosome that works well without proteins. 76. Wilder Penfield, 1891 to 1976. Renowned neurologist specializing in the recall of memories through stimulation of the brain, professor at McGill University. After a professional lifetime spent in trying to discover how the brain accounts for mind, it comes as a surprise now to discover, during this final examination of the evidence, that the dualist hypothesis, body and soul, seems the more reasonable of the two possible explanations. 77. Ernst Mayr, 1904 to 2005, professor at Harvard and one of the most prominent and vocal defenders of neo-Darwinism. The problem of the origin of life poses a keen challenge. The chances that this improbable phenomenon could have occurred several times is exceedingly small, no matter how many millions of planets in the universe. 78. Michael Denton, 1943 to the present, former director of Prince of Wales Hospital's Genomics Lab, Sydney, Australia, professor of biochemistry at the University of Otago, New Zealand. In short, the laws of physics are supremely fit for life, and the cosmos gives every appearance of having been specifically and optimally tailored to that end. There is simply no tolerance possible in the design of the celestial machine. For us to be here, it must be precisely as it is. The new picture that has emerged in 20th century astronomy presents a dramatic challenge to the presumption which has been prevalent within scientific circles during most of the past 4 centuries, that life is a peripheral and purely contingent phenomenon in the cosmic scheme. These advances in astronomy and physics have established what for Newton and generations of natural theologians was only an affirmation of belief, that there is indeed a deep and necessary connection between virtually every characteristic of the cosmic stage and the drama of life. 79. Daniel Cohen, 1951 to the present. Professor of genetics at the University of Avery and scientific director of GenSet, a genetic engineering lab, helped map the human genome. The genome is a program written in a very sophisticated language. Could such a complex language arise by accident? We are free to suppose that, but we can't demonstrate it. Personally, I went from being an atheist to agnostic in the space of 1 year, because if this language is not the result of chance, then I suspect that one day we will be able to demonstrate it. Imagine what a sea change that would be. 80. Michael Behe, 1952 to the present. Professor of biochemistry at Lehigh University. The simplicity which one believed to be the foundation of life has been revealed to be a fantasy which has been replaced by systems of frightening complexity. The awareness that life was conceived by an intelligent being is a shock for we men of the 20th century who were made to think that life was the result of simple natural laws. 81. Dean H. Kenyon, 1939 to the present. Professor Emeritus of Biology at San Francisco State University. It is absolutely incredible to observe on this microscopic scale such a finely tuned mechanism, a device that bears the mark of intelligent design and manufacturing. We have the details of a highly complex molecular universe which manages genetic information, and it is precisely in this new branch of molecular genetics that we see evidence of the most indisputable intelligent design on Earth. 82. Pierre-Jules Lejeune, 1932 to 2007, winner of the 1991 Nobel Prize in Physics. Another thing that intrigues me is the fact that the genetic code is always the same, whereas life has adopted many different solutions. I have difficulty believing that Darwinian evolution could give rise to only a single type of code. 83. Hubert P. Yockey, 1916 to 2016. Professor of Theoretical Physics at Berkeley and specialist in information theory applied to biology and the origins of life. The origin of life by chance in a primeval soup is impossible in probability in the same way that a perpetual motion machine is impossible in probability. The extremely small probabilities calculated in this chapter are not discouraging to true believers. A practical person must conclude that life didn't happen by chance. 84. Georges Salé, 1907 to 2002, polytechnician, statistician, author of Hasard et Certitude, which opposes the invincibility of chance as theorized by Jacques Monod. It is not those who think that living beings arose through the action of an intelligent being who make appeal to miracles, but those who deny it. 85. Roger Sperry, 1913 to 1994, neurologist and winner of the 1981 Nobel Prize in Medicine. I must take issue especially with the whole general materialistic reductionist conception of human nature and mind that seems to emerge from the currently prevailing objective analytic approach in the brain behavior sciences. I suspect that we have been taken, that science has sold society and itself a somewhat questionable bill of goods. 86. Philippe Labro, 1971 to the present, researcher at the Center for Molecular Biophysics, CNRS, Orléans. For some researchers, the fact that the living cell shows a terrifying level of complexity proves that it probably could not have come about in stages, but rather that it emerged fully formed out of nothing. The probability of such an event happening is comparable to the chances of a tornado blowing over a dump heap to create a functioning Airbus A320 out of scrap metal. 87. Yves Coppin, 1934 to 2022, paleontologist and paleoanthropologist. It is still astonishing that changes for the better happen just when they are needed. In any case, chance does things better than can be believed. 88. Ali Demirsoy, 1945 to the present, professor of biological sciences at Hacettepe University in Ankara. The probability of the formation of a cytochrome C sequence, an enzyme necessary for life, is as likely as 0. That is, if life requires a certain sequence, it can be said that this has a probability likely to be realized once in the whole universe. In fact, the probability of the formation of a protein and a nucleic acid, DNA-RNA, is a probability way beyond estimate. Furthermore, the chance of the emergence of a certain protein chain is so slight as to be called astronomic. 89. Pierre-Paul Grosset, 1895 to 1985, professor of biology at the University of Paris, zoologist and ethologist. The idea that man is the result of innumerable errors in the copying of DNA during molecular duplication seems, upon reflection, absurd, not a damning fault in itself, but also contrary to reality, which condemns the idea. 90. John Joe McFadden, 1956 to the present, professor of molecular genetics at the University of Surrey. But who's doing the tweaking? Another reason scientists are wary of the anthropic principle is that it seems to reverse the Copernican revolution and place humankind at the center of the universe. Even worse, it could allow creationists to bring the G word back into science. 91. Stuart Kauffman, 1939 to the present, professor of biophysics at the University of Vermont and specialist in complex systems. Consider all proteins of length 200 amino acids. There are 20 to the 200th power or 10 to the 260th power such proteins. Were the 10 to the 80th particles in the universe to do nothing but make proteins length 200 on the Planck timescale, it would require 10 to the 39th times the lifetime of the universe to make all these proteins just once. 92. Perry Reeves, 1945 to the present, professor of chemistry at Abilene Christian University. When one examines the vast number of possible structures that could result from a simple random combination of amino acids in an evaporating primordial pond, it is mind-boggling to believe that life could have originated in this way. It is more plausible that a great builder with a master plan would be required for such a task. 93. Francis Collins, 1950 to the present, geneticist, director of the American National Institute of Health, and specialist in the sequencing of the human genome. Belief in God can be an entirely rational choice, and the principles of faith are, in fact, complementary with the principles of science. 94. Bruce Lipton, 1944 to the present, professor at the University of Wisconsin. As a conventional biologist, I believed that I was merely a mechanism and that my life was nothing but the folds of molecules, and so I felt that I was only an accident, as Darwin had said. My research in cellular biology showed me that I was far more than my physical reality, and that there was an energy, a spirit, or a God that controlled the laws of biology. 3. Mathematics. 95. Kurt Gödel, 1906 to 1978, logician and professor of mathematics at Princeton. Mechanism in biology is a prejudice of our time which will be disproved. In this case, one disproof, in my opinion, will consist in a mathematical theorem to the effect that the formation within geological time of a human body by the laws of physics, or any other laws of similar nature, starting from a random distribution of the elementary particles in the field, is as unlikely as the separation by chance of the atmosphere into its components. There is a scientific, exact philosophy and theology, this is also more highly fruitful for science, which deals with the concepts of the highest abstractness. Est Deus. God exists. 96. Paul Dirac, 1902 to 1984. One of the fathers of quantum mechanics and winner of the 1933 Nobel Prize in Physics. God is a mathematician of a very high order, and he used very advanced mathematics in constructing the universe. 97. Alexander Polyakov, 1945 to the present, mathematician, professor at Princeton. We know that nature is described by the best of all possible mathematics because God created it. 4. Philosophy of Science. 98. Antony Flew, 1923 to 2010, professor of philosophy at the University of Reading and one of the greatest atheist philosophers of our time. He chose atheism at age 15 and wrote against divine creation for more than 54 years. The title of his article, Theology and Falsification, is the most explicit. He publicly renounced this stance in 2004 and later said, with regret, "As people have certainly been influenced by me, I want to try and correct the enormous damage I may have done." Again, the most impressive arguments for God's existence are those that are supported by recent scientific discoveries. The argument to intelligent design is enormously stronger than it was when I first met it. Also, what I think the DNA material has done is that it has shown, by the almost unbelievable complexity of the arrangements which are needed to produce life, that intelligence must have been involved in getting these extraordinarily diverse elements to work together. When you examine RNA as a chemist, you simply experience such complete awe before a molecule that is so wondrous, as well as before its magnificent complexity, that you ask yourself the question, how is it possible that this structure appeared? 99. Edward Feser, 1968 to the present, American atheist turned Catholic philosopher, professor of philosophy at Pasadena City College in Pasadena, California. I don't know exactly when everything clicked. There was no single event, but a gradual transformation. As I taught and thought about the arguments for God's existence, and in particular the cosmological argument, I went from thinking, these arguments are no good, to thinking, these arguments are a little better than they are given credit for, and then to, these arguments are actually kind of interesting. Eventually it hit me. Oh my goodness, these arguments are right after all. By the summer of 2001, I would find myself trying to argue my wife's skeptical physicist brother-in-law into philosophical theism. 100. Neil Manson, professor of philosophy at the University of Mississippi. The multiverse hypothesis is alleged to be the last resort for the desperate atheist. 14. What do scientists believe in? The previous chapter explored the challenges and surprises that some of the greatest scientists of the 20th century faced as they grappled with the implications of their own discoveries. This leads us to the related question of belief among scientists in general. Conventional wisdom holds that modern scientists are not very religious, or at least far less religious than the general population. Some people consider this a sign that science leads naturally to unbelief, an indirect proof that God does not exist. To address this common perception, this chapter will study belief among scientists in depth, analyzing a selection of surveys and studies on the question. The first thing to note is that the claim is made up of two distinct underlying questions that we will consider separately. 1. Do materialist scientists today outnumber the scientists who believe in something? Do they represent an overwhelming majority? 2. If unbelieving scientists are indeed an overwhelming majority, is this a consequence of their scientific knowledge or of other factors? 1. Let us begin by examining the major studies on religious belief among scientists. 1. A 2009 study by the Pew Research Center, Scientists and Belief, has the largest sample size and is the most recent of studies on the issue. It shows that a majority of American scientists, 51%, believe in something, while a minority, 41%, are atheists. 7% of scientists polled declined to answer the question. If we compare these results with rates of belief among the general population, it is undeniable that a greater proportion believe in something. Believers made up 95% of those surveyed. It is worth noting that younger scientists, those under the age of 34, are much more likely to claim some kind of belief, 66%, than older researchers. In fact, only 46% of researchers over 65 claimed some form of belief. This study is so valuable because it is recent, 2009, and takes into account researchers working in every scientific field. Additionally, the survey was carried out in the United States, the undeniable world leader in scientific research and a place where scientists are particularly numerous. In contrast to other studies, the survey offered a wide selection of possible responses, including, for example, belief in a creative spiritual being that is not a personal God. The survey provided space for respondents to express their doubts and even allowed them to skip questions they did not wish to answer. 2. A 2003 study by geneticist Baruch Abba Shalev analyzed the beliefs of all Nobel laureates since the prize's inception. Entitled 100 Years of Nobel Prizes, the study showed that 90% of Nobel Prize winners identified with some religion, and that 2/3 of them have been Christians. Further, 35% of the recipients of the Nobel Prize in Literature have been atheists, as compared with only 10% among scientists. Incidentally, this goes to show that, at least according to this survey, there are more atheists in the field of literature than in the sciences. Between 1901 and 2000, the 654 Nobel laureates belonged to 28 different religions. A majority of them, 65.4%, identified as Christian. More precisely, Christians won 72.5% of the prizes awarded in chemistry, 65.3% in physics, 62% in medicine, and 54% in economics. Jews were awarded 17.3% of the prizes in chemistry, 26.2% in medicine, and 25.9% of the prizes in physics. Atheists, agnostics, and freethinkers were awarded 7.1% of the prizes in chemistry, 8.9% in medicine, and 4.7% in physics. Muslims have won 13 prizes in total, or 2% of the total prizes awarded, including 3 in the scientific categories. This second survey is of interest because while its scope is very broad in terms of time and space, it concerns only Nobel Prize recipients. Since Nobel laureates represent the world's scientific elite, their opinions and beliefs carry more weight than those of the general population. As the Nobel Prize was created in 1901, the study spans the entire 20th century. The questionable aspect of this survey is the uncritical identification made between culture and belief, which in no way guarantees that the belief is actually embraced by the individual concerned. 3. In a 1989 survey of heads of research units in the exact sciences at the French National Center for Scientific Research, 110 of the researchers surveyed described themselves as believers, 106 as unbelievers, and 23 as agnostic. 70% believed that science can neither prove nor disprove the existence of God. The percentage of believers in this study is similar to the 2009 study cited above, around 50%. 4. James H. Luba's studies. 2 studies undertaken in 1914 and 1933 by the American psychologist James H. Luba showed disbelief increasing over time among people identified as what the study terms greater scientists, while the percentage had remained stable among scientists in general since 1914, around 60.7%. What were his criteria for making this judgment? There is no answer. These first 4 studies show relatively homogeneous results. We will now consider 2 others that draw a diametrically different conclusion, that believers make up a very small percentage of scholars. 5. A 1998 Nature study entitled Leading Scientists Still Reject God reported that among the American scientists of the National Academy of Scientists, only 7% described themselves as believers, 20% as agnostics, and all the rest as atheists. What the study does not tell us is that this academy was founded in 1867 in the context of a bitter polemic between science and religion. Since its foundation, all members have been hand-picked for their commitment to the Academy's particular ideals. The percentage of its scholars who are believers is so markedly different from that found in the other studies that it is obviously unrepresentative. Even the title of the study, Leading Scientists Still Reject God, displays a marked bias that reinforces our doubt about the survey's objectivity. 6. A survey of 1,074 members of the British Royal Society carried out by E. Cornwell and M. Sturrett by email in 2007 presents a similar case. 86% of respondents categorically denied believing in a personal God, while only 3% said they believed. As with the previous survey, this study has the major defect of being confined to one academy whose limited number of members has always been self-selecting. The resulting figures are a statistical anomaly, making this study as questionable as the last and deserving of similar skepticism. As we see it, the results of the last two studies are compromised by bad sampling. Their sample sizes are limited and unrepresentative, since the scholars surveyed belong to academies with a self-selecting closed membership. The conclusion that emerges from the first four surveys, whose sample size is in fact large enough to be statistically significant, is that the proportion of scientists who believe in something remains high. According to the first study, believers even constitute a majority in the United States, the world's leading producer of scientific research. Therefore, the claim that scientists who believe are now only a small minority is completely unfounded and inaccurate. 2. Let us now examine the fact that the proportion of believers among scientists is smaller than the proportion of believers among the general population, and let's see what factors might cause this difference. What are we to make of the fact that the percentage of scientists who are believers is lower than that of believers in the general population? What factors might be at the root of this difference? If we go by the results of the Pew Research Center's poll, the most recent and broadest survey of the scientific community, we find that, as in most studies of this type, the number of respondents who believe in something is lower among American scientists, 51%, than among the rest of the U.S. population, 95%. This difference could be chalked up to several causes, including science itself, the socioeconomic class of scientists, the historic conflicts between science and religion, the very recent nature of the discoveries supporting the existence of a creator God, the thermal death of the universe, the Big Bang, fine-tuning, the improbability of life arising by chance, etc. 1. The influence of socioeconomic status on belief. A recent survey from the Pew Research Center was categorical. Wherever you are in the world, the richer you are, the less religious you are. This phenomenon, already mentioned in the introduction to this book, should come as no surprise. Material comfort, the security of social systems, and medical progress have made turning to any god to solve mankind's problems seem unnecessary. If we look at the Pew Research Center's study in detail, the correlation between standard of living and disbelief is extremely well established. Since scientists tend to be well off, it might be expected that they are less religious than others. The correlation between belief and standard of living is firmly established, but there has not yet been any empirical evidence establishing a correlation between belief and scientific education. It is therefore impossible to claim at this stage that science makes people less religious. If scientists are indeed less religious than the rest of the population, it is possible that this is simply attributable to their high standard of living. 2. Correlation is not causation. Hasty correlations often lead to false conclusions. The question of correlation is a complex one. Here we are dealing with a well-established and clear correlation between a low-status, high-belief group and a high-status, low-belief group, and scientists belong to the latter. It is therefore unsurprising that, due to this factor alone, scientists tend to be less religious than the average person. If we aren't satisfied with that answer, what would it take to prove a causal relation between advanced scientific knowledge and lack of belief in God? We would start by determining more precisely how the standard of living parameter functions as a factor in disbelief. This would require a similar survey of individuals in a variety of professional sectors who enjoy a comparable standard of living, but have no special scientific knowledge. We could study professors, lawyers, writers, and actors, for example. If it turned out that the people of this category, enjoying a social status and high standard of living comparable to leading scientists but without their advanced scientific knowledge, believed in God at a higher rate, then we could conclude that there is indeed a causal link between greater scientific knowledge and a decreased belief in God. Inversely, if individuals of socially equivalent status but lacking advanced scientific training turn out to have similar rates of unbelief to those of scientists, then science can be eliminated as a factor influencing unbelief. Unfortunately, to our knowledge, none of these surveys have been conducted, nor is it at all certain that they would be conclusive. What would happen if it turned out that professors, philosophers, actors, and writers were just as unbelieving as scientists? The popular myth of causality between science and disbelief would definitively fall apart. We are not claiming that there is no causal link between science and belief, as we do not have the data to prove this. What we do claim is that based on the evidence available today, it is impossible to draw a conclusion from this correlation. The limited data available to us does tend to make us doubt it. As noted above, Nobel Prize-winning scientists are much more likely to be believers than the winners of the top prize in literature. 3. Long-standing conflicts between science and religion. Although most of the great scientific discoveries of the modern era were made by Christian scientists, scientists who remained Christian even after they made their discoveries, like Copernicus, Galileo, Newton, and Kepler, their findings, perhaps inevitably, sparked lively controversy. But these controversies were often instrumentalized by Christianity's detractors. As a result, the history of modern science is usually told as a battle between scientists struggling to spread their discoveries and religious people attempting to maintain their own interests and worldview. Perhaps influenced by this version of scientific history, many scientists of our time have rejected religion in general, and by extension the very idea of the existence of God. It is obviously impossible to put a precise figure on the impact of this distorted historical narrative, but it is important to keep in mind nonetheless. 4. Many scientific discoveries favoring the existence of God are very recent. New and convincing scientific proofs for the existence of a creator God have only emerged very recently, most of them only within the last generation. The thermal death of the universe was not definitively proved until 1998. The necessity of a beginning to the universe, Borde-Guth-Vilenkin theorem, dates only to 2003. The discovery of the fine-tuning of the universe dates only from the 1980s. The complexity of DNA and the intricacy of the smallest living cells, coupled with the improbability of life arising through pure chance, was discovered only in the early 1960s. The controversies generated by these modern discoveries resemble the uproar provoked by Galileo and Darwin in their own times and are probably just as inevitable. How long did it take for Darwin's discoveries to be accepted? Perhaps 100 or 150 years? No doubt this new proof for the existence of God will also take time to produce its effect. According to a Pew study included in the bonus PDF, the percentage of younger American scientists who believe in something, 66%, is strikingly higher than the percentage of scientists over 65, only 46%, who do. The survey may illustrate the early stages of a shift in opinion among scientists. 5. Another thing to consider when drawing a causal relationship between belief and scientific knowledge. Baruch Abba Shalev's study revealed that Nobel laureates in science are more religious than Nobel laureates in literature. The fact is of utmost importance because Nobel Prize winners are held to be remarkable regardless of the field in which they excel. We can therefore learn from this that, among remarkable individuals, science is more of a factor in belief than disbelief. Conclusion. The first assumption noted at the beginning of this chapter, that there are not many believers among scientists today, is at best unfounded and probably inaccurate. The second assumption is equally baseless. There is no verifiable evidence to support the claim that scientists are less religious because of their scientific knowledge. It is likely that we need to look at other factors, such as their socioeconomic status or the fraught history of science itself, to explain this tendency. 2 more surveys of scientists on the question of religious belief. In a 2002 report analyzing 43 studies conducted since 1927, Mensa, an association of gifted people with an IQ over 132, some 2% of the population, concludes, the higher one's intelligence or education level, the less one is likely to be religious or hold beliefs of any kind. Once again, we encounter a logical fallacy. A correlation is observed and wrongly presented as causation without any justification. A study published by CIRST, Centre interuniversitaire de recherche sur la science et la technologie, based in Montreal, Canada, and carried out by two sociologists, Christophe Tallien, research fellow at CNRS, and Yves Gingras, professor of history at the University of Quebec in Montreal, concludes, the more religious one is, the less competent in science. The two authors carried out a comparative analysis of religious practice, belief, and level of scientific advancement with samples taken internationally. For them, the results seem clear. The more people identify with and practice a religion, the weaker their scientific skills are. As a general rule, more religion translates into less science. This CIRST study commits the same error as did the previous one. It confounds correlation and causation. How can we account for the significant differences between the conclusions of these various studies? How is it possible that in dealing with a question as apparently simple as, does science make people believe less in God, we find studies with results at opposite ends of the spectrum? On one hand, we find 51% of U.S. scholars believing in something, according to the Pew Research Center study, and 90% of the Nobel Prize-winning scientists self-identified as believers in Barak Abba-Shalev's dubious study. With only 3% of scholars reported as believers in Cornwell and Sturrott's study, we get the impression that on this topic it is possible to read everything and its opposite. These divergent results likely stem from the sensitive nature of the subject itself. The problem of the existence of God, which underlies the relationship between science and belief, is difficult to approach dispassionately. This translates into the choice of methods, whether conscious or not, that skew the poll's results according to the presuppositions of the surveyors. As we have already seen, multiple parameters are subject to bias here. Poorly worded questions, correlation hastily interpreted as causation, non-representative or even clearly biased samples, statistics based on averages between groups that are too different. As we come to the end of these two chapters devoted to the opinions of scientists in general on this matter, a question springs naturally to mind. What were the beliefs of the scientists who played a major role in the great scientific advances of the 20th century? Two such cases prove particularly interesting, that of Einstein, without question the greatest physicist of the last century, and Gödel, whom John von Neumann called the greatest mathematician and logician since Aristotle. As we shall see in the two chapters to follow, these two men were no strangers to the question of God. What's more, their reflections on the question of the existence of God appear to have been directly linked to their scientific work, and this has been the case for many other scholars in recent decades. Several great atheist or agnostic scientists became deists purely on the basis of 20th century scientific discoveries. In The Return of the God Hypothesis, Stephen Meyer gives a few examples, including Fred Hoyle, who is convinced by the discovery of the astonishing adjustments needed for the genesis of carbon in the stars, see page 164, and famous Caltech astronomer Alan Sandage, page 31, as well as his colleague Owen Gingerich, page 31. But also physicist George Greenstein, page 176, and biologist Dean Kenyon, page 204.